Hi, my name is Janani Ravi, and welcome to this course on digital transformation with the cloud. Digital transformation with the cloud involves leveraging cloud techniques to innovate, streamline operations, and enhance business agility. It enables organizations to adopt new business models, improve customer experiences, and drive significant efficiencies through scalable and flexible cloud solutions. In this course, you will learn about the Cloud Digital Leader certification, including an overview of the certification's requirements, exam details, and key topics. This will provide you with a clear understanding of the skills needed to achieve the certification. Next, you will explore the fundamentals of cloud computing, focusing on its core principles and benefits such as scalability, cost efficiency, and flexibility. You will also examine how cloud computing drives digital transformation with case studies illustrating real world applications and benefits. Finally, you will learn about different cloud deployment models, including private, public, hybrid, and multi cloud environments. You'll also cover various cloud service models such as infrastructure as a service, platform as a service, and software as a service. This will equip you with the knowledge to navigate and leverage cloud solutions to drive digital transformation within organizations. Hi, and welcome to the certification journey. If you're preparing for the Cloud Digital Leader certification on the Google Cloud platform, well, you've come to the right place. Now, the Cloud Digital Leader certification is by far the simplest and easiest certification that the Google Cloud has to offer. It's specifically meant for a non technical audience, and it's meant to get you up to speed with what the Google Cloud has to offer for businesses. In this video, I'll introduce you to the Cloud Digital Leader certification exam. I'll give you a brief overview of the different certifications that Google offers and who the target audience is for each certification exam. Let's start with the Cloud Digital Leader. This certification is for anyone who wishes to demonstrate their knowledge of cloud computing basics and how Google Cloud products and services can be used to achieve an organization's goal. This certification is ideal for business professionals seeking foundational cloud knowledge. So, if you happen to fall in that category, you've come to the right place to learn. I make the assumption that you know absolutely nothing about the cloud, whether it's Google Cloud or some other cloud platform, and we start from the very basics. We explain the basic cloud concepts and terms, network terminology and infrastructure terminology, and we'll discuss a diverse range of Google products and services meant for compute, storage, networking, artificial intelligence, and more. A little more technical than the Cloud Digital Leader certification is Google's certification for Associate Cloud Engineer. This certification is for candidates who have a solid understanding of Google Cloud fundamentals and have experience deploying cloud applications, monitoring operations, and managing enterprise solutions. This certification is best for entry level IT professionals and those who are transitioning to cloud roles. So let's say you're technical, but you've been working in a different field. Maybe you've been working with data. Maybe you've been performing some administration in an on premises center and you want to transition to the cloud. This is the right certification. This provides hands on skills and job readiness. And when you become more of an expert on the Google Cloud, you'll be ready to tackle the professional certifications that Google Cloud has to offer. Now, there are a whole range of professional certifications. These are all meant for candidates with in depth experience working hands on, setting up cloud environments for organizations. These certifications are suitable for experienced professionals seeking to validate and demonstrate their advanced skills in specific areas such as architecture, data engineering, development, security, networking, artificial intelligence, and so on. Let's quickly understand the other categories of certifications before we focus on Cloud Digital Leader. Let's start with the Associate Cloud Engineer and understand the target audience and the benefits of this certification. This certificate is a beginner level technical certification. The target audience includes entry level cloud engineers, IT professionals who are looking to transition to cloud roles, or individuals who are new to the Google Cloud but expect to work hands on the Google Cloud. The main focus of this certification is on hands on skills deploying, monitoring, and maintaining projects on the Google Cloud. Studying for this certification requires a lot of practical, hands on training. But again, this is an entry level certification, so it's a credential for beginners and it serves as a stepping stone for those new to cloud engineering, validating their ability to work with the Google Cloud. The Associate Cloud Engineer certification prepares individuals for roles such as cloud engineer, cloud administrator, and other similar positions. The professional certifications, of course, are much more difficult and require in depth knowledge of Google Cloud services. The Google Cloud offers a range of professional certifications focusing on different aspects of the Google Cloud. For example, the professional cloud architect, the target audience includes experienced cloud professional solution architects and IT leaders, and it validates advanced skills in designing, developing, and managing robust, secure, and dynamic solutions on the GCP. The professional data engineer certification requires you to demonstrate expertise in designing and building data processing systems, managing data analysis, and ensuring data quality on the Google Cloud. The target audience is data professionals, data engineers, and analysts. The professional cloud developer is focused on software developers and engineers, and this is where you focus on building scalable and highly available applications using Google recommended practices and tools. The cloud security engineer is meant for security professionals and IT administrators, and it certifies your skills in designing and implementing secure infrastructure on the Google Cloud, managing access and identity, and protecting data. Then there is the professional cloud network engineer targeted at network engineers and cloud architects, and it covers advanced networking concepts, ensuring candidates can design, implement, and manage network architectures on the Google Cloud. There are other certifications here in the professional certifications category: professional DevOps engineer, professional machine learning engineer, professional cloud database engineer, and so on and so forth. I wanted to give you an overview of what else was out there in terms of Google Cloud certifications. But what we are really interested in today is the Cloud Digital Leader, which requires no technical prerequisites. The target audience here is business decision makers, executives, managers, and team leaders who make strategic decisions about technology and need to understand the potential of cloud computing. This certification is useful if you're one of them, or if you're working in a non technical role, such as marketing, finance, legal, operations, who work alongside the technical team and need a basic understanding of cloud concepts. This certification is also the right one if you're an absolute newbie and have never worked on the cloud. Individuals new to the cloud who want to build a foundational knowledge before pursuing more technical certifications. Again, this is a great certification to start off with. Another category of individuals who could benefit from this certification are consultants and advisors, professionals who advise businesses on digital transformation and need to understand cloud services and their impact on business processes will also find the Cloud Digital Leader certification helpful. How is this certification going to help you? This certification will give you foundational cloud knowledge. It provides a comprehensive introduction to cloud computing concepts, the services offered on the Google Cloud, and how those services can be applied in business contexts. If you're a business professional working with technical teams, you need to have an understanding of their terminology and what and how exactly they're working on things. This certification will help non technical teams communicate more effectively with technical teams. As a business professional, you're likely focused on innovation in your organization. This certification can give you strategic insights to help you identify opportunities for leveraging cloud technologies to drive innovation, efficiency, and competitive advantage. The certification is also great for career advancement. It allows you to demonstrate that you have an understanding of cloud technology, and this can be beneficial for your career growth and transition into roles that interact with cloud environments. The certification can help professionals understand how to use cloud services to support business goals, optimize operations, and drive digital transformation initiatives. The content covered in the certification is divided into six broad categories or sections. The first section is digital transformation with the Google Cloud. This is where you demonstrate an understanding of the role of cloud computing in driving digital transformation. This section will test you on your understanding of how cloud technologies can enable organizations to innovate, improve efficiencies, and create new business models. Another section is exploring data transformation with the Google Cloud, which is where you need to demonstrate an understanding of the role of data in modern business and how Google Cloud services can be used to collect, store, process, and analyze data. In order to tackle this section, you need a good understanding of the stages of data from ingestion to analysis and visualization and how they can be achieved using Google Cloud services. Another section is innovating with Google Cloud artificial intelligence. This is where you should be able to demonstrate the potential of AI to transform businesses and how Google Cloud's AI and machine learning services can be utilized. Modernizing infrastructure and applications with the Google Cloud is another section. This is where you need to demonstrate an understanding of modernizing IT infrastructure and applications to leverage the benefits of cloud computing. You need to understand cloud migration, microservices and containers, and serverless computing in order to tackle questions that relate to this section. Then we have trust and security with the Google Cloud. This section deals with ensuring the security and compliance of cloud environments and data. This is where you need to understand security best practices, compliance, and the security tools offered on the Google Cloud. And finally, the last section here is scaling with Google Cloud operations. This is where you understand concepts related to managing and scaling operations efficiently using Google Cloud's operational tools and services. You'll be questioned on monitoring and management, automation, reliability, and resilience of cloud solutions. Each section has equal weightage in the exam, so each section covers about 16 to 17% of the questions in the exam. So, what are some of the use cases of the certification? This will help you understand how to leverage cloud technologies to create new business models, improve customer experience, and streamline operations. This will also help you facilitate better communication and collaboration on projects that involve both technical and non technical teams, that is, cross functional projects. And finally, this certification equips consultants and advisors with the knowledge to recommend cloud solutions that align with business goals and objectives. Just a bit of exam information, I'll cover this again in the next video. The certification is earned by passing an exam that comprises of multiple choice and multiple select questions, about 50 to 60. This journey is very comprehensive and covers everything that you need for the exam, but there are also additional resources offered by Google, which I'll show you in the next video. Now, if you're completely new to the cloud, it'll take you a few weeks of dedicated study to prepare for this exam. This exam is not meant to be difficult and it's basically a lot of common sense. And finally, the exam is designed to test both the theoretical understanding and practical knowledge of cloud concepts. Now, even though the certification does not expect you to have any hands on experience with the Google Cloud, as a business professional, you're not expected to, you'll see that in this journey, I have included extensive hands on demos for a few key cloud concepts. I just feel that viewing those demos will allow you to get a better understanding of how the Google Cloud works. It's not really necessary for you to implement the demos, but viewing them and seeing how things work on the Google Cloud is a way to improve your understanding of cloud concepts. Now that I've given you a quick overview of the Cloud Digital Leader Exam certification, let's head over to the main certification page where we can see the details of the exam and the exam topics. Simply head over to cloud.google.com/learn/certification, and there you'll get all of Google's certifications we are interested in Cloud Digital Leader. And here is the main page of the certification. Here you get a quick overview of what a cloud digital leader should know and who can be successful in passing the certification exam. Articulate the capabilities of Google Cloud core products and services and how they benefit organizations. Cloud Digital Leader is the most basic certification that Google has to offer, where you have to have an understanding of all its products and services. This certification does not expect you to have extensive hands on experience with Google Cloud products. Now, the Google Cloud Digital Leader exam assesses your knowledge in these 6 broad areas: digital transformation with the Google Cloud, exploring data transformation with Google Cloud, innovating with Google Cloud artificial intelligence, modernizing infrastructure and applications with Google Cloud, trust and security with Google Cloud, and scaling with Google Cloud Operations. This journey will cover all six of these topics. This certification journey will cover all six topics in extensive detail. Assume that you're an absolute beginner and you have no idea what the cloud is about, and then I take you through all of Google's products and services for various use cases. After you're done with the certification journey, you might want to register to give the exam. You'll come here and click on this register link, and this is where you can sign up to get an exam date. You can see that this Google Cloud test is powered by Criterion, and this is the page where you'll sign up for a web assessor account and then sign in and find a test location close to you and a test date that suits you. Getting a test location and a test date, that's fairly straightforward. Nothing that you need worry about. Let's focus on our study. I'm back here on the Cloud Digital Leader registration page and I click on this View FAQs button. This is a great page that answers a bunch of basic questions about the certification. This is where you can navigate all of Google Cloud certifications, know why you should get certified, the benefits that you receive once you have the certification. The Cloud Digital Leader is a proctored exam that can be conducted remotely or at a test center. And here you'll find the resources for on-site and remote proctored certification exams. Google itself offers a bunch of exam preparation resources, and you can access these here as well. This is a useful page, you should know that it exists, and I just wanted you to be familiar with the Cloud Digital Leader certification page. Here on the main certification page, let's scroll down and you'll find important details about the exam. You can see it's a 1.5 hour exam, length is 90 minutes. At the time of this recording, the cost of giving the exam is $99. The exam is available in English and Japanese, and the exam format comprises of 50 to 60 multiple choice and multiple select questions. You'll find that you have about 1.5 minutes to answer each question, and that should be a fairly decent length of time. Good preparation with the help of this journey should allow you to answer those questions within the time limit. Notice the exam delivery method. You can take an online proctored exam from a remote location. That is, you can log in from home and give the exam sitting at your study table. You'll of course have to clean up your remote location to make sure you have no study material around you. You can take a look at those requirements, or you can choose to take the on-site proctored exam at a testing center located near you, and there are centers all over the world. Observe here that the Cloud Digital Leader has no prerequisites. Prereqs, none. You only need to have experience collaborating with technical professionals, and you should be technical in that you should have an understanding of technology. The certification is valid for 3 years, and you should get recertified after 3 years if you need to. If you scroll down below, you'll find that Google gives you a nice step-by-step breakdown for how you can prepare for the exam. You need to understand what's in the exam, expand your knowledge with training. The learning path here is a video path that's very useful, but what I'm going to be covering here in this journey is far more extensive and essentially covers the same topics as Google's resources. There are additional resources available here at this link if you're interested in studying further. But what's really useful here is that the Cloud Digital Leader certification comes with some sample questions. Once you're fairly confident that you know the topics that will be covered in this exam, I suggest you come here and take the sample test and see how you perform. That will allow you to assess how well you know your study material before you take the final step, where you go ahead and schedule an exam. Let's scroll back up and take a look at the exam guide. This will give you a quick overview of all of the topics covered in the exam and all of the topics that I'm going to be covering here in this learning journey. We've seen before that the exam covers 6 broad topics, and each of these 6 topics have equal weightage. There are 6 sections here in this exam guide, and you can see that each section comprises of roughly 17% of the exam. The first section, Digital Transformation with the Google Cloud, is all about an introduction to the cloud. This is where you're supposed to know basic cloud terminology, know the difference between cloud technology and traditional on-premises technology. You should understand how digital transformation can benefit companies. You should be able to understand and describe the concepts of on-premises infra, public cloud, private cloud, hybrid cloud, and multi-cloud. You should have a solid understanding of fundamental cloud concepts. You should understand the idea of capital expenditures, operational expenditures, and the total cost of ownership, either on premises or on the cloud. You should have a basic understanding of network infrastructure terminology, and you should understand cloud computing models and the idea of shared responsibility. Within this, you should understand IaaS, PaaS, and SaaS, infra as a service, platform as a service, and software as a service, and understand the benefits and disadvantages of each. The next section is all about data transformation with the Google Cloud, and it accounts for roughly 16% of the exam. This is where you need to understand the importance of data. Now, data storage technologies such as databases, data warehouses, and data lakes, how they're different, how they help. You need to have a solid foundational understanding of the various storage technologies and services that the Google Cloud has to offer: Cloud Storage, Cloud Spanner, Cloud SQL, Cloud Bigtable, BigQuery, Firestore, and more. Of these, Cloud Storage tends to be the most important, and you'll be expected to know a bunch of nitty gritty about cloud storage. Don't worry, we'll be covering all of that in this journey. You'll also need to know about business intelligence tools such as Looker that Google Cloud has to offer, and how streaming analytics and batch analytics works. The Google Cloud platform has a very strong offering for artificial intelligence. The next section is about innovating with Google Cloud Artificial Intelligence. This is where you need to know basic concepts of AI and ML and how ML can help unlock value within an organization. You need to be familiar with Google Cloud's AI and ML solutions and discuss the range of Google Cloud solutions and products available. Solutions such as BigQuery ML, AutoML, custom training, and ML APIs. The next section is all about modernizing infrastructure and applications with the Google Cloud, again about 17% of the exam. Here we'll discuss various services and technologies offered by Google for application modernization. Google Kubernetes Engine, serverless containers with Google Cloud Run, Cloud Functions, App Engine. All of these technologies will be covered here. In this section, you need to understand the importance of using APIs for software development and the Apigee API management service that Google Cloud has. And here is where you'll need to understand the hybrid and multi cloud world in detail. Moving on to section 5, trust and security with the Google Cloud makes up another 17% of the exam. This is where we'll see how cloud applications are secured and who is responsible for what part of the security. You'll need to understand fundamental cloud security concepts, understand how Google's infrastructure takes care of security on the cloud, understand terms such as authentication, authorization, and auditing, understand two step verification and identity and access management, know the different Google Cloud security products such as Google Cloud Armor, understand what SecOps or security ops is all about, and know Google Cloud's trust principles and compliance. And finally, the last section here is scaling with Google Cloud operations, the last 17% of the exam. This section expects you to understand financial governance and how you can manage costs on the Google Cloud. You need to know how identity and access management works on the GCP and how you can use cloud billing to visualize your cost data and cloud expenditures. This is where you need to have a fairly good understanding of cloud budgeting and cloud customer care and how you can run sustainable operations on the GCP. Now that you have a big picture understanding of the various topics that are going to be covered in the exam, let's go back to the main exam overview page. And here I'm going to scroll down, and you can see step 2 here talks about expanding your knowledge with training. If you click on start preparing here, you'll be taken to a training path for the Cloud Digital Leader exam. These are video based training resources that Google makes available for absolutely free. There are courses here covering every section of the Cloud Digital Leader exam. Now, these courses are great. I consider them a great starting resource, but this journey that you're on right now, well, that's far more extensive. I went through this training and I found it kind of sparse, useful, but a little sparse. Back on the main page, there are also additional resources that you can use for your study. So, if you're interested in certain topics beyond what is covered in this learning journey, here are additional resources that you can access. And of course, once you're done with all of your preparation and you're feeling confident about what you've studied, go ahead to the sample questions. The sample questions are in the form of a Google form. I definitely recommend that you take these sample questions when you're feeling good and ready. We're now ready to dive into the course content. We'll start at the very beginning. It's a good place to start. In this video, we'll try and understand what exactly cloud computing is all about. In order to understand cloud computing, it's important that you go back in time and understand how traditional computing works. What is traditional on premises computing? This is where organizations went ahead and bought physical hardware. Traditional computing involves use of physical hardware and software resources that are installed on that hardware and managed and maintained by an organization's own team and own facilities. These resources could be servers, storage devices, networking equipment, and all necessary software applications. And all of these are physically located in the company's premises. This is how things used to work just a few years ago, and in fact, on premises computing has not yet gone away. Now, what are the characteristics of on premise computing? The organization goes ahead and purchases and owns their own servers, storage systems, networking equipment, and all other hardware that they need to support their computing needs. This hardware that they purchase is usually housed in on site data centers or server rooms and is completely managed by the organization's staff. Now, let's say the organization uses a particular application. Maybe it's an HR system or a financial system. All of the applications and operating systems for the hardware are installed directly on the organization's servers, and the licenses for the software must be purchased and managed by the organization. You need Windows Server running on your machines. Make sure you have Windows Server licenses. Once organizations have installed their hardware, they need a way to connect all of this hardware up. The organization is then responsible for setting up the internal networks to connect the hardware components and ensure that they can communicate effectively. This might include routers, switches, firewalls, and other networking devices. In traditional on premises computing, the organization's staff is responsible for management and maintenance. You need a dedicated IT team that is responsible for managing, monitoring, and maintaining the entire infrastructure. This could include tasks such as hardware repairs, software updates, security patching, and other troubleshooting issues. Software gets outdated and has bugs. The organization is responsible for managing upgrades and the scalability of your solutions. In order to scale operations, the organization has to buy and install additional hardware and configure it. Upgrading the infrastructure can end up being a very time consuming and an expensive process and require very careful planning and investment. The organization is also responsible for the security of the infrastructure and the applications. Security measures such as firewalls, which control traffic, intrusion detection systems, and physical security controls, all of this must be implemented and managed by the organization to protect against threats. I'm not sure how you feel, but I'm already getting quite intimidated by the amount of work that goes into maintaining an on premises setup. However, in return, the organization has complete control over the customization of the hardware setup as well as the software. Organizations control the hardware configurations, the software installations, and their security measures. And this allows high levels of customizations to meet specific business goals. On premise systems can be tailored to the unique requirements of the organization, providing flexibility on how resources are allocated and managed. For example, even today, many stock exchanges across the world maintain their own on premises infrastructure. Stock exchanges generally do not rely on cloud platforms for their core computing needs because their needs are so specialized and it's so critical to ensure that the stock exchange is reliable and available throughout the trading day. Next, let's discuss the costs involved with on premises infrastructure setups. We first have capital expenditure. Capital expenditure or capex refers to the significant upfront investments required to purchase hardware and software for on premises computing. Everything that you have to pay upfront in bulk. The company must go out, buy physical servers, storage devices, networking equipment, and that can be quite expensive, especially if you're a small or medium sized business. In addition to these, you have software licenses for operating systems. All these add to the initial expenses. Then there are installation and setup expenses for this infrastructure. Your capex investment depreciates over time. Hardware depreciates and becomes obsolete, And this means that you have to periodically replace or upgrade your systems, and that requires additional capital expenditures. Now, the second kind of cost that's involved is operational expenditure or OPEX. This includes the ongoing costs associated with running and maintaining on premises infrastructure. This can include power consumption for operating and cooling the hardware. This can lead to high energy bills. Effective cooling systems and the physical space required for data centers also contribute to OPEX. Also, regular maintenance, updates, repairs of hardware and software require IT staff, and their salaries are also part of OPEX. There is other stuff here: implementing backup and disaster recovery solutions, investment in security measures, insurance that you may have to buy. You can clearly see that there is a lot going on in terms of cost when you have your on premises infrastructure. On premises infrastructure served us well for a long time and still continues to serve us well, but there are clear challenges. The first is scalability. Scaling on premise infrastructure is challenging because you need significant capital investment in additional hardware. You'll have to buy new servers, networking, storage, databases. This can be very expensive and time consuming. It's also very painful to physically install and configure this hardware. You need skilled IT personnel. All of this adds to the complexity. Maintaining this infra requires continuous attention and expertise from the IT team, and you have to hire and manage the IT team yourself as an organization. You need regular software updates and patches to make sure there are no security flaws and your applications are up to date. You need hardware maintenance to prevent failures, but that's quite labor intensive and disruptive. You need routine backups to safeguard data, and you need to manage all of these backups. Clearly, lots of ongoing maintenance. And then, of course, you have to plan for disaster recovery, which is a whole other ball game. This is a complex and expensive operation. You have to have reliable backup systems to ensure that your data can be recovered in the case of natural disasters, hardware failures, or cyber attacks. Once you've seen what's involved in maintaining on premise infrastructure, it's pretty clear that organizations would be looking to improve this process and simplify this process. And cloud computing evolved to tackle these challenges. But how did the cloud come about? Let's just look at the steps first. We started off with dedicated servers, and then we set up virtual private servers. We then moved on to shared hosting, and finally, we're now at cloud hosting. Let's understand what each of these terms mean, starting with dedicated server. The dedicated server is your traditional on premise infra setup where organizations have complete control and customization over the hardware that they own themselves. The advantage of this setup is that you're not sharing your resources with others. Also, you can customize these resources for your specific use case. But we've already seen everything that's involved here. Now, slowly we moved on to having virtual private servers rather than a dedicated server. This was the first step towards more flexible resource allocation, where new virtualization technology was used to partition a single physical server into multiple virtual environments. Each virtual private server operates independently within its own operating system and resources, providing a balance between cost and performance. Virtualization technologies came into its own in the early 2000s, and this model allowed for better utilization of the hardware and easier scalability compared to dedicated servers. You do lose a little bit of control with virtual private servers, but you get more flexibility and more scalability. A further evolution over virtualization technology was shared hosting. Shared hosting just involves multiple users sharing the resources of a single physical server, making it the most cost effective and accessible option for individuals and small businesses. Each user has very limited control and customization capabilities as the server's resources and configuration are shared amongst all users. Shared hosting used to be very common for hosting websites where low traffic websites and applications are all placed in a different folder on the same physical server, and we have different users for each website. This was not a great way to share resources because there were potential drawbacks like reduce security, increase security risks, limited scalability, and so on. But this was an affordable way to get many users on the same machine. But today we have cloud hosting. Cloud hosting leverages a network of interconnected virtual and physical servers to provide scalable and flexible hosting solutions. Now, the best thing about cloud hosting is that you, as an organization, are not managing the infrastructure and maintenance of the infrastructure. Cloud hosting allows multiple users to share resources. Resources can be dynamically allocated and scaled based on demand. Any workload on cloud hosting is usually distributed across multiple servers, thus improving its performance. Cloud hosting taken to the next level is cloud computing. Cloud computing is essentially the delivery of various computing services. This includes servers, storage, databases, software, analytics, networking over the internet. Cloud computing allows businesses to move away from owning and maintaining physical data centers or servers. Businesses can access all of these services on demand from cloud providers who offer these cloud computing services. All of the hardware lives somewhere in the world. We have software running on the hardware, but users can access and manage all of these computing resources and applications through the internet. The whole idea is you access infrastructure that's maintained by a third party provider. You are not responsible for it, but all of that infrastructure is available to you to run your applications via easy to use user interfaces and command line tools over the internet. Now that we've introduced cloud computing, what are its characteristics and benefits? That's what we're going to be discussing in this video. Now, I've already defined cloud computing before. Here is the definition just to refresh our memory. This is the delivery of computing services over the internet or the cloud. The cloud refers to the internet. This includes servers, storage, databases, networking, software, analytics, and artificial intelligence. All of these services are hosted on the cloud, that is, on remote servers accessible via the internet. These services are provided by cloud service providers or CSPs like Amazon Web Services AWS, Microsoft Azure, Google Cloud Platform GCP, and others. Cloud computing allows organizations to access and use technology resources on demand without the need for owning and maintaining physical infrastructure. We know the characteristics of on premise computing. Let's compare that to the cloud. We've already seen in the previous video that managing hardware and software on premises is hard. This requires significant expertise and resources, which can be challenging for many organizations to sustain. Hiring and retaining skilled IT staff for specialized tasks such as server maintenance, network management, and cybersecurity can be expensive and difficult and out of the reach of small and medium businesses. The most important aspect of cloud computing is that these complex tasks are handled by cloud providers. So it's Amazon, Google, or Microsoft that's taking care of your infrastructure for you. These cloud providers employ experts to manage the infrastructure. This allows other organizations using the cloud to leverage the latest technologies and best practices without needing in house specialists. Organizations can thus hire specialists only to focus on core activities. By outsourcing infrastructure management to cloud providers, businesses can focus on their core activities and strategic initiatives rather than being bogged down by IT maintenance and troubleshooting. Eliminating infrastructure management frees up the organization to focus on tasks that are important for their customers. Organizations using the cloud can take advantage of the scalability and flexibility that it offers. Cloud computing provides the ability to scale resources dynamically, allowing organizations to adjust their computing power, storage, and other services in real time based on current needs. Let's say to handle peak traffic, you need 5 machines. Well, you quickly go and provision 5 machines on the cloud. In fact, cloud can automate this provisioning for you. If you find that your traffic has scaled down and you need just 2 machines, You scale down to two machines on the cloud. Because you do not own those machines, you only pay for the use of those machines. You pay for five machines when you need five, and two machines when you need two. The scaling up and down of these resources is not manual, though it can be, but it's usually automated. And this automation is referred to as the elastic nature of the cloud. Automatic scaling up and scaling down, that is cloud's elasticity. This elasticity means that businesses can quickly respond to changes in demand, such as traffic spikes during peak times or scaling down during off peak periods, ensuring optimal resource utilization and saving on costs. This is the cloud's pay as you go model. Businesses only pay for the resources that they use. Another advantage is that the cloud allows you to deploy your applications very close to where your end users are. Cloud providers operate data centers in multiple geographic locations around the globe. This global presence helps to reduce latency and enhances the user experience by ensuring faster access to applications and data. This also helps with disaster recovery and business continuity as data can be replicated across multiple locations, reducing the risk of data loss due to localized failures. Cloud providers design their infrastructure with multiple redundancies across various components. So everything is redundant. The server that you're working on, your storage systems, your networking, your databases, your analytics tools, everything. All of these are designed to ensure high availability. The architecture minimizes the risk of service interruptions by automatically redirecting traffic and workloads to healthy resources in the case of outages. Cloud providers also offer comprehensive disaster recovery solutions that include automated backups, ensuring that data is regularly and securely saved to multiple locations across the world. In the case of some kind of data loss incident, such as maybe a cyber attack or a natural disaster, these backups can be quickly used to restore your data, ensuring business continuity. Organizations do not need to build these disaster recovery solutions themselves. They can simply configure these options on the cloud. Another great advantage of the cloud is security. Cloud providers invest very heavily in advanced security measures to protect their infrastructure and customer data. This includes encryption of data both at rest, that is when it's stored in a database, and in transit, that is when it's transferred over the network. Cloud providers also offer identity and access management systems to control and monitor access to resources, ensuring that only authorized users can access critical systems. You can imagine that cloud providers are very careful about security. Google, Microsoft, and Amazon do not want security incidents to become public because it gives them a bad name. They spend a lot of time ensuring that the infra is secure. On the cloud, security follows a shared responsibility model, and we'll talk more about this a little later on in this journey. This model delineates the security roles and responsibilities of the cloud provider and the customer. The cloud provider is responsible for securing the infrastructure, that is, your servers, databases, networks, and so on. Organizations using the cloud are responsible for securing their applications, data, and any configurations that they set up. This includes managing user access, securing application code, and ensuring data privacy. Using the cloud for your software solutions really speeds up innovation because you have to do a lot less. Cloud services allow rapid deployment of applications and services, and they significantly reduce the time required to bring new products to market. On the cloud, you can provision resources quickly, you can quickly iterate on your application code, and quickly deliver features to your customers for fast feedback. And this entire deployment and delivery process can be automated end to end with tools available on the cloud. Another great thing about using the cloud is that you don't have to constantly worry about whether you're using the latest and greatest technologies and whether you're using the right tools. In order to maintain a competitive advantage, cloud providers continuously integrate the latest technological advancements such as artificial intelligence, machine learning, big data analytics, and anything that you can think of into their platforms. When the gold rush for generative AI started, all cloud providers worked extremely hard to ramp up their offerings in Gen AI. which means as a user of the cloud, you can stay at the cutting edge of innovation by using the latest tools provided by these cloud providers. A great advantage of using the cloud is that you can experiment with new features without making a significant upfront investment. You can quickly provision resources and prototype your ideas without investing a great deal of time and money. With the cloud, you can fail fast and learn fast, and businesses can quickly test and refine ideas, iterating based on feedback and results. When you're working on the cloud, you have remote access to all services. It doesn't matter where you're in the world, as long as you have an internet connection, you can work on the cloud. This makes remote work very, very simple. Cloud providers also offer a number of cloud based tools to enable real time collaboration amongst team members, thus improving the productivity and efficiency of your team. We know the costs associated with on premises computing. Let's talk about costs on the cloud. You'll find that the cloud proves to be much more cost effective than on premises infrastructure. The cloud operates on a pay as you go model where organizations only pay for the resources that they actually use. So, if you use a database, you pay for it, you pay for its storage, you pay for its uptime, but you don't pay for the database if you don't provision it. With on premises, you have to buy the storage system hosting the database, and essentially you've paid for it whether you use it or not. This eliminates the need for significant upfront investments in hardware and resources, reducing capital expenditure. The cloud makes it easier for you to manage your budgets because you can perform budget estimation based on usage rather than based on investments for the future. Cloud computing significantly reduces the need for capital expenditure by eliminating the requirement to purchase and maintain physical hardware. The upfront hardware and installation costs can be a significant burden on small and medium businesses, especially, but that's completely gone when you use the cloud. Your capex is actually converted to opex or operational expenditure, which means that your spends tend to be spread out based on usage. When you're using resources on the cloud, you're leasing those resources and you thus end up spreading costs over time and preserving capital for other investments. This shifting of capex to opex increases the operational efficiency of your business. You can monitor your resource utilization, you can optimize your resource utilization, and you only pay for what you need. You'll avoid the costs associated with over provisioning and underutilization. Before we move on to other topics, let's quickly compare on premises versus cloud computing. We know that scaling on premises requires actually purchasing and installing hardware, whereas with cloud computing, you have dynamic scaling with on demand resources. The cloud providers have already purchased a bunch of hardware, you only lease the hardware as and when you need it. With on premises, all of the maintenance, updates, and troubleshooting is managed by your IT department. Whereas with cloud computing, you just leave this all to the cloud provider and it's responsible for maintenance, updates, and security. With infra on premises, security is managed internally within the organization. Whereas when you're running on the cloud provider offers advanced security measures including encryption, identity and access management, and threat detection. On premises infra can be highly performant, but the performance and reliability actually depends on the hardware. If your hardware is not up to date, well, your performance is going to suffer. When you use the cloud provider makes significant investments in hardware and is responsible for robust infrastructure. Actually, procuring hardware is pretty painful. It involves a lot of steps and a physical component. It can really slow down innovation. With the cloud, you can rapidly deploy the resources that you need for your new prototype, and that speeds up innovation. On premises infra can incur significant upfront capital expenditure for purchasing all the equipment that you need, and this can be beyond the capability of certain businesses. Cloud computing, though, operates on a pay as you go model. So instead of capex, you convert your expenses to opex, and this tends to be much more manageable for most businesses. Now, you may have heard the term digital transformation. People are always saying things like companies need to undergo digital transformation to face the future and to innovate for the future. But what does that really mean? That's what we're going to be discussing here in this video. Here is a definition of digital transformation. We know that technology is constantly evolving and improving. Digital transformation refers to the integration of this digital technology into all areas of a business, fundamentally changing how organizations operate and deliver value to customers. Digital transformation may involve doing the same things that you did before, but you do it in a different, more efficient way thanks to digital technology. In the context of the cloud, digital transformation involves leveraging cloud computing technologies to enhance your business processes, improve efficiency, and drive innovation. Now, why do organizations undergo digital transformation? It sounds painful and disruptive to existing processes. Well, there are several reasons: to improve the efficiency and productivity of the org, for scalability and flexibility, for better cost management and an improved bottom line, for an enhanced customer experience, in order to get a leg up on innovation over their competition, and for the purposes of security and compliance. Any and all of these can be reasons to undergo digital transformation. Let's start off by talking about improved efficiency and productivity. We'll see how a digital transformation to using the cloud can help achieve this. The cloud makes automation of routine tasks easier. Cloud based tools enable automation of tasks, thus reducing manual effort and increasing efficiency. This allows employees to focus on more strategic activities. As an e commerce site, let's say you were manually moderating the reviews of your products, you can turn to cloud based solutions to automate this for you quickly and easily. Cloud platforms also provide collaborative tools that facilitate better communication and teamwork, regardless of geographic location. Collaborative tools such as Google Meet, Documents, Chat all foster faster decision making and better collaboration. Organizations have been collecting data for decades and they struggle with data silos, where information is isolated within different departments or systems, making it difficult to get a holistic view of operations. Cloud computing facilitates the integration of data from various sources into a centralized platform, breaking down these silos. This centralized management allows for more comprehensive data analysis and can help you get insights that were previously difficult or impossible to obtain. A digital transformation to the cloud improves the scalability and flexibility of your organization. The cloud allows businesses to scale resources up or down based on demand, ensuring that businesses can handle varying workloads efficiently without over provisioning or under provisioning. That's a huge advantage of the pay as you go leasing model of the cloud. Cloud services offer flexibility in adopting new technologies and adjust to market changes quickly. And this agility is crucial for staying competitive in a rapidly evolving business landscape. Earlier, switching to a new technology to improve your product, such as integrating machine learning models within your product, might require offline approvals of hardware, no more when you're using the cloud. Organizations today want to use open infrastructure that allows them to integrate various platforms and technologies seamlessly. They do not want to be tied down to one vendor or provider. This allows them to innovate faster and reduces lock in to a single cloud provider and adds flexibility to build, migrate, and manage applications. Let me explain a little bit about what open infrastructure means. Now, open infrastructure refers to open standards and open source. Open standards are publicly available and universally accepted specifications that ensure interoperability and compatibility between different software and hardware systems. They are developed through a collaborative and consensus driven process involving multiple stakeholders, industry experts, companies, and maybe even regulatory bodies. Open standards help prevent vendor lock in by allowing users to choose from a variety of compliant products and services, thus enhancing competition and innovation in the market. Examples include HTML and CSS for web development, the IEEE 802.11 for wireless networking, and JPEG for image compression. Open infrastructure also includes open source. Open source refers to software whose source code is made available to the public, allowing anyone to inspect, modify, and distribute the software. The idea behind this is to promote collaborative development and transparency, fostering innovation and improvement by leveraging the community's contributions. Open source products tend to be more robust because you have a whole community of people fixing security flaws and other issues. Examples include the Linux operating system, Kubernetes, and TensorFlow. Kubernetes for cluster orchestration and TensorFlow for machine learning were both originally developed by Google engineers. Next, let's talk about how digital transformation helps with cost management. Now, by moving to the cloud, that is your digital transformation, you reduce your capital expenditure. You reduce upfront investments in hardware and software and convert these costs to operational expenses based on actual usage. The cloud also reduces the need for extensive IT maintenance and management, thus lowering ongoing operational costs and freeing up resources for other strategic initiatives. Companies would rather have people working on applications that help the customer and help promote sales rather than on maintaining IT infra. Cloud providers often have an incentive to build their data centers in an environment friendly and sustainable way. Since they are operating at scale, it also makes business sense for these cloud providers to build energy efficient data centers. So, as an organization, using the cloud can help you be more sustainable. Digital transformation can help enhance customer experience. That's because using the cloud, you can build personalization systems using advanced data analytics and machine learning to improve your product. In fact, cloud providers, including Google, provide a number of no code solutions for this. You can harness cutting edge no and low code technologies offered by these platforms to deliver more personalized products. Cloud infrastructure also enables faster delivery of bug fixes and features. With cloud infra, businesses can deploy applications and updates much more rapidly, ensuring they meet customer demands promptly and effectively. Cloud providers make it easy for you to set up continuous integration and continuous delivery pipelines so that a bug that you fix today can reach your customers tomorrow. Cloud providers also have a business to run, and they often tend to be the very best at what they do. Think Microsoft, Google, Amazon. They're the best in their fields. This means that they're constantly innovating the cloud products they offer, which means if you're using the cloud, you have access to the latest innovations in AI, ML, and big data analytics. Because you don't have to invest in expensive infra to quickly prototype and test something, the cloud supports a fail fast, learn fast approach, allowing businesses to experiment with new ideas and rapidly iterate based on feedback. If your organization is still stuck delivering software the old way, the slow way, you might find that your competitors come out with new products and features months ahead of you. And finally, the cloud makes adhering to security and compliance easy, yet another reason to adopt and move to the cloud. Cloud providers have to keep secure all of the organizations using their services. They typically invest very heavily in security and they offer measures like encryption, identity, and access management, and this often surpasses the capabilities of individual organizations. As compliance takes front and center stage, cloud providers often build their products and services keeping industry standards and regulations in mind, thus helping orgs using their cloud to meet compliance requirements more easily. For example, you may have data storage requirements and require that all your data be stored in, say, Europe, the US, or Asia. Services such as BigQuery and cloud storage on the Google Cloud allow you to clearly specify where you'd like your data to be located. And they ensure that this compliance is strictly adhered to. They offer a guarantee. Today, we are talking about digital transformation as it relates to the cloud. But digital transformation has existed for centuries, from horse drawn carriages to locomotives, from TV to the internet, from in person delivery models to online delivery models. In this video, we'll discuss four different categories of digital transformation, and for each category, we'll discuss the examples of some companies that successfully made this digital transformation, this innovation leap, and some other companies that failed to do so. four different digital transformation case studies from fairly recent history over the last 50 years or so. The first kind of digital transformation we'll discuss is the one from analog to digital music, which spanned the 90s and 2000s. We know that the music industry underwent a massive transformation with the advent of digital technologies. In the 90s, music was predominantly distributed through physical media like vinyl records, cassette tapes, and CDs. The introduction of MP3 and other digital music formats revolutionized how music was stored and distributed, and this shift enabled music to be easily copied and shared, disrupting traditional distribution channels. Platforms like Napster initially highlighted the potential and legal challenges of digital music sharing. This was followed by legitimate services like Apple's iTunes, where you could legitimately download and purchase individual tracks. The next leap was the rise of streaming services like Spotify and Apple Music, which provide on demand access to vast libraries of music without the need for physical or digital ownership. Next, we'll discuss the transformation from brick and mortar stores to e commerce, which spans the 90s to the present day. Commerce has shifted online beginning in the late 90s with companies like Amazon and eBay. Amazon started as an online bookstore but quickly expanded to becoming a global marketplace for virtually any product. Customers got access to vast product selections and competitive pricing. And the development of secure online payment systems like PayPal and advancements in cybersecurity were crucial in building consumer trust in e commerce platforms. Next, we'll discuss the shift to digital banking and fintech from the early 2000s to the present day. Traditional banking models, which relied heavily on physical branches and face to face interactions, have been disrupted by digital technologies that offer greater convenience, efficiency, and personalization. And finally, we'll discuss some examples of digital transformation related to the rise of cloud computing, starting from the late 2000s and ongoing till the present day. Cloud computing, we know, marked a significant transformation in how businesses manage their IT infrastructure. Companies like Amazon Web Services, Microsoft Azure, and the Google Cloud offer scalable on demand computing resources that allowed businesses to avoid large capex on physical infra. Taking this one step further, cloud based applications like Salesforce, Microsoft 365, and Google Workspace enable organizations to access powerful software solutions over the internet, reducing the need for complex on premise installations and maintenance. Let's discuss a few companies that fall in each category, starting with analog to digital music. We'll discuss some companies that succeeded and others that failed. A company that transitioned effectively and capitalized on digital music was Apple. With the introduction of the iPod and the iTunes Store, Apple revolutionized how music was purchased and consumed. iTunes allowed users to buy individual songs digitally, which was a major shift from purchasing entire albums on CDs. Another example of a company that succeeded in this era was Spotify. This pioneered the streaming model of music, offering users access to a vast library of music for a subscription fee. This model fundamentally changed how people listen to music, moving away from ownership to access. There were some companies that did not make this shift successfully. Tower Records was a major music retailer which failed to adapt to the digital revolution and the shift to online music sales and streaming. As a result, it filed for bankruptcy in 2004 and eventually closed all its stores. Another example is Blockbuster Music. This is similar to the parent company Blockbuster and its DVD rentals. Blockbuster Music did not transition effectively to digital formats and streaming services, leading to its decline alongside physical media rentals. Next, let's discuss the transition from brick and mortar stores to e commerce. This transition is still ongoing. A company that pioneered this transition was Amazon. Amazon started as an online bookstore and quickly diversified into a wide range of products, becoming a leading global e commerce platform. Amazon's investment in logistics, cloud computing, and personalized shopping experiences solidified its position. Another company that's successful in this new era, though it still owns a large number of brick and mortar stores, is Walmart. Although traditionally a brick and mortar retailer, Walmart has expanded into e commerce through acquisitions like Jet.com and significant investment in online shopping platform and infrastructure. For each success story, there are failure stories as well. Sears was once a retail giant. It struggled to adapt to the rise of e commerce, and its failure to innovate and compete effectively with online retailers like Amazon led to a steady decline and eventual bankruptcy. Toys R Us is another brick and mortar giant that failed to transition. This toy retailer did not invest adequately in its online presence, which, combined with financial struggles and competition from both online and big box retailers, led to its bankruptcy and closure of physical stores. What about the shift to digital banking and fintech? Which are some of the companies that succeeded? The first example here is JP Morgan Chase. This can be thought of as the most important bank in the US. JP Morgan Chase has heavily invested in digital transformation, launching initiatives like their mobile banking app, AI driven financial services, and blockchain technology. This has enhanced customer experience and operational efficiency. Another major player here is PayPal. It originally started as a digital payment platform. PayPal has expanded its services to include peer to peer payments, digital wallets, and online merchant services. Its early adoption of digital and mobile payment solutions positioned it at a leader in the fintech space. Wachovia is an example of a company that struggled with this transition. It struggled to keep up with the digital innovations in the banking sector. The bank's inability to effectively compete with emerging digital banking solutions contributed to its decline and eventual acquisition by Wells Fargo during the financial crisis. Another example of a company that failed to make the transition is Western Union. Although it's still operational, Western Union has faced challenges in adapting to the digital shift. Its reliance on traditional money transfer services has made it difficult to compete with faster, cheaper, and more convenient digital payment solutions like PayPal, Venmo, and other fintech startups. And finally, let's discuss some examples of digital transformations powered by the cloud. The most prominent example here is Netflix. Netflix was originally a DVD rental service. It transitioned to a streaming model leveraging cloud computing to deliver content globally. It also uses cloud services for data analytics and to manage its extensive content library. Another example here is Dropbox. It moved from providing basic file storage to offering comprehensive cloud based collaboration and productivity tools, relying heavily on cloud infrastructure for scalability and reliabilities. But what about the other side of the coin? Which companies did not make the shift? The most prominent example here is Blockbuster. Despite opportunities to innovate and adapt to streaming and digital distribution, Blockbuster remained focused on its physical rental model. This inability to pivot led to its downfall as competitors like Netflix grew. Another example here is BlackBerry. BlackBerry was one of the first quote unquote smartphones. It was known for its secure email services and hardware, but it was slow to transition to the cloud and mobile app ecosystem, which contributed to its decline in the smartphone market. In this video, we'll discuss the various deployment models available for your software solutions. Now, most of these deployment models relate to cloud computing. There's just one deployment model, the traditional on premises deployment model that does not use the cloud. Cloud deployment models refer to the various ways in which cloud services and infrastructure can be implemented, managed, and accessed. They define the location and management of the cloud infrastructure, as well as the distribution of responsibilities between the cloud provider and the user, the company that uses the cloud. In our cloud deployment model discussion, the first model here is on premises, which is not technically a cloud solution. On premises or on prem refers to IT infrastructure that is hosted or managed within an organization's own facilities. This model offers full control over the hardware and software, providing high levels of customization and security. Next, we have the private cloud. The private cloud can be thought of as one step up from on premises. This involves cloud infrastructure that is exclusively used by a single organization, either hosted internally or by a third party provider. It offers greater control and security tailored to meet specific needs and compliance requirements of the organization. The cloud that we've been discussing so far has generally referred to the public cloud, that refers to cloud services offered by third party providers over the public internet. AWS, Microsoft Azure, Google Cloud. The public cloud is available to anyone who wants to lease resources from the cloud. The model is cost effective and scalable and requires no maintenance from the user, as it's the provider that manages the infrastructure. The hybrid cloud is a combination of both public and private clouds, or public and on premise infrastructure. This configuration allows data and applications to be shared across the two deployment models. This model often offers greater flexibility, scalability, and optimization of existing infrastructure by leveraging the benefits of both deployment models. The downside is, of course, it's more complex. And finally, we have multi cloud. Multi cloud refers to the use of multiple cloud services from different providers, a combination of Azure and Google Cloud, or Google Cloud and AWS. That's an example of multi cloud. This allows organizations to meet various needs or avoid reliance on a single vendor. It mitigates vendor lock in. Again, in exchange for flexibility, reliability, and redundancy, this model is a little more complex. We've discussed on premise deployments in some detail. Let's quickly summarize. This is where the organization is responsible for hosting and managing its IT infrastructure within its own facilities. Organizations have full control over the hardware, software, and security, and all of this is the organization's responsibilities. Here are the pros and cons of on premises deployments. The upside is organizations have complete control over their IT environment, allowing for tailored configurations and optimizations. Another upside is that enhanced security measures can be implemented if the organization has stringent regulatory and compliance requirements. And the third is performance. Because the hardware will be close to end users, this can result in lower latency and potentially better performance for certain applications. You know the downsides already. Significant upfront investment is required to purchase and maintain hardware, software, and the physical facilities where they are housed. You also need to have local expertise, in house staff responsible for maintenance. All of the updates and troubleshooting demands tend to be significant. And finally, these have scalability limitations because scaling up requires purchasing additional hardware and infrastructure, which can be time consuming and expensive. A private cloud mitigates some of the challenges associated with on premise deployments. A private cloud is a computing environment dedicated exclusively to a single organization. In public clouds, resources are shared amongst multiple tenants. A private cloud offers isolated resources to ensure high levels of security, privacy, and control. Let's say you're the New York Stock Exchange and you have your hardware and infrastructure that's very specialized for your needs, and you don't want to run all of the IT infra in house. You could choose a private cloud. Private clouds give you some of the advantages of public clouds, such as scalability and automation, but within a more controlled and secure environment. These are typically used to comply with regulatory requirements. Now, where do private clouds run? Turns out there are some options here. Private clouds can be hosted within the organization's own data centers, leveraging existing infrastructure and resources. This is the setup that provides maximum control and customization. This setup might be slightly more scalable and flexible than traditional on premises deployment. Another option is to have organizations choose to host their private cloud in a third party provider's data center. This combines the benefits of private cloud isolation with the advantages of outsourcing infrastructure management. So, some of the overhead of managing one's own data center is eliminated here. And finally, there are organizations that offer managed private cloud facilities. This is a variation where a third party vendor manages the private cloud infrastructure on behalf of the organization, whether on premises or in the vendor's data center, providing expertise and reducing operational burdens. Let's discuss some advantages to using the private cloud. Because you have dedicated resources, this ensures that the data and applications are isolated, providing higher levels of security and privacy compared to public clouds. Because private clouds are only for your organization, they can be tailored to meet specific regulatory and compliance requirements with customizable security protocols and configurations. Organizations have full control over their cloud environment, including hardware, software, and network configurations, allowing for optimized performance and management. You have all of the advantages of on premises deployments plus the advantage of scalability. Private clouds offer scalability, although to typically a lesser extent than public clouds. But of course, there are drawbacks. Private clouds tend to be expensive because setting up and maintaining a private cloud involves significant capital expenditure and operational costs. Once again, you need in house expertise for maintenance. You can, of course, outsource to a third party private cloud provider, but that also tends to be expensive. Although private clouds offer scalability, they are generally more limited than public clouds, particularly in terms of elastic scaling during peak demands. There are sound reasons to choosing the private cloud. Organizations handling sensitive data, such as healthcare providers, financial institutions, and government agencies, may opt for private clouds to ensure data security and compliance with strict regulations. Businesses requiring specific configurations and tailored solutions also benefit from the extensive customization options available in private clouds. The stock exchanges I was talking about before, that's a very specialized use case, and private cloud makes sense there. Companies that need full control over their IT infrastructure, including security policies and system management, they may find that private clouds are more suitable than public or hybrid alternatives. Organizations with performance sensitive applications may prefer private clouds to optimize latency and throughput by utilizing dedicated resources. Industries with stringent regulatory requirements often choose private clouds to meet compliance standards. Healthcare organizations often choose private clouds to comply with regulations like the Health Insurance Portability and Accountability Act, HIPAA, in the United States. Companies that have to meet GDPR requirements, that is, General Data Protection Regulation, the Data Privacy and Protection Law enacted by the European Union, may also choose to use the private cloud. GDPR regulates how organizations collect, store, process, and share personal data of individuals within the EU. Next, let's discuss public clouds, the cloud computing model, where services and infrastructure are provided by third party providers over the public internet. These services are available to multiple customers on a shared basis, which means that resources are pooled and distributed among various tenants. Services are typically offered on a pay as you go basis, allowing organizations to only pay for the resources they consume. Where do public clouds run? Public cloud services are hosted in the data centers owned and operated by cloud service providers such as Amazon Web Services, Microsoft Azure, and Google Cloud. The data centers are located globally to provide widespread availability and low latency. Users access public cloud services over the internet using web based interfaces, APIs, or specialized software tools provided by the cloud provider. Public clouds tend to be cost effective because they operate on a pay as you go model, eliminating the need for significant upfront investments in hardware and software. Public clouds offer virtually unlimited scalability, allowing businesses quickly scale their resources up or down based on demand. Cloud providers handle all aspects of infrastructure management, including maintenance, updates, security, and compliance, and reduce the operational burden on organizations. Public clouds have data centers all around the world, allowing you to deploy applications and services close to your users, reducing latency and improving performance. Some of the downsides of the public cloud are around security and privacy concerns. Even though they implement robust security measures, because the infrastructure is shared, there can be concerns about data privacy and vulnerabilities. Organizations with stringent regulatory and compliance requirements may face challenges in ensuring that public cloud environments meet all necessary standards. Public cloud users have less control over the underlying infrastructure compared to private clouds. Customization options may be limited, and businesses must rely on cloud providers' configurations and policies. The most important downside, in my opinion, is the potential for vendor lock in. Relying heavily on a single public cloud provider can lead to vendor lock in, which means that if you're not satisfied with the provider's performance or their security, it might be very, very difficult to switch or integrate with other platforms. Organizations choose the public cloud for cost savings. The pay as you go model eliminates the need for significant capital expenditure. Organizations may also choose the public cloud for scalability. Businesses with fluctuating or unpredictable workloads benefit from the public cloud's ability to scale resources dynamically. Organizations that need to quickly deploy applications and services can leverage the public cloud's rapid provisioning capabilities, delivering features to customers quickly. Organizations also choose the public cloud in order to focus on their core business and offload infrastructure management to the cloud provider. Companies that have global operations can use the public cloud's distributed data centers to ensure consistent performance and low latency for users around the world. We've already discussed the cloud deployment models: on premises infrastructure, private cloud, and public cloud. Let's now discuss the hybrid cloud. A hybrid cloud combines the elements of multiple cloud deployment models. You can choose to combine the public cloud and a private cloud, or you can choose to combine a public cloud with traditional infrastructure, that is your on premises deployments, or you can combine a private cloud with traditional infrastructure. The hybrid cloud allows data and applications to be shared between the different cloud providers. This model leverages the benefits of both deployment types that you've chosen, providing greater flexibility and optimization of existing infrastructure. The most common practice is to combine the public cloud with traditional on premises deployments. Organizations can maintain sensitive data and critical workloads on the private cloud or on premises while using the public cloud for less sensitive operations and scaling as needed. Rather than differentiating between private cloud and traditional infrastructure in the rest of this video, I'll just refer to private clouds. That also includes on premises deployments. So let's talk about where hybrid clouds run. The private cloud component can run on the organization's own data centers, utilizing existing infrastructure and resources for critical and sensitive workloads. The public cloud component can run on cloud providers such as Google, Microsoft, or Amazon. The private cloud infrastructure can also be managed by third party providers, but still dedicated exclusively to one organization. This can also be part of a hybrid cloud setup. So, there are different ways to set up hybrid clouds, but the idea is that you integrate on premises and public cloud environments to get the best of both worlds. So, what are some advantages of the hybrid cloud? Hybrid clouds provide the flexibility to move workloads between private and public clouds based on changing needs and priorities. For example, if you're an e commerce site, you may serve some of your resources, some of your web pages from your private cloud or on premises infrastructure. During times of peak demand, you might scale to use additional resources on the cloud. Organizations can use the public cloud for high volume, non sensitive workloads and burst capacity during peak times, reducing the need for significant investments in private infrastructure. Hybrid clouds enhance disaster recovery and business continuity by replicating data and applications across both private and public environments, ensuring resilience against outages. Let's say your infrastructure is shared across private and public clouds. Let's say the public cloud suffers an outage for some reason. You'll simply serve requests from your private infrastructure and vice versa. Another advantage is that sensitive data and critical applications can remain on the private cloud to meet compliance and security requirements. Such as for a healthcare provider, you might want patient information to remain on the private cloud, but other general information can be on the public cloud. Another advantage, which I haven't explicitly mentioned here, I've just made the assumption, but that's the most important advantage of all, and that hybrid clouds mitigate vendor lock in. Let's say you're not happy with your public cloud provider for some reason, you're not happy with Azure, Google, or AWS, you're not stuck with them. You already have your private infrastructure. You can simply move your resources to your private infrastructure, ensure business continuity while you figure out your options. There are trade offs to every cloud deployment model. Here are some of the cons of using the hybrid cloud. The first is complexity. Managing a hybrid cloud environment can be complex. This requires robust integration, orchestration, and management tools to ensure seamless operation between private and public clouds. When you have two different environments with different configurations, your security risks go out. Ensuring security across both environments can be challenging, particularly when data and applications move between private and public clouds. Hybrid clouds tend to be cost effective, but this is something that has to be managed carefully. They can lead to unexpected expenses if not properly managed. If you're constantly moving data between your private and public clouds, you can incur significant network transfer charges. Ensuring that applications and data can move seamlessly between environments requires careful planning and compatibility considerations, which can complicate deployment and management. When would organizations choose the hybrid cloud deployment model? Companies looking for a balanced approach to leverage both the control and security of private clouds and the scalability and cost efficiency of public clouds might choose hybrid clouds. Companies with stringent regulatory requirements can keep sensitive data on private clouds while using public clouds for less sensitive operations. Hybrid clouds enhance disaster recovery and business continuity plans by leveraging the redundancy and geographical distribution of public cloud resources, ensuring that your applications have minimal downtime and data loss. And the last cloud deployment model that we'll discuss today is multi cloud. This approach involves using multiple cloud services from different cloud providers to meet various organizational needs. A multi cloud strategy specifically leverages multiple public cloud providers. On premises infrastructure or private clouds do not enter the picture here. The biggest advantage of multi cloud is that it reduces a company's reliance on a single vendor and allows organizations to optimize their cloud environment by selecting the best services from each provider. If you're going with a multi cloud strategy, you may choose, say, Azure and Google, or AWS and Google, or some other combination. Where does multi cloud run? Multi cloud environments typically run across various public cloud platforms such as AWS, Google Cloud, Azure, IBM Cloud, Oracle Cloud, and others. In order to be able to spread your resources across multiple clouds, these environments can be interconnected through secure network connections, APIs, and integration tools that allow seamless data and application management across different cloud services. You can also set up a more complex hybrid integration. Your deployment model can include multiple public clouds, but also include, say, private clouds and on premises infrastructure if you need that redundancy and flexibility. The first and most important advantage of the multi cloud deployment model is vendor independence. By using multiple cloud providers, organizations avoid vendor lock in and gain greater negotiating power, flexibility, and choice. Let's say you offer a product that's running on Amazon, and tomorrow you find that Amazon is your competitor. If you choose a multi cloud strategy, you're not that impacted. However, if you were reliant only on Amazon, well, the fact that Amazon is your competitor is now going to be a serious problem. This is why big organizations prefer multi cloud as opposed to being tied into a single cloud vendor. Another advantage of multi cloud is that you can pick and choose services across cloud platforms. Different cloud platforms are good at different things, they have specialized strengths. For example, Google Cloud is especially good at artificial intelligence and machine learning, and you might choose those services from the Google Cloud, but for other services, you might choose other providers. Multi cloud environments also enhance reliability and uptime. Your workloads are typically distributed across multiple cloud platforms along with your data. If there is an outage in a specific cloud provider, well, your services are less likely to be impacted. Organizations can often optimize costs by choosing the most cost effective services for specific workloads and leveraging competitive pricing amongst providers. Typically, when you set up a multi cloud infrastructure, Each cloud provider is aware that you're working with other cloud providers, and this will cause them to offer more competitive pricing. Here are some of the downsides of multi cloud operations. The first is, of course, complexity. Managing multiple cloud environments requires sophisticated integration, orchestration, and monitoring tools to ensure seamless operation and governance. Rather than just worrying about security and compliance in one cloud, you now have to worry about multiple clouds and understand how security policies work across these cloud environments. That's another challenge. This requires additional management overhead because you need to manage relationships, contracts, and billing with multiple providers. This can significantly increase your administrative and operational overhead. And finally, you might face interoperability challenges. You have to ensure that all of your products and applications work across different cloud services and platforms. This definitely requires additional technical effort. The first and most important reason to choose multi cloud is to mitigate the risk of dependency on a single cloud provider to mitigate vendor lock in. This gives you greater flexibility and negotiating power. Businesses might go the multi cloud way to choose the best services and technologies from each provider. By distributing applications and data across multiple cloud providers, organizations can enhance their resilience and reduce the risk of downtime due to provider specific issues. Multi cloud strategies can help meet diverse regulatory requirements by enabling data residency and sovereignty options across different regions and providers. And finally, leveraging multiple cloud platforms allows companies to scale resources dynamically and ensure optimal performance by selecting the best fit service for each application or workload. In this video, we'll discuss cloud service models, which define how cloud computing resources are delivered and consumed by users. These models categorize cloud services into three distinct types: infrastructure as a service, platform as a service, and software as a service. Each of these offer different levels of control, flexibility, and management, and they provide a framework for organizations to choose the appropriate type of cloud service based on their specific needs and goals. Let's look at the three cloud service models. The first is infrastructure as a service, abbreviated to IaaS. This provides virtualized computing resources over the internet, including virtual machines, storage, and networking. The idea behind infra as a service is that the user can provision and use these virtual machines in order to deploy and scale their applications. There is a certain amount of management and operational overhead that the user has to bear when working with IaaS solutions. Next, we have platform as a service. This delivers hardware and software tools over the internet, primarily for application development. It provides a platform that includes infrastructure, operating systems, and development frameworks, allowing developers to build, test, and deploy applications quickly and efficiently. Platform as a service solutions abstract away from the user the nitty gritty of managing and provisioning infrastructure. PaaS offerings typically take care of additional details such as scaling, traffic management, load balancing, and versioning. Working with PaaS solutions reduces the operational overhead on you, the user, and more of this operational overhead is borne by the cloud service provider, that is Google. And finally, you have software as a service. SaaS offers software applications over the internet on a subscription basis. Users can access these applications via web browsers without the need for installation or maintenance, making it convenient for delivering and using software services. With software as a service, you're not actually building your products using infrastructure, you're just using the product offering directly. So, infrastructure management, scaling, versioning, none of these are your problem. You just have to make sure that the software suits your purposes. It's actually very useful to visualize these cloud service models as a pyramid. Observe that infra as a service is at the very bottom, then we have platform as a service, and then software as a service at the very top. This pyramid illustrates the levels of abstraction and management provided by each model. Let's understand these in more detail, starting with infra as a service at the very bottom of the pyramid. This offers the most basic and fundamental cloud services: virtual machines, storage, and networking. This is the most hands on that you can be on the cloud. Organizations using IaaS solutions have the most control over their IT environment, but also bear the responsibility for managing the operating systems, middleware, and runtime environments. With Infra as a Service, it's your responsibility to provision and configure the virtual machines, add additional machines if your demand spikes, manage the versioning of the software installed on those machines. All of these are your responsibility. With Infra as a Service, you're not really abstracted away of the nitty gritty of working with servers and storage. Higher up in the pyramid, we have Platform as a Service, which provides a higher level of abstraction. PaaS includes not only infrastructure but also development tools, databases, and middleware, allowing developers to focus on building and deploying applications without worrying about the underlying hardware and software maintenance. With PaaS solutions, your focus is on writing the code for your application, managing and provisioning the infrastructure, traffic management, load balancing, versioning. All of that is taken care of by the cloud provider. Here you are abstracted away from more of the nitty gritty, but you lose some control over the underlying infrastructure. So, PaaS offerings generally tend to be less customizable. And then finally, at the very top of the pyramid, you have software as a service. This offers fully managed software applications delivered over the internet. Users can access these applications through web browsers or APIs without needing to manage the underlying infrastructure or platforms. SaaS provides the highest level of abstractions. You're using ready to use software, you're not responsible for building the software. Now that you have an understanding of each of these offerings, let's dig into each in a little more detail, starting with infrastructure as a service. Let's start by discussing the characteristics of infra as a service offerings. IaaS provides virtualized computing resources over the internet. This could be virtual machines, storage, and networking. These offerings tend to be very scalable. You can provision additional resources based on your needs. You can turn down resources if you feel you no longer need them. They offer flexibility for fluctuating workloads. However, it's your responsibility to configure the scaling up and down of solutions. This can be manual or automated, but the configuration is up to you. Infra as a service offers on demand service, which means that resources can be provisioned and deprovisioned as needed, often through a web based interface or an API. You actually have a fair level of control over how and where your applications run. Let's say you set up 3 virtual machines in a cluster and you need more resources, you can increase the number to 5 or 7 or reduce it down to 3 or 2. This follows pay as you go model. Users only pay for the resources that they provision and use, typically on an hourly or monthly basis. While the infrastructure is managed by the provider, users have control over the operating system, the applications that you install, and any configurations that you set up. If you require a certain level of customization and control over how your application runs, infra as a service is what you'll choose. IaaS is also highly flexible. As a user, you can create and manage virtual machines, networks, and storage, and these tend to be suitable for a wide range of use cases, including running legacy applications, custom applications, and complex workloads. Infra as a service offerings are scalable, you have fine grained control over resource allocation, and you can scale up and down as needed. And here is an important benefit for infra as a service legacy application support. These solutions tend to be ideal for running legacy applications that cannot be easily adapted to other kinds of cloud services, such as platform as a service or software as a service environments. Let's say you have an application running on premises and you want to lift and shift it to the cloud. Infra as a service will offer you the easiest migration path. You'll likely be able to port your applications without extensive rewrites. Infra as a service gives you more control over security measures and compliance configurations, and users can generally implement their own security policies and encryption. And finally, Infra as a service enables rapid experimentation and innovation by providing a flexible and configurable environment. What are the downsides of infra as a service? It requires more management and maintenance from you. You are responsible for managing the operating system, middleware, runtime, and applications. This might include patching, updating, and monitoring the infrastructure. If you're looking for fast prototyping, this may not be the best choice. Infra as a service generally tends to have a lower development speed compared to platform as a service because developers need to set up and configure the environment before they can code. And finally, these solutions tend to have a higher operational overhead due to the need for continuous management of the virtual machines, storage, and network configurations. Let's discuss some Google services that fall in the infra as a service category. The first, of course, is Google Compute Engine, which provides scalable high performance virtual machines. Google Cloud Storage, that offers scalable object storage for storing and retrieving large amounts of structured data, usually used for binary files such as media files, images, videos, and so on. Google Virtual Private Cloud is what allows users to create and manage virtual networks and configure subnets, IP addresses, and firewall rules. And then, of course, we have Google Cloud Load Balancing, which distributes incoming traffic across multiple instances, ensuring high availability and reliability of applications. Next, let's understand the characteristics of platform as a service offerings. PaaS provides a platform with built in software development frameworks, allowing developers to build, test, deploy, and manage applications without worrying about the underlying infrastructure. The idea is you should get to coding directly without worrying about provisioning or managing anything. PaaS also offers middleware services and runtime environments which handle the execution of applications. This includes support for various programming languages and libraries. The underlying infrastructure, the storage, the servers, the networking, the scaling, the traffic management, all of that is handled by the cloud service provider. Developers do not need to worry about hardware maintenance or scaling the infrastructure. PaaS platforms can automatically scale applications up or down based on demand, ensuring optimal performance and resource utilization. You don't have to manage the scaling yourself. PaaS platforms often include managed database services, offering relational and non relational database options with built in scaling and high availability. And finally, they provide built in security features, including identity and access management, data encryption, and compliance. As you might imagine, platform as a service solutions offer several advantages over infra as a service solutions. PaaS abstracts away much of the underlying infrastructure, which means that users can focus on code and application development rather than focusing on infrastructure management. PaaS solutions often come with integrated development tools, version control systems, collaboration features, and managed databases, which streamline the development workflow. Infra as a service requires users to set up and manage these tools independently. PaaS platforms often include automatic scaling and load balancing as a part of their managed services. Infra as a service definitely allows for scaling, but it requires more manual configuration and management. PaaS solutions can be more cost efficient because it eliminates the need for managing infrastructure and reduces operational overhead. Infra as a service also offers a pay as you go model. PaaS further reduces costs associated with infrastructure management and maintenance. Developers using PaaS solutions can focus on application logic and functionality rather than dealing with the complexities of infrastructure management. PaaS solutions accelerate the development process by providing pre configured environments, integrated tools, and managed services. Let's look at the other side of the coin here. Here are some of the disadvantages of platform as a service offerings. The first is limited control and customization. PaaS provides less control over the underlying infrastructure. You can't manage the operating system, network configurations, or hardware, which can be limiting for certain applications. The most important downside, though, in my opinion, is vendor lock in. PaaS often involves using proprietary tools, services, and APIs provided by the platform, which can make it difficult, if not impossible, to migrate applications to another PaaS provider or back to an on premises environment. Infra as a service offers more flexibility in choosing tools and configurations, making it more portable and making it easier for you to switch providers. PaaS environments are shared among multiple tenants. So your application may be running alongside an application from another organization and you wouldn't even know. This can lead to performance issues due to noisy neighbors. This is less of a problem with infra as a service where you provision and manage resources. With PaaS, as a user, you have to rely on the provider's security measures and compliance certifications, and this can be a concern for applications with stringent security or compliance requirements. Again, less of a problem with infra as a service that allows users to implement their own security measures and compliance protocols. Platform as a service offerings typically offer specific programming languages, frameworks, and tools, and you're limited to using those runtimes. This can be restrictive for developers who need to use languages or frameworks which are not supported by the platform. Let's look at some of Google's platform as a service offerings. The first is App Engine, which is a fully managed serverless platform that allows developers to build and deploy scalable web and mobile applications. Serverless because you don't manage the infrastructure, Google does. App Engine supports multiple programming languages including Java, Python, Node.js, and Go. It takes care of infrastructure provisioning, traffic splitting, scaling, versioning of your apps, and everything. You just focus on code. Google Cloud Functions is an event driven serverless compute platform. It's an execution environment for building and connecting cloud services. Developers write and deploy code that responds to events from Google Cloud Services and other external services. All you have to do is write code for the function and deploy it. The rest is taken care of by Google. And then we have Google Cloud Run, which is a managed platform that automatically scales stateless containers. Cloud Run allows developers to run containerized applications in a fully managed environment without the need for managing the underlying infrastructure. It supports any programming language and uses standard container technologies such as Docker. Another example is Google BigQuery, which is a fully managed data warehouse that enables fast SQL queries using the processing power of Google's infra. BigQuery is designed for analyzing large data sets and provides built in machine learning capabilities. Next, let's discuss the characteristics of software as a service offerings. SaaS offerings are full fledged solutions that you consume as is. SaaS delivers software applications over the internet, eliminating the need for users to install, manage, or update software on their own device. For example, if you signed up for Google Workspace to use Gmail, that's an example of a SaaS offering. SaaS offerings tend to be subscription based. It's typically offered with pricing models that can include per user, per month, or usage based billing. These solutions are usually accessible from any device with an internet connection, providing flexibility for remote work and collaboration. SaaS solutions are completely managed by the provider. This includes infrastructure, security, maintenance, and updates. As a user, you don't have to worry about any of this. SaaS offerings are highly scalable. The companies that offer these services ensure that this is indeed the case. Applications can easily scale to accommodate growing numbers of users or increased usage. Since these are delivered over the internet, any updates to the software are applied to all users automatically. Users have access to the latest features and security improvements without needing to manage the updates themselves. You would choose SaaS offerings when you want a standard solution that's already available prepackaged. SaaS provides ready to use software applications designed to meet common business needs. These applications come with predefined functionalities and workflows that can be used right out of the box. SaaS providers handle all aspects of software maintenance, including updates, patches, and security fixes. You have no application maintenance burden. If you have a software solution that fits your needs and it's available as a SaaS offering and you don't want to worry about maintaining that application, just go for it. With SaaS solutions, IT teams are freed from routine maintenance and management tasks, which means the teams can focus on developing new applications and improving existing systems rather than on maintenance. SaaS solutions are also the right choice when you have the need to access your applications from anywhere on any device. This is useful if your organization has remote workers, multiple office locations, or employees who travel frequently. So, what are some of the SaaS products that Google has to offer? Well, the first one is Google Workspace. This is Google's business collaboration suite that includes Gmail, Google Drive, Google's Docs, Sheets and Slides, Google Meet, and Google Calendar. Another Google SaaS solution is Google Analytics, a web analytics service that tracks and reports website traffic. This provides insights into user behavior and it helps businesses make data driven decisions to improve their online presence. Another incredibly useful SaaS offering is Google Ads, an online advertising platform that allows businesses to create and manage pay per click advertising campaigns. One last SaaS offering here is Google Cloud Identity, a unified identity access app and endpoint management platform. It helps manage users, devices, and applications from a single console. Let me summarize how you would choose between these service models. Opt for infra as a service if you need full control over your virtual computing environment. Choose platform as a service if you want to focus on application development without managing the underlying infrastructure. And select software as a service if you prefer ready to use software that requires minimal setup and management. And before we close out this video, here is the cloud service model pyramid. You can see the infra as a service, platform as a service, and software as a service offerings from Google. On the left, you have the Google services. On the right, you have the target audience for each of these offerings. Infra as a service is primarily preferred by IT engineers. Software developers who just want to focus on coding and not on infra management prefer platform as a service offerings, and end users who prefer ready to use software will opt for software as a service offering. This brings us to the very end of this course on digital transformation with the cloud. We started this course off by introducing the Cloud Digital Leader certification, providing an overview of what the certification entails. We covered the Cloud Digital Leader exam details, including the format, the types of questions to expect, and the key topics that are assessed. This foundation gave us a clear understanding of the certification's requirements and the skills that we need to develop to successfully achieve it. Next, we learned about the fundamentals of cloud computing, focusing on its definition and core principles. We explored the benefits of cloud computing, such as scalability, cost efficiency, and flexibility. We also discussed in detail the concept of digital transformation, examining how cloud computing drives innovation and business growth. To reinforce our understanding, we studied various digital transformation case studies which illustrated real world applications and the tangible benefits organizations have experienced. Finally, we explored different cloud deployment models, starting with private and public clouds, and then moving on to hybrid and multi cloud environments. We also covered the various cloud service models, including infrastructure as a service IaaS, platform as a service PaaS, and software as a service SaaS. These lessons provided us with a comprehensive understanding of how different cloud solutions can be deployed and managed to meet diverse needs. In conclusion, we've built a solid foundation in cloud computing by understanding the Cloud Digital Leader certification, learning the benefits and implications of cloud technology, and exploring various deployment and service models. This knowledge equips us with the essential skills to navigate the cloud landscape and leverage its potential to drive digital transformation within organizations. We are ready to move on to the next course in this journey, introducing Google Cloud Concept. Hi, my name is Janini Ravi, and welcome to this course on introducing Google Cloud Concepts. Google Cloud empowers users with a comprehensive suite of services, providing the tools necessary to innovate and optimize operations. By understanding the shared responsibility model, total cost of ownership, and Google Cloud's infrastructure, users can effectively navigate and utilize its ecosystem to enhance business agility and efficiency. In this course, you'll learn about Google Cloud and its various services, including compute, storage, networking, AI, and big data. This will provide you with an overview of the vast capabilities and functionalities available within Google Cloud. Next, you'll explore the shared responsibility model on the cloud, understanding the division of responsibilities between cloud providers and customers. You will also examine the total cost of ownership, gain insights into Google Cloud's global infrastructure, and learn about the Google Cloud Adoption Framework. Finally, you'll dive into fundamental Google Cloud concepts and the resource hierarchy within the platform. You will create a project on the Google Cloud, access various products and services, and become familiar with Cloud Shell and the Cloud Shell editor. These hands on activities will enhance your understanding of how to navigate and utilize Google Cloud's tools and services efficiently. At this point, you have a good understanding of basic cloud concepts. So you're ready to learn about the Google Cloud, specific technologies and services that are available on the Google Cloud for different use cases. This video is an introduction to the Google Cloud where I'll briefly explain some of the most popular products and services. Every cloud platform has its own naming convention for virtual machines, for clusters, for storage services, for networking, and so on and so forth. This particular video is an introduction to Google Cloud Services so that you get familiar with the product and service names and what those products are meant for. Let's start off with an introduction to the Google Cloud. Now, the Google Cloud Platform is often abbreviated as GCP. It's a suite of cloud computing services offered by Google that runs on the same infrastructure that Google uses internally for its end user products. Products such as Google Search, Gmail, file storage, YouTube, all of these use the infrastructure provided by the GCP. The Google Cloud offers resources such as virtual machines, cloud storage, and APIs for developers to build, test, and deploy applications. The idea is, and this is true for all public clouds, Google manages your infrastructure for you so you can focus on your applications. Google offers several products meant for businesses. For example, Google Workspace, which was formerly known as G Suite, is a collection of cloud based productivity and collaboration tools developed by Google. All of the business collaboration products offered by Google, such as Gmail, Google Drive, that allows you to store and access files from any device, Google Docs, Sheets, and Slides, an alternative to Microsoft Office, Google Calendar, Google Meet, all of these offerings are part of Google Workspace. Google Workspace is a separate offering from the Google Cloud. These are all software as a service offerings. This is where you directly use the software solution that Google has developed. We'll discuss software as a service in more detail later. But for now, let's discuss some different categories of Google Cloud services. Google Cloud offers a wide range of services designed to meet the diverse needs of businesses, ranging from cloud computing and storage to machine learning and data analytics. I'm going to discuss a few categories of services here first. Google Cloud offers a variety of different services for compute, that is, to deploy and run your cloud solutions. Google Cloud has services for storage and databases, where your data will live. There are also services for big data and analytics, which you can use to extract insights from your data. Google is especially popular for its machine learning and artificial intelligence services. Google offers robust networking capabilities. This involves firewalls and routes to secure your applications. And Google offers robust identity and security services. I've just picked some of the important and broad categories of services that Google has to offer. This is not a comprehensive list. Google has a large number of services for different use cases, and really, if you were to just hear all of the names, there's no way that you could remember all of them and what they're meant for. We'll discuss the important services here. Let's start with compute. Google Compute Engine is often abbreviated to GCE. This provides scalable virtual machines, VMs, that users can customize based on their needs. With virtual machines, you're running on virtualized hardware. That is, you do not get access to the underlying hardware directly. There is a layer of virtualization on top of which your operating system runs. Google App Engine is a platform as a service product that lets developers build scalable web applications and mobile backends without having to manage the underlying infrastructure. We'll discuss platform as a service in more detail in just a bit, but the basic idea is in platform as a service offerings, Google is responsible for the underlying provisioning of the infrastructure, scaling, versioning, traffic management, typically taken care of by Google. Google Kubernetes Engine is a managed environment for deploying, managing, and scaling containerized applications using Google's infrastructure. Containerization is a way to deploy modern applications. And Kubernetes is a container cluster orchestration technology originally developed by Google that is now open source. GKE, that is Google's offering of Kubernetes, allows you to run and scale your applications on a cluster of machines. Google Cloud Functions is a serverless execution environment for building and connecting cloud services with code. Now, serverless does not mean there is no server. Serverless just means that you as a user are not responsible for provisioning the server. Instead, the server provisioning and infrastructure management is handled by Google. Cloud functions are just functions that you deploy on the Google Cloud that react to external events. For example, you might upload a file to cloud storage and that might trigger a function and cause it to execute. Next, let's discuss some storage services and databases that Google Cloud has to offer. Google Cloud Storage offers durable and highly available object storage for unstructured data. Object storage is typically used to store blobs of unstructured binary data, images, media, videos, audios, etc. Google Persistent Disk provides block storage for compute engine virtual machines. When you create a virtual machine, you have to have some kind of hard disk associated with the virtual machine. That's the Google Persistent Disk. Google Cloud SQL is a fully managed relational database service for MySQL, PostgreSQL, and SQL Server. If you wish to run any of these technologies on the Google Cloud, Cloud SQL is what you'll choose. Google Cloud Bigtable is a NoSQL big data database service. It's NoSQL because you do not use SQL or structured query language to query its contents. Bigtable is meant for very large sparse datasets and it offers extremely low latency and high throughput. Cloud Firestore is a NoSQL document database for building web, mobile, and server applications. A document database typically stores data as entities such as JSON objects. And Google Cloud Spanner is a globally distributed database service that scales horizontally and combines the benefits of relational database structures with non relational horizontal scale. Next, we'll discuss some popular services which are part of big data and analytics, starting with Google Cloud BigQuery. This is one of Google's most popular products. It's a fast, highly scalable, and cost effective data warehouse for analytics over very large data volumes. Google Cloud Dataflow is a managed service that is used for processing data, both batch data stored in files or databases, or streaming real time data. Google Cloud Dataproc is a managed Apache Spark and Hadoop service that simplifies processing large datasets. And finally, Google PubSub provides real time messaging services that allow applications to exchange messages reliably, quickly, and asynchronously. Let's discuss some machine learning and artificial intelligence products and services. Here, I'm going to do a blanket mention of Vertex AI, which used to be previously called Google AI Platform. This is a unified umbrella platform that provides various tools and services to assist developers in building and deploying machine learning models. One of the most popular offerings within Vertex AI is Google AutoML, which allows users with limited machine learning expertise to train high quality models specific to their business needs. And here I'd like to mention TensorFlow. TensorFlow is not a product or a service. Instead, it's an open source software library for training deep learning neural network models. TensorFlow is an integral part of Google Cloud's ML offerings and is deeply integrated into its infrastructure and machine learning workflows. Let's discuss a couple of offerings under the networking category. Google offers VPCs or private networks with IP allocation, routing, and network firewall policies to manage a virtual network within the Google Cloud. Google also offers Cloud CDN, Content Delivery Network. This uses Google's globally distributed edge points to catch HTTPS load balanced content close to users. And finally, let's discuss some of Google's offerings for identity and security. Google IAM, or Identity and Access Management, manages access control by defining who has what access to which resources. Google Cloud Security Command Center provides risk and threat identification to protect your GCP resources. When you're working on the Google Cloud, you'll bring together a number of different products and services to build your software solution. Here you can see an example web application that has been deployed on Compute Engine, a virtual machine. The web application accesses data from Google Cloud Storage and Cloud SQL. In a typical case, you deploy your web application using Cloud Deployment Manager. This makes it easy for you to provision your infrastructure using templates. Maybe your web application includes Dialogflow, Google's conversational AI service. Your virtual machine, your databases, your storage all live within a Google VPC, Google's virtual network. And it's quite possible that when you're serving resources to your users, you cache your content on Cloud CDN. Now, I realize that this video covered a lot of information in a very short time. What I was trying to do is introduce you to the variety of services that Google has to offer. There is no reason for you to remember all of these services and what they're used for right away. All of the services that we've discussed here in this video, we'll be covering in more detail in the rest of this journey. Before we move on to the next video, let me just discuss what Google Cloud Identity is all about. This is a unified identity management solution provided by Google that offers identity and access management services for Google Cloud Platform and other Google services. It extends these capabilities to applications and resources from other providers as well. Cloud Identity is designed to help organizations maintain security and compliance while managing users and resources efficiently. When we talk about organizations using cloud providers, you may have heard the term shared responsibility model. In this video, we'll discuss what the shared responsibility model is and what it means for the organization and for the cloud provider. The shared responsibility model in cloud computing delineates the division of security and compliance responsibilities between the cloud service provider and the customer. This model helps clarify what aspects of security are managed by the cloud provider and which are the customer's responsibility. This ensures both parties understand their roles in maintaining a secure cloud environment. The shared responsibility model recognizes two components of security. The cloud provider is responsible for security of the cloud. This refers to the measures and controls implemented by cloud service providers to protect the infrastructure, the networks, and the foundational services that power the cloud. Security of the cloud includes the physical security of data centers, network protections like firewalls, and distributed denial of service mitigation, and maintaining the hardware and hypervisors that host virtual machines and services. The second component in the shared responsibility model is security in the cloud, and it's the customer who is responsible for this. Security in the cloud pertains to the responsibilities of cloud customers in safeguarding their own data, applications, and configuration within the cloud environment. It's the customer's responsibility to implement robust identity and access management, encrypt data, secure applications, and ensure proper configurations to mitigate risks. With this big picture understanding, let's dive into security of the cloud. This is something the cloud provider is responsible for. Security of the cloud includes the security for the underlying infrastructure, hardware, and the managed services that they offer. The specific responsibilities can vary based on the type of cloud service, whether it's infra as a service, platform as a service, or software as a service. Now, this has various components. Infrastructure security refers to the physical security of data centers, access control, surveillance, and environmental safeguards. This also refers to network security, firewalls, and distributed denial of service protection. Operational security involves managing and patching the underlying hardware and software infrastructure, ensuring the availability and reliability of the cloud services, and ensuring data redundancy and disaster recovery mechanisms. The cloud provider is also responsible for compliance and certifications, adhering to regulatory requirements and obtaining necessary certifications such as GDPR compliance, This is a regulation enforced by the European Union that mandates strict data protection and privacy requirements for organizations handling personal data of EU residents. The customer is responsible for security in the cloud. This includes managing their data, access controls, and configurations of the services they use. The customer is responsible for the security of their data. They need to ensure that they encrypt the data at rest and in transit. They are also responsible for ensuring proper data backup and recovery plans. It's the customer's responsibility to implement strong authentication and authorization mechanisms using identity and access management. It's only the customer who knows what resources should be available to which users. The customer needs to manage user identities and roles and ensure that access is given based on the principle of least privilege. Every user needs to have the minimal number of permissions that they need to perform their job well. The customer is also responsible for application security, securing the applications and services they deploy on the cloud. They are also responsible for regularly updating and patching their applications to protect against vulnerabilities. If the software that you deploy has a security vulnerability, that's your responsibility and not the cloud providers. And finally, the customer is responsible for configuration management and properly configuring security settings of the cloud services they use. Monitoring and auditing the configurations for compliance and security purposes also falls under the customer's responsibility. The specific responsibilities shared between the cloud provider and the customer can vary based on the cloud service model that you opt for. The responsibility of the customer and the cloud service provider is different for on premises setups, for infra as a service solutions, platform as a service solutions, and software as a service solutions. Google has a very nice graphic showing you how these responsibilities are shared between the cloud service provider and the customer across these different service models. The rows in this view represent various aspects of security and management tasks that need to be handled in different computing environments. I'll explain just a few of these. For example, the content on top refers to the actual data and applications created and managed by the customer. Hardware at the very bottom refers to the physical hardware infrastructure that supports the computing environment. Somewhere in between, we have audit logging that refers to the logs of system activities for monitoring, compliance, and troubleshooting. And then we have operations somewhere near the top, which refers to the daily management and operations of the IT environment. Now, if you were working on a traditional on premises setup where the organization is responsible for everything, all of these different aspects of security and management have to be handled by the customer. Everything is the customer's responsibility. There is no concept of shared responsibility because on prem setups are completely handled by the organization. Now, if you're working on a public cloud and you choose an infra as a service solution, then here is how the shared responsibility is split. It's Google's responsibility to take care of hardware, boot, hardened kernel, storage and encryption, network, and audit logging. All of the tasks above that are the customer's responsibility. That is your responsibility. You are responsible for the guest OS, data and content, network security, identity, web application security, deployment, access policy, content, amongst others. If you were to opt for a platform as a service offering, the cloud provider takes on more tasks and more management in the shared responsibility model. You can see that Google's responsibility has vastly increased here. It takes care of identity, operations, access and authentication, and network security. The customer is responsible only for application code and data, web application security, usage, deployment, access policy, and content. If you're opting for a software as a service solution, well, your responsibility is really minimal. As a customer, you're only responsible for content and access policy. Everything else is taken care of by the cloud provider. And here that's Google. Let's summarize the responsibilities of the cloud provider versus the customer for infra as a service. In bare metal offerings, where the underlying hardware is provided to the user, The cloud provider is responsible for the physical machine, network security, and data redundancy. The customer uses the hardware and installs the operating system and software that the customer plans to use. The customer is responsible for OS and application security and data security. In virtual machine offerings, the cloud provider is responsible for virtual infrastructure, the virtual machine images, and the hypervisor, that is the virtualization layer. The customer is responsible for configuring the virtual machine instance, the application, and the data. For containerized offerings, where containers are isolated packages that run your applications, the cloud provider is responsible for the cluster itself, the Kubernetes control plane, and the orchestration service. The customer is responsible for cluster configuration, the container images, and the applications that they build and run using containers. In platform as a service offerings, the cloud service provider manages the underlying infrastructure, including servers, storage, networking. They ensure availability, scalability, and reliability of the platform and ensure that automatic updates and patching of the runtime environment is performed. As a customer, you're responsible for developing and deploying the application code, configuring application settings and scaling parameters, and managing application data security and implementing access controls. For software as a service solutions, the cloud service provider is responsible for managing and maintaining the entire software application, including infrastructure, middleware, and applications. They are also responsible for ensuring the security, availability, and performance of the application, and they are responsible for data backup and disaster recovery. As a customer, you are responsible for managing user access and permissions within the application. You are responsible for ensuring data integrity and security through proper use of the application's features, and you should configure application settings to meet business requirements. All cloud providers use similar shared responsibility models. Here is the shared responsibility model on AWS. I won't focus on the details, but you can see the split is similar. AWS is responsible for security of the cloud, and these are all its components, the infrastructure, and some software, whereas the customer is responsible for security in the cloud. You can see that the responsibility split is very, very similar to Google's visualization. And Microsoft's Azure also has a similar model for shared responsibility. Here you can see the various responsibilities along rows. These are the security and management tasks that could be the purview of the customer or the cloud service provider. You can see that the tasks at the very top layers, the responsibility is always retained by the customer. For the tasks in the middle, based on the service model, the responsibility varies between the customer and the cloud service provider. And at the very bottom, the responsibility is always with the cloud provider. And again, you can see for on premises setups, the entire responsibility lies with the customer. For infra as a service setups, most of the responsibility is with the customer, except at the very bottom where the physical host, network, and data center are managed by the cloud provider. For platform as a service offerings, the cloud providers tend to take on more responsibilities. And finally, for software as a service offerings, the platform takes on much of the responsibility. Very little lies with the customer. For every organization, in order to make the decision to transition to the cloud, there is an important factor that they need to keep in mind: the total cost of ownership. Total cost of ownership, often abbreviated as TCO, is a financial estimate that encompasses the complete direct and indirect costs associated with acquiring, deploying, operating, and maintaining a product or a system over its entire life cycle. Keeping a software system up and running has many costs, some of which are obvious and others less so. It's important that you understand all of the involved costs so that you can make the right decision during migration. The total cost of ownership provides a comprehensive view of the economic impact of an investment beyond just the initial purchase price. It includes all of the relevant costs, such as the initial acquisition, installation, training, operation, maintenance support, and eventual decommissioning or replacement. TCO analysis helps organizations make informed decisions by comparing the long term financial implications of different options, ensuring that both immediate and future expenses are considered. When organizations make the decision to move to the cloud, this total cost of ownership becomes very important because you have to accurately assess how your costs are going to be, how they're going to change. There are some common mistakes that companies tend to make when comparing the total cost of ownership for on premises versus cloud. Let's discuss a few of these. The first thing is they tend to ignore hidden operational costs. People often overlook ongoing operational expenses for on premises infrastructure, such as power, cooling, and physical security. These hidden costs can significantly add to the overall TCO, and they are not always immediately apparent when making initial cost comparisons. Another common fallacy is underestimating the maintenance and support expenses. The cost of maintaining and supporting on premises hardware and software, including routine updates, patches, and dealing with hardware failures, is frequently underestimated. This can lead to a misleading TCO calculation that does not fully capture the true long term costs. Or, while making comparisons, companies might overlook staff and training costs. On premises solutions typically require a dedicated IT team for management and maintenance. The salaries, benefits, and ongoing training for these staff members are often not fully accounted for in TCO comparisons, leading to an underestimation of the costs associated with on premises infrastructure. And another fallacy is failing to consider scalability and flexibility. The cost of scaling on premises infrastructure to meet growing demand can be substantial, involving new hardware purchases, installation, and configuration. Also, with on premises, you tend to over provision your current systems and they tend to be underutilized. This is not factored into TCO calculations. Cloud solutions, which are on demand, scalable, and elastic, often offer better resource utilization. When you're computing the total cost of ownership, there are three costs you need to consider: capital expenditures or CapEx, operational expenditures or OpEx, indirect costs. We'll first consider each of these in turn for on premises infrastructures. Let's start with on premises CapEx. These are by far the easiest to understand. These costs include initial hardware costs when you purchase servers, storage devices, networking equipment, and backup hardware. Along with the initial purchase costs, you should also consider the eventual replacement or upgrade costs. Another component of CapEx is the purchase of software licenses. Licensing costs for operating systems, databases, virtualization software, and application software. These may include one time purchase costs or annual licensing fees. And then, of course, you have the data structure, infrastructure costs, the cost for building or leasing a data center, including the physical space, power, cooling, and physical security systems. Next, let's consider the operational expenditures associated with traditional on premises infrastructure. The first is cost for maintenance and support. Ongoing maintenance of hardware and software, including support contracts and any warranty extensions that you might have to take on. Then there are the salaries and benefits for IT staff required to manage and maintain the infrastructure. These could be system administrators, network engineers, hardware professionals, security professionals. Then there are recurring costs for utilities, for electricity to power and cool data center equipment. That's often a significant ongoing expense. And one must not forget depreciation here. The hardware that you purchase is going to get depreciated or less valuable over time. And finally, we have a bunch of indirect costs. Let's look at some examples of what these might be. The first is the cost of downtime, the potential revenue loss and productivity impacts from system downtime due to hardware failures, software issues, or maintenance activities. And then, of course, we have the cost for scaling up capacity. You are likely to incur additional costs, which might involve purchasing additional hardware and software. And then finally, another source of indirect costs can be costs associated with decommissioning and disposing of obsolete hardware. as well as migrating to new systems. Now that we understand the total cost of ownership of on premises infrastructure, let's consider the total cost of ownership of cloud platforms. We'll consider the same three components: capex, opex, and indirect costs. Let's start with the capital expenditures involved for cloud computing infrastructure. The main thing about using cloud infra is that you significantly reduce your capital expenditures. All of the costs associated with buying hardware and equipment, well, they are completely eliminated. Also, the costs associated with the maintenance of the physical space is shifted to the cloud provider. The whole idea of using the cloud is that you have a minimal initial investment. Cloud computing significantly reduces or eliminates the need for upfront capital investments in hardware and data center infrastructure. Initial costs are primarily related to service setup and configuration. These tend to be non physical costs. Now, with cloud computing infrastructure, your capital expenditures are often converted to operational expenditures, and these tend to be significant. You might be paying a bunch of subscription fees. These are ongoing costs for cloud services, typically billed on a pay as you go basis. These include costs for compute, storage, networking, and other managed services. If you're relying on managed services, there might be additional costs that are included. There might be costs for database management, machine learning platforms, and application services, which reduce the need for in house expertise. One of the advantages of cloud computing is that you have a reduced need for extensive IT staff, as many of the infrastructure management tasks are handled by the cloud provider. However, there may still be a need for cloud architects, security experts, and developers, and all of them might need extensive training to keep up with the cutting edge technology available on the cloud. And then, of course, there are indirect costs with migrating to and working on the cloud. The first of these relate to training and transition costs. Moving to the cloud often requires training staff on new technologies and processes. There are, of course, costs associated with this training, as well as the cost of time required for employees to become proficient with the new systems. Then we have costs associated with downtime during migration. During the transition to cloud services, there may be periods of downtime or reduced productivity as applications and data are migrated and users adjust to the new environment. Once you've selected your cloud provider, there is a certain level of vendor lock in. You have to take into account vendor lock in and switching costs. Relying heavily on a specific cloud provider can lead to vendor lock in, which means it's costly and complex to switch to another provider in the future. The lock in costs can include costs associated with redoing and re architecting your applications and potential data migration fees. And finally, there are costs associated with running your applications in an optimal manner on the cloud. Ensuring optimal performance may involve additional costs for performance tuning, monitoring, and management. This includes expenditures on third party tools or services to enhance performance and ensure efficient resource utilization. In this video, we'll introduce and discuss some common terms that are used when we speak about the global infrastructure that cloud service providers are building. These are just terms that you might encounter when people speak of the cloud and of data centers around the world, and you should understand what these terms mean. Cloud providers are building extensive global networks to deliver high speed, reliable, and low latency services to users around the world. A critical component of this infrastructure is the deployment of undersea cables, which connect different continents and regions, forming the backbone of the global internet. These undersea cables are essential for supporting the huge data traffic generated by cloud services and ensuring seamless connectivity across the world. This image shows you the network of undersea cables that Google has. You can see just the sheer scale of the operation. And imagine Azure, Amazon, all of these have equivalent number of undersea cables. All major tech companies, especially cloud providers like Google, Amazon, and Microsoft, invest heavily in undersea cable projects. These investments are aimed at enhancing their global network capacity, reducing latency and ensuring redundancy for better reliability and performance of their cloud services. If the services of one provider are noticeably faster and quote unquote better than other providers, well, they have a competitive advantage. And this is why all of the major cloud providers are in a race to set up this undersea infrastructure. These undersea cables are super important because they carry a significant portion of the world's data traffic, enabling high speed internet connections between continents. These cables are capable of transmitting terabits of data per second, which is crucial for supporting the high bandwidth demands of cloud applications, video streaming, online gaming, and other data intensive activities. Every tech giant wants their services to be as close to their end users as possible. By strategically laying undersea cables, cloud providers can reduce the physical distance that data needs to travel, thus minimizing latency. Especially today, when so many of our applications are real time, video conferencing, online gaming, financial transactions, interactive web applications, lower latency is vital for all of these. And of course, the deployment of multiple undersea cables provides redundancy, ensuring that if one cable fails, others can handle the data traffic. This mitigates the risk of service interruptions due to cable cuts or other issues. In the context of networking and access to services, let's discuss two important terms: throughput and latency. Throughput refers to the amount of data that can be transmitted from one point to another within a given time frame. It's typically measured in bits per second (bps), megabits per second (mbps), or gigabits per second (gbps). When you talk about the speed of your internet connection, you're actually referring to the throughput. Latency refers to the time it takes for a data packet to travel from the source to the destination across a network. It's typically measured in milliseconds. This latency is critical for real time applications which require very quick responses. If you made phone calls or in a video conference, you often encounter a lag or a delay when a particular person speaks. That's latency. Throughput is the amount of data or the rate at which data can be successfully delivered over a network. Higher throughput indicates a higher capacity for data transfer. The term throughput is often used interchangeably with bandwidth. Throughput is the actual achieved data transfer rate, whereas bandwidth is the theoretical maximum data transfer rate of the network. Throughput is affected by the network capacity. The physical infrastructure and the technology determine what throughput you can get, whether you're using fiber optics or wireless. Throughput also depends on network congestion. If you have very high traffic volumes, that can reduce the throughput. Latency, we know, is the time taken for a packet to get from the source to the destination. There are many aspects of latency. There is the propagation delay, the time it takes for a signal to travel through the physical medium. There is the transmission delay, the time taken to push all the packet's bits onto the wire or medium. There is a processing delay, the time taken by a network device to process the packet header and make forwarding decisions. There is queuing delay, the time a packet spends waiting at queues at intermediate network devices due to congestion. All of these are components of latency. There are several factors that affect latency. For example, physical distance. Greater the distance between source and destination, higher the latency. Network hops. The number of intermediary routers or switches a packet must traverse can increase latency due to additional processing. Network congestion. High traffic volumes can lead to queuing delays, increasing latency. Another term that's often used is edge network. This just refers to a distributed computing paradigm where computation, data storage, and data processing occurs closer to the data source or the edge of the network, rather than in a centralized cloud data center. The proximity to the source of data generation enhances response times and saves bandwidth by reducing the amount of data that needs to be transmitted to a centralized location for processing. Let's say some processing occurs because of some data that you've uploaded. That processing should be as close to you as possible and not somewhere far away from you. The edge network places computational resources as close to the user as possible, minimizing the distance data has to travel. This proximity reduces latency and improves real time processing capabilities. Cloud computing traditionally tends to be centralized. However, edge networks distribute processing tasks across multiple edge nodes, And these nodes can be located in various locations, such as local servers, gateways, or even on the device themselves. You might have heard of companies pushing their AI systems to be on mobile devices. Well, processing can occur right within your device, giving you faster predictions. Edge networks support horizontal scaling, meaning you can increase the computational capacity of edge networks by adding more edge nodes to handle increased data loads. This distributed architecture allows for greater flexibility and resilience. And finally, edge devices and nodes perform initial data processing and filtering before sending relevant data to the cloud. This reduces the volume of data transmitted and stored in central data centers. Next, we'll discuss some common concepts and terms that you'll hear in the context of the cloud: availability, scalability, elasticity, fault tolerance, and disaster recovery. Let's start off by discussing availability. Now, you want your service to be highly available. What does that mean? Availability refers to the degree to which a system, service, or application is operational and accessible when required for use. Basically, high availability systems are designed to ensure minimal downtime, providing continuous operation. How do you get high availability? Well, you set up redundancy, so you have multiple data centers serving your resources. You implement failover mechanisms, so if the primary fails, you switch to a standby, and you make sure that you maintain your infrastructure. In cloud computing, availability is often quantified by service level agreements or SLAs, which specify the expected uptime and performance metrics. In this example here, notice that the request from the client is sent to a load balancer, which then directs the request to compute instances that lie in different zones or different data centers. A zone can be thought of as a data center. We'll discuss that in more detail in a bit. If there is an outage in one data center, the request should be redirected to another one that's functioning without a hitch. Next, let's talk about scalability. This is the ability of a system to handle increased load or to be expanded to accommodate growth. As you can see, there are two types of scaling here: horizontal scaling and vertical scaling. Let's talk about vertical scaling first, because this is the more typical traditional scaling methodology. Let's say you have a server performing some kind of processing. If the data processing load on the server increases, you can add more compute resources to the same server. You can add more memory, you can add more CPUs, and you're making that single server, that single resource more powerful. That is vertical scaling. Horizontal scaling works differently. This is where, let's say you're performing an operation like data processing, that operation is not performed by a single server. Instead, the processing is distributed across a cluster of servers, a cluster of machines. It's distributed processing. Scaling up and down based on demand is easier in horizontal scaling. If you need more processing power, you simply add more servers or more machines to the cluster. If you need to scale down processing power, well, you just remove machines from the cluster. Most modern applications follow this distributed architecture and use horizontal scaling. Next, let's talk about elasticity. This refers to the dynamic allocation and deallocation of resources as per the changing demands of applications. Elasticity is related to scaling in that it still talks about the scaling of resources, but the automation of resource scaling, that is what is referred to as elasticity. Let's say you had static scaling, your scaling was not elastic. Your black line represents your current capacity, and your workloads can fluctuate around what your capacity can handle. With static scaling, your resources are likely to be underutilized most of the time. With dynamic or elastic scaling, your resources grow and shrink based on the workload, and they do so in an automated manner. So, if you experience very high demand, well, more resources will be added to deal with that demand. If your demand falls, resources will be taken away or turned down so that your utilization remains more or less constant. Next is fault tolerance. This is the capability of a system to continue functioning correctly in the event of a failure of some of its components. Fault tolerance is achieved through redundancy, replication, and automatic failover mechanisms. Here, notice that requests are sent to a load balancer, which are then passed on to web servers. There are multiple web servers in the backend serving requests. This is redundancy via replication. Now, let's say that these web servers fail. You can have an additional standby web server and you can fail over to serve requests from the standby. This ensures that your system is highly fault tolerant. Closely related to fault tolerance is disaster recovery, which is just a set of policies, tools, and procedures to enable the recovery or continuation of vital technology, infrastructure, and systems following a natural or human induced disaster. Let's say your original web servers are all located in one particular geographic region. Let's say it's Iowa in the US. In case there is some kind of outage or complete failure in Iowa, you may want a standby web server somewhere else, maybe in Virginia or in Oregon. This is disaster recovery. These plans should include data backup, replication, and recovery strategies to restore normal operations as quickly as possible. Your organization has decided to migrate to the Google Cloud. But how do you start? How do you assess how the migration should be performed? How do you assess the current capabilities of your team? And how do you know what they need to train or learn upon before they can help with the transition? Google helps you with this. Google has a cloud adoption framework that provides a structured approach to help organizations successfully transition to the cloud, leveraging Google Cloud services. This framework helps you identify key activities and objectives that will reliably accelerate your cloud journey. This framework builds a structure on the rubric of people, process, and technology that organizations can work with, providing a solid assessment of where they are in their journey to the cloud and actionable programs that get them to where they want to be. This cloud adoption framework is a result of Google's vast experience helping companies transition to the cloud. Now, I'll be discussing the main features of the framework here. Google's complete cloud adoption framework is available as a PDF at this URL that you see here on screen. The link here also has an assessment which allows you to assess your organization's cloud maturity today. If you're really thinking about transitioning right away, well, this assessment might be useful to see where exactly you stand. Google feels to build a truly cloud first organization, there are four themes or realms that you need to excel in, whatever your business goals. These themes lay the foundation of your cloud readiness. The first of these is learn. The first theme is learn, and this basically refers to the quality and scale of the learning programs that you have in place to upskill your technical teams. This might include the integration of experienced external partners to support your IT staff. Also, it's important for you to evaluate who's participating in these programs, how widely they are implemented across the organization, the level of effort that's invested, and the tangible outcomes that have been achieved. The second theme is lead, and this refers to the extent to which IT teams are supported by a mandate from leadership to migrate to the cloud and the degree to which the teams themselves are cross functional, collaborative, and self motivated. It's important that the team has clear directives from executives to move to the cloud, and you need to be constantly assessing how these teams are organized, whether they have strong executive backing, and how cloud initiatives are budgeted, managed, and evaluated. The third theme is scale. This is the extent to which you use cloud native services that reduce operational overhead and automate manual processes and policies. This is where you consider how you provision cloud services, how you allocate resources for different workloads, and manage application updates. The goal is to streamline operations and improve efficiency through automation. The last theme, secure, refers to the capability to protect your services from unauthorized and inappropriate access with a multi layered identity centric security model. This security capability relies on the maturity and integration of your learning, leadership, and operational strategies. You need to evaluate the security controls and technologies in place and overarching strategies that guide your security measures. How ready your organization is to move to the cloud and be successful there is determined by your current business practices in each of these four themes that we've discussed. For each theme, these practices will fall into one of the following phases. There are three phases, and each of the themes can be in any of these three phases. The first is tactical. In the tactical phase within your org, individual workloads have been moved to the cloud, but there is no real overarching strategy to unify them or plan for future expansion. The primary goal is to reduce costs for specific systems and migrate to the cloud with minimal disruption, resulting in quick but small scale gains. A more mature phase is strategic. This is where a comprehensive vision guides the design and development of individual workloads with a focus on future scalability. This is where within your org there's a growing acceptance of change, and both people and processes are now involved in the cloud adoption journey. Your teams are working well together and they are effective, thus enhancing the overall business value of cloud adoption. The most mature of all phases is transformational. This is where cloud operations are running smoothly, allowing focus to shift towards integrating data and leveraging insights gained from cloud operations. In this phase, data is shared transparently across the organization. New data is collected and analyzed, and advanced analytics and machine learning are applied. For each of the four themes and the three phases possible for each theme, you have a nice breakdown with a nice visualization of the cloud maturity scale so you can understand where exactly your organization is at across the board. You can see the four themes along the columns: learn, lead, scale, and secure. And you can see the three phases along the rows: tactical, strategic, and transformational. So, for example, if your team is in the tactical phase for the learn theme, they are self taught and they rely on third parties in the cloud migration journey. If they are in the strategic phase in the lead theme, you've set up a new cross functional cloud team to allow people to work together effectively. If your cloud maturity is at the transformational phase in the scale theme, your products are constantly changing and evolving. All change is constant, low risk, and fixed very quickly. Once you've identified your current stage in the cloud maturity journey, the next step is to plan and organize your cloud adoption program. You'll need to implement various work streams referred to as epics. These epics are designed to be distinct from each other, aligned with specific groups of stakeholders, and can be broken down into smaller tasks or user stories to simplify program planning. These epics are categorized under the familiar themes of people, technology, and process. You can see this Venn diagram with overlapping areas between circles, outlining the epics that you need to focus on. Google's recommendation is if you can only focus on a few epics, prioritize those that are in the highlighted segments that form the overlap between people, technology, and process. You can reach out and take Google support in your cloud migration journey. Google can set you up to work with a technical account manager or a TAM. With the TAM's help, you can perform a high level assessment of your organization's cloud maturity, which will tell you how to prioritize your training and change management programs. The TAM will help you with your partner relationships, your cloud operating model, and your secure account configuration. The TAM works within the cloud adoption framework and guides you along your journey from your first cloud project to becoming a fully cloud first organization. Earlier on in this journey, I introduced you to a few widely used services and products on the Google Cloud platform. We looked at services for compute, storage, networking, AI, ML, and so on. Starting from this video, we'll actually dive into Google Cloud concepts across these services. Let's start off with big picture concepts first. We'll understand what regions and zones are. On the Google Cloud, the term region refers to specific independent geographical locations where Google Cloud resources are hosted. Each region contains multiple zones and is designed to be isolated from other regions to enhance fault tolerance and reduce latency. Regions are just geographical areas around the world. For example, Google Cloud has a number of data centers in Iowa. Iowa is a region on the Google Cloud platform. The data centers that are in Mumbai in India, make up another region, Asia South 1. Each region is made up of multiple zones, where zones are just isolated locations within a region that actually hosts GCP resources. Each zone has its own power, cooling, and networking infrastructure to provide high availability and fault tolerance within a region. The best way to think of a zone is that it's a single data center. The zone may not be one data center, it could also be two or three data centers all connected together. A single region usually has multiple zones, and what I've seen with Google is that each region has a minimum of three zones for fault tolerance. The zones in a region are all connected via high speed network links. Zones and regions are logical abstractions of underlying physical resources which may be spread across one or more physical data centers. These data centers may be owned by Google or they may be leased from third party data center providers. Let's discuss each of these in a little more detail, starting with regions. We know they are specific geographic locations where GCP resources are hosted. Regions are set up to ensure geographic diversity. They are distributed globally to provide localized services and reduce latency for users in different parts of the world. There are Google regions in every continent of the world except maybe Antarctica. And of course, most continents have multiple regions. Regions host completely independent resources. Resources in one region are independent of those in another, which means any issue that brings down one region generally does not affect other regions. Resources are distributed across and grouped into regions to ensure compliance and to meet data residency requirements. Regions help organizations comply with data residency and regulatory requirements by allowing them to choose specific locations for their data and workloads. If your organization has a need that this particular workload and this data has to be stored in the European Union, choose a region within the European Union. Here are some regions on the Google Cloud. US Central 1 is a region located in Iowa, that is the central United States. Europe West 1 is a region located in Western Europe, it's actually in Belgium, and Asia East 1 is a region in Eastern Asia. The region is actually in Taiwan. Next, let's discuss zones in more detail. A single region is made up of multiple zones. Zones within a region are designed to be isolated from each other, so a failure in one zone does not affect other zones in the same region. This setup enhances the redundancy and availability of applications. When you host your software solution on the Google Cloud, you can distribute resources across multiple zones within a region to achieve higher availability and fault tolerance. For example, for high availability Cloud SQL databases, you typically have a primary instance in one zone within a region, and your backup instance is configured in a second zone in the same region. Zones in the same region are connected by high bandwidth, low latency networks, enabling seamless communication and data transfer between zones. A zone is a deployment area for Google Cloud resources within a region. Zones should be considered a single failure domain within a region. To deploy fault tolerant applications with high availability and help protect against unexpected failures, make sure you deploy your applications across multiple zones in a region. I find it easy to think of a zone as a data center so that I know it's not fault tolerant. However, zones and regions are both abstractions over data centers and they have no direct mapping with data centers. Let's discuss one way to categorize Google services and resources. Now, resources can be zonal resources, and these are resources that operate within a single zone. If there is an outage or failure in a zone, that resource will be unavailable. So, zonal outages can affect some or all of the resources in that zone. An example of a zonal resource is a compute engine virtual machine instance that resides within a specific zone. Regional resources are resources that are redundantly deployed across multiple zones within a region. Regional resources typically tend to be more highly available relative to zonal resources because the failure of a single zone will not bring down that resource. For example, App Engine applications are regional resources and hence more fault tolerant than an app deployed within a single virtual machine, which is a zonal resource. A number of Google services are multi regional. They are managed by Google to be redundant and distributed within and across regions. These services optimize availability, performance, and resource efficiency. Google services such as Bigtable, Cloud Storage, Artifact Registry are all multi regional. These multi regional services are designed to be able to function following the loss of a single region. So, if all of the zones in a region are down, those services will still work. Google also supports a number of global services. The resources for these services reside globally, they're spread across the world, and the idea of zones and regions are abstracted away. Resources such as the network, that is, the virtual private cloud, images, snapshots, all of these are examples of global resources. With global resources, there is no concept of region or zone. They are not tied to any geographic location, they just reside globally. And finally, Google has a number of internal services. Underpinning and supporting many customer facing Google Cloud services are a set of proven internal services like Colossus, Borg, and Chubby. These internal services are either globally load balanced across multiple regions or dedicated to each region in which they are available. These internal services form the backbone of your applications, and as a user, you're unlikely to interact with them directly. None of these internal services are limited to a single logical data center or to a region. Let's discuss service dependencies on the Google Cloud for just a bit. In general, for Google Cloud services, if a single region fails, only customers in that region are impacted. Customers who have multi region products are not impacted. Google Cloud has designed these services with a goal to prevent correlated failures across regions. We discussed internal services just about a minute ago. All Google Cloud services rely upon these core internal tools to provide fundamental services such as networking, access to data centers, and identity and authorization systems. These tools are built to be resilient to regional outages with the goal of one region not being impacted if other regions are not available. Google Cloud also has this concept of scopes. The scope determines the accessibility of a resource to other resources on the Google Cloud. A resource is always globally accessible to users, but how accessible it is to other resources determines its scope. Global resources are accessible from any region or zone. Disk images, disk snapshots, and VPCs or networks are examples of global resources. Regional resources are only accessible to other resources from the same region. Regional resources include regional static IP addresses and regional persistent disks. Zonal resources can only be accessed by other resources that are located in the same zone. Zonal resources include virtual machine instances and zonal persistent disks. Now that we've understood regions and zones, let's quickly talk about latencies. Interregional latencies on the Google Cloud are typically of the order of 3-digit milliseconds, 400, 500, 600 milliseconds. Interzonal latencies, that is within zones in the same region, are typically of the order of 2-digit milliseconds, 20, 30, 50 milliseconds. On this page, I've just listed out a few examples of global, regional, and zonal resources. There are global static IP addresses, images and snapshots are global, networks, firewalls, and routes are also global. If there are terms here that you cannot understand, don't worry, you'll understand them by and by before the end of this journey. Examples of regional resources include subnets, these are just logical divisions of a network, regional static external IP addresses, and regional persistent disks. And zonal resources are virtual machine instances and zonal persistent disks. The scope of any operation that you perform on the Google Cloud depends on what kind of resource you're working with. Creating a network is a global operation because a network is a global resource. Reserving an IP address is a regional operation because the address is a regional resource. Here in this visualization, you can see the network is global, it can span regions. There are multiple zones within a region, and virtual machines and disks tend to be zonal resources. They are provisioned within a zone. whereas a static external IP address is a regional resource. I'd like to explain one last concept on the Google Cloud before we move on to other topics, the point of presence or POP. A point of presence is a physical location where Google has deployed networking equipment to connect users to its global network. Google operates a global network of peering points of presence, which means customer traffic can travel within the Google network until it's very close to its destination, providing users with better experience and better security. POPs provide connectivity between Google's global network and local internet service providers. This ensures that data can travel from users to Google's data centers and back with minimal latency and high reliability. Strategically placing POPs close to users, Google reduces the physical distance that data must travel, thus resulting in faster response times for applications and services. POPs help manage and optimize the flow of data. They act as hubs where data can be efficiently routed to the appropriate Google data center or service endpoint. This helps in load balancing and avoiding network congestion. POPs are integral to Google's content delivery network. They cache frequently accessed content closer to users, reducing the time it takes to load web pages, videos, and other digital content. Multiple POPs across different geographic locations provide redundancy. If one POP experiences an issue, traffic can be rerouted to another POP, ensuring continuous service availability. If you're interested in seeing where Google's data centers are located around the world, here is a great URL that shows you exactly this. Cloud.google.com about locations will show you the locations of Google Cloud regions around the world. This will always give you the latest information, so depending on when you're viewing this course, you'll have the up to date information of Google Cloud locations. Google Cloud is constantly adding new regions to support its platforms. You can see that in 2023 and 24, new regions were added in Berlin, Doha, Dammam, Johannesburg. So, four new regions came up in just a matter of 2 years. Let's scroll down below and that will give you a big picture overview of Google Cloud's data center capacity. There are a total of 40 regions around the world. Regions, as you know, are specific geographic locations where GCP resources and services are hosted. Regions comprise of zones, and multiple zones in a region provide high availability and redundancy within that region. You can see that these 40 regions have a total of 121 zones. I've noticed on the Google Cloud that every region tends to have at least 3 zones. So if you host your services within a region, you can make sure that you can configure high availability and you get redundancy because of the multiple zones. Zones, as you know, are isolated locations within a region and represent distinct data centers. Hosting your services in a single zone is not highly available. Every zone is independent of other zones with its own power, own cooling, and networking infrastructure. So, if there is an issue in one zone, other zones will not be affected. Google has a total of 187 network edge locations. These are strategically placed data centers and infrastructure that are closer to the end users. Edge locations are closer to users and thus reduce the time it takes for data to travel and makes it faster for users to access cloud services. Edge locations often serve as points for content delivery networks or CDNs to cache and deliver content quickly to users around the globe. And you can see that Google Cloud is available in 200 plus countries and territories. It definitely has a very wide reach. And here is a geographic representation of Google's regions. Let me just click on this icon here, and that will allow us to see the map on full screen. Every filled circle that you see here is a current region with at least 3 zones. Every triangle is a region that's planned in the future. You can see that the regions are distributed across the world, and you can always choose to host your services in a region that's close to where your users are, ensuring that your users have low latency when they access your app. I find the distribution of Google's regions very interesting, but what I also find interesting is Google's network. Let's select this network tab and let's take a look at Google's network. Notice a number of interesting details about the network. There are both blue lines and green lines. The blue line represents the current network of fiber optic cables that Google has already set up. And you can see that the blue lines span the globe. In addition to their current network, Google is constantly investing in new network infrastructure to get cloud services and technologies closer to you faster. The green lines on this graph represent submarine cable investments. These will be included and part of Google's network in the future. The gray filled circles that you see here on this map are Google's edge point of presence or edge POPs. Let me expand this graph so that you can see these in detail. An edge point of presence on the Google Cloud refers to a network location where GCP's edge network interfaces with other networks, including internet service providers. These locations tend to be crucial for delivering content and services efficiently and with low latency to end users. You can see that Google has an edge pop in almost every continent. This map also shows you Google's Cloud CDN point of presence. So if you select that option and let's zoom into the map again, the gray filled circles are Cloud CDN POPs. These tend to overlap with the edge points of presence for the most part. A Cloud CDN, that is Content Delivery Network point of presence, is a strategically located data center used to cache and deliver web content to users more efficiently. These CDN points of presence ensure that content is delivered from the closest possible location to the user, reducing latency and improving performance. Let's go back and let's select the last option here, the Media CDN point of presence. Media CDNs are specialized nodes within a content delivery network designed to handle the efficient distribution and delivery of media content. Media content can include video, audio, and other large files. These POPs are strategically located to optimize the performance, reliability, and scalability of media content delivery. If you look at India as a country, you can see there are a large number of media CDNs there. So if you're consuming, say, YouTube in India, you'll find that certain videos which are very popular in India get delivered very quickly with very low latency. That's because those videos tend to be cached in these media CDNs. I've definitely noticed that if I were to access a video that may not be very popular with Indian users, maybe it's not cached in a media CDN within India or close to India, well, that content takes much longer to load on my YouTube app. Let's head back and let's explore this Google Cloud Locations page further. And here you'll find the different products and services on the Google Cloud available by location. Typically, the most common Google Cloud products and services such as virtual machines, cloud storage, basic databases, data warehouses, these tend to be available in all regions across the world. But there might be certain products that are not available in some regions. For example, you can see that App Engine is not available in the Dallas, US South 1 region. Notice there is no green circle near where my cursor is. App Engine is not available in Dallas. So if you're trying to host your App Engine application here, well, you're out of luck. You'll have to pick another region close to you. This page gives you a complete list of all cloud services and what regions they're available on across all continents. So if you're interested in Asia Pacific, just select that in the tab and then look for the services that you're interested in and see whether it's available in the region of your choice. The way you'll use this particular feature is you'll select the continent and the region that you're interested in and then scroll down to find the product that you want to work with, and you'll see whether it's available in your region. Now, there are certain products that are not tied to a particular region. These are referred to as global products and services. Here is a list of these global products. For example, the security product Cloud Armor that defends against distributed denial of service attacks, that's a global product. In data analytics, Looker Studio is global. Under management tools, the Cloud Billing API and Cloud Shell are global products not tied to any specific region. There is an entire list here, and this will be much more interesting and relevant once you're familiar with Google Cloud's products and services. Now, how do you decide which region you should pick to host your applications? There is a great tool that Google offers to pick your region. This is the Google Cloud Region Picker tool. Now, when you actually choose the region that will host your application, there are different parameters that you might want to consider. You might want to go for a region that has a lower carbon footprint. That is a region that's more environmentally friendly and is built based on sustained engineering practices. You might want to go for the lowest price region, or you might want to select a region that will offer the lowest latency for your users. I'm now going to click through to this Google Cloud Region Picker tool, and let's see how we can use this to select the right region for our cloud solution. We'll use these sliders that you see here at the bottom to select how important the different parameters are. And off to the right, you should see the recommended regions. So let's scroll down. Here are our three parameters optimizing for lower carbon footprint, lower price, or lower latency. And the slider allows you to express how important each of these are to you. You'll specify the measure of importance that you ascribe to each of these parameters. But what's important here is also to specify where your traffic is coming from. You need to indicate your current location, whether you're based in Asia, America, or Australia. That's important. Now you can pick the location of your choice. Since I'm located in India, I'm going to select my traffic as coming from India. I've kept my slider at the default parameters where each of the three parameters are equally important and they are all of medium importance. You can see that the slider is right at the center. Just another note, you can also filter your selection based on product availability. So if you're looking for a particular product that you want to use, well, that's the filter that you'll apply here at the bottom. Google has already set up a default selection of products highlighted in gray. I'll just stick with those. Now, based on traffic coming from India, here are the recommended regions off to the right, where every parameter is equally important. You can see that locations in Europe are recommended first, and as I scroll down, I can see locations in America, in the US. Well, but what if I said that lower price is the most important? Let me change my slider. Based on my increased importance for lower price, you can see there's just one European location that appears first, and then the remaining locations are from the US. And then if you scroll down, you can see Europe West one in Belgium and Montreal, Canada is also part of the recommendations. Now, what if price is not important at all? I'll set that to 0. Notice now that Europe West 3 in Frankfurt, Germany is second on the recommended list. That's clearly a region where prices are higher relative to other regions in Europe. But it likely has a lower carbon footprint and lower latency to users in India. Now, let me change another parameter. What if I indicate that latency is extremely important, price is not important, low carbon footprint of middling importance? You can see that the recommendations have completely changed. Europe North 1 is still first, but Asia South 1 in Mumbai, India now has a higher priority. I know from personal experience that this is an expensive region, so only when price is not a consideration and latency is a very important consideration does this region make sense. Other recommendations here include another region available in Delhi, Asia South 2. Well, now that you understand how this Google Cloud Region Picker tool works, I'll leave it to you to explore this on your own. Change where your traffic comes from to your location. Make sure you optimize the different parameters that you're interested in. Make sure you select the products that you're interested in and see what regions are recommended to you. I've changed the parameters, but let's say I'm interested in cloud functions. Observe that the recommendations change based on the product that you want to use on the GCP. In order to deploy your software solution, you will be provisioning resources on the Google Cloud. These resources could be virtual machines, you could set up a load balancer, maybe you'll configure a CDN cache, maybe you'll use a database, maybe you'll provision a network. On the Google Cloud, all of these resources lie within a hierarchy, and that resource hierarchy is what we're going to be discussing in this video. This is what the Google Cloud resource hierarchy looks like. You can think of this resource hierarchy kind of like a file system, though it's not actually a file system, but it's a similar hierarchy. This is a way of organizing and managing entities hierarchy. Each resource has exactly one parent, and this hierarchical organization enables you to set access control policies and configuration settings on a parent resource, and the policies and identity and access management settings are inherited by child resources. Observe the components in this hierarchy. We have the organization, within which we have folders, within which we have projects, and then we have the individual resources. Let's start at the top of the hierarchy. The organization resource represents a company and is the root node in the resource hierarchy when present. The organization resource is the hierarchical ancestor of folder and project resources. Any access control policies that you apply on the organization flows down through the hierarchy and it applies to all resources in the organization. The organization resource is closely associated with the Google Workspace or Cloud Identity account. When a user with a Google Workspace or Cloud Identity account creates a Google Cloud project resource, an organization resource is automatically provisioned for them. The organization resource is not always present. If you were to work on the GCP using your Gmail account, for example, you won't have a corresponding organization. But if you were to use a Google account associated with your company, you'll find that the organization resource is present. The organization is at the top of the resource hierarchy, and policies applied at the organization level are inherited by all underlying projects and resources. The organization gives you centralized control over access and permissions. The identities for accessing Google Cloud resources come from Google Workspace or Cloud Identity accounts. Each account can provision exactly one organization resource, and this resource acts as the central point for managing all new Google Cloud projects created by account members. Now, why does it help to have an organization resource? Any Google Cloud project created by an account member belongs to the organization. Administrators of the organization have central control of all resources. They can view and manage all of your company's project resources, which means they can no longer be shadow projects or rogue administrators. Now, let's say an employee creates a project within which he or she is working. That project belongs to the organization and not to the employee. Tomorrow, if the employee were to leave the organization, the project resource would still be available to others. Folder resources are optional resources which provide an additional grouping mechanism and isolation boundaries between projects. They can be seen as a sub organization within the organization. Folder resources can be used to model different legal entities, departments, and teams within a company. For example, a first level folder resource could be used to represent the main departments in your organization. Subfolder within the top level folder can represent individual teams, and so on and so forth. Both organization and folder resources are optional. However, you cannot work on the Google Cloud without creating a project. The project resource is the base level organizing entity. Organizations and folders may contain multiple projects. You have to create a project resource before you can use the Google Cloud. This forms the container for creating, enabling, and using all Google Cloud services, managing APIs, enabling billing, adding and removing collaborators, and managing permissions. When you interact with Google Cloud resources, you have to provide the identifying project resource information for every request that you make. At the very bottom of the hierarchy, we have resources. These are components that you provision. They can be virtual machine instances, app engine services, cloud storage buckets, anything. A resource is any component that incurs billing. Anything that you have to pay for that you provision on the Google Cloud, whether it's a database or some storage service or an ETL pipeline, that's a resource. All resources have to live within a project. You cannot have a resource that exists outside of the project container. Now, it's possible for you to set identity and access management permissions and policies on a single resource. These allow you to specify who can perform what operations on the resource. In addition, IAM policies inherited from the organization, the folder, and the project levels flow down to the resource level. A resource is, of course, a single entity and is at the lowest level of the hierarchy. Let's talk a little bit about identity and access management policies and how they're inherited down the resource hierarchy on the Google Cloud. I'd mentioned earlier that the organization and folder components are optional. If you log into the Google Cloud using your Gmail account, they won't exist. But if you're working within an organization, they will exist. Off to the left, you can see the Google Workspace or Cloud Identity account, which represents a company, and this is a prerequisite to have access to the organization resource. This provides identity management, recovery mechanisms, ownership, and lifecycle management. Here in this image, you can see the link between the Google Workspace account, cloud identity, and the Google Cloud resource hierarchy. Identity and Access Management, or IAM, lets you assign granular access to specific Google Cloud resources and prevents unwanted access to other resources. This lets you control who has what access to which resource. You can set an IAM policy at any level, organization, folders, or projects, and they'll be inherited down to individual resources. A policy set at the organization level will be inherited down to folders, projects, and individual resources. There are several different ways you can access Google Cloud resources to work with them. The first is the Google Cloud Console, which is a web based interface for managing resources. It provides a GUI to interact with various GCP services, making it easy for users to navigate and manage their cloud environment. Cloud Shell is an online shell environment provided within the Cloud Console. It provides command line access to your Google Cloud resources with pre installed tools and libraries. Google Cloud provides several command line tools for advanced users who prefer scripting and automation when dealing with resources. gCloud is the main command line SDK, but there's also GSUtil to work with buckets, BQ to work with the BigQuery data warehouse, kubectl to work with Kubernetes clusters. Google also offers APIs for programmatically accessing and managing its services. There are also client libraries available for various programming languages. Those tend to be a more convenient way to access the APIs. Let's discuss each of these in just a little more detail, starting with the Cloud Console. The Cloud Console offers a dashboard which gives you an overview of your GCP resources, usage, billing, and performance metrics. It allows you to create, configure, and manage resources like virtual machines, storage, databases, and networking components. You can also manage identity and access management, roles and permissions, set up security policies, and monitor security alerts. You can use the Cloud Console to track and manage your billing information, set up budgets, and view cost reports. And finally, this includes interactive interfaces for Cloud SQL, BigQuery, Kubernetes Engine, and other Google services. The Cloud Shell is another way to access and work with Google resources. The Cloud Shell offers a command line interface right within your browser. It's a pre configured environment that comes with essential command line tools like gCloud, that is a Google Cloud SDK, BQ to work with BigQuery, GSUtil to work with cloud storage buckets, and many others. Cloud Shell offers 5 GB of persistent disk storage, allowing you to store scripts, files, and other resources. Cloud Shell is a browser based terminal, so it's accessible from any browser, providing you a secure way to manage your resources without needing local installations. If you'd like to work using the command line, you don't need to download and install the Google Cloud SDK if you use Cloud Shell. Cloud Shell also offers a built in code editor. This is an integrated code editor for quick edits and development tasks. Google has a host of command line tools that you can use to interact with Google services and resources. gCloud is the primary command line tool for interacting with GCP services. You can manage projects, compute resources, networking, and more. GSUtil is a separate command line tool to work with Google Cloud Storage buckets, supporting operations to manage storage buckets and objects. The BQ tool allows you to work with BigQuery. You can run queries, manage datasets, and perform data analytics tasks. kubectl is used for managing Kubernetes clusters and applications, providing control over deployment, scaling, and management of containerized apps. And finally, let's talk about the APIs and client libraries you can use to access Google Cloud resources. RESTful APIs provide endpoints for interacting with GCP services programmatically, allowing for custom integration and automation. Client libraries are just software development kits available for languages such as Python, Java, JavaScript, Go, and more. These libraries simplify API calls by handling authentication and formatting requests. In this demo, we'll log into the Google Cloud Platform and explore what the platform looks like. This will give you a little bit of an idea of how to work with the GCP in a hands-on manner. Now, the Cloud Digital Leader certification does not require any hands-on implementation or hands-on experience with the GCP. But you'll find that in this journey, I've included some hands-on components. Now, you can choose to execute and implement these hands-on components by setting up your own GCP account, or you can just follow along while I perform the demos. Now, why did I include hands-on demos in this particular journey, even though that's not really needed for the Cloud Digital Leader exam? What I found is that when you're just learning theoretical concepts, everything is very abstract and it's hard for you to understand how the platform really works. With a little bit of hands-on experience or just viewing some hands-on demos, you'll get a better feel for the Google Cloud and you'll find that you'll remember the concepts better. And this is why I've included hands-on demos, even though the Cloud Digital Leader does not mandate any hands-on experience. What we'll do first is log into the Google Cloud platform. I have an incognito window open. Navigate to this URL, console.cloud.google.com. This is the URL where you can access Google Cloud. Navigating to this URL will bring you to the Google sign-in page. Now, if you have a Google account, whether it's a Gmail account or your organization's Google account, you can just sign in to the Google Cloud platform. You'll directly have access. Of course, in order to access all of the resources available on the Google Cloud, you'll have to enable billing. I'll show you how you can enable billing in just a bit. But for now, just go ahead and type in your Google account username, click on next, specify your account's password, and go ahead and sign in. And this will take you to the main page on the Google Cloud. You might find a page that looks like this, but a little different. Now, why is my page different? That's because I use this account frequently to work with the Google Cloud, and I've already set up a number of projects that I can use. One of the projects that I've created, which I use often, is the LuniQuant project. So you can see that as soon as I sign in, I'm taken to LuniQuant. If you're signing in for the very first time, you might find that you're working within a project named My First Project. So where you see LuniQuant here at the top left of my page, you should see My First Project. When you first sign into your Google Cloud account, Google automatically sets up a project for you to work with. And the name of that project is usually My First Project. We've discussed that you can't work on the GCP without setting up a project. A project is a billable container for your resources. This is the foundational entity where all Google Cloud resources and services are organized and managed, and projects serve as a primary organizational unit for accessing and using GCP services. Now, in my case, my project LuniQuant sits under the lunicorn.com organization. That's because I'm using my organization's Google account. If you've signed in with a Gmail account, this idea of an organization will not exist and you'll be directly working within a project. Every project has a unique project number and a project ID. My project ID is LuniQuant. Now, this page is kind of a launch page for your Google Cloud. And you can see there are a number of links here giving you quick access to some of the most commonly used services. You can get access to Compute Engine, Cloud Storage, Kubernetes Engine, billing, APIs, and services. These are some of the most commonly used services on the Google Cloud, and these are quick links. If you click on this button corresponding to your project's name, this will bring up a dialog showing you all of the projects that you have access to. What you see here is a list of all the projects that I've created or have access to from the account that I use to log in, the Cloud User account. You might find that you have just one project, My First Project. If there are certain projects that you work on often, you might want to star those projects and you'll find those in this Start tab. And if you want to see all of the projects accessible from this account, that is, that have been shared with this account or have been created by this account, you'll go to the All tab. Because I'm using a Google account associated with my organization, all projects that I create lie within the lunicorn.com organization. Any project created by any employee of this organization will belong to the organization and not to that employee. And that's why this resource hierarchy is important. When your organization signs up for the Google Cloud, the organization component is the top level structure and all projects and folders are created within the organization. I don't have any folders here, but I do have all projects within my Lunicorn.com organization. Let's not use any of these existing projects. I've created these for different use cases. Let's create our own project. Click on this new project link off to the top right of the dialog, and this will take you to a page where you can set up your own project. Now I've specified the project name as Looney GCP CDL. Now you can name your project anything. There's no constraint of uniqueness on the project name. However, the project ID has to be globally unique. You can see that a default project ID of Looney GCP CDL has been auto-generated by Google Cloud. You can edit this ID if you want to. My suggestion would be to always have your organization's prefix for your project names so that your project name can be globally unique. Now, if you want, Google can generate a project name for you. So if you click on this little refresh button, Google will auto generate random unique project IDs for you. These project IDs are rather interesting. There's the Fifth Citadel Academic Being. There are some numbers and some letters all mixed in. Project IDs are globally unique. Whatever project ID you select has to be unique across all projects in the world. So, for example, if I try to pick a project ID that's common like this one, my first project separated by dashes, well, clearly that's an error because a project with this name already exists, belongs to somebody somewhere in the world. You can see that Google tells me very clearly that this project ID is not available. Well, let's go back to a project ID that makes sense for us, Looney GCP CDL GCP Cloud Digital Leader. Now, this project lives within the Lunicorn.com organization. I can select no organization. Well, but that's not the way you actually use the organization resource. So I select Lunicorn.com. The location of this project, well, this is where you specify a folder within which you want to place this project. Since I have no folders created, I'm just going to have this project lie directly under Lunicorn.com. That's all the information that you need to specify to create your project. Go ahead and click on the create button, and in a few moments, your new project will have been set up for you. Now I'm still on the Lunicorn project, so let me click on the button once again. Notice my Looney GCP CDL project is now available for me to select. I select that, and I'm now currently working in this project, the newly created Looney GCP CDL project. Note that the project ID is one that we selected, Looney GCP CDL, and the project number was automatically assigned by Google Cloud. This can be thought of as the home page of your project. Let's click on Dashboard, and this will take you to the main dashboard for your Google Cloud account. This dashboard is just a web-based interface that gives you an overview and management interface for all resources, services, and operations within your Google Cloud project. This dashboard is a centralized view to help you monitor and manage your cloud infrastructure. On the top left of this dashboard, you have the project information. At the center, you have an API graph which tells you what requests were made to various Google Cloud APIs recently. We have no recent requests for this project. We haven't done anything yet. And off to the right, you have the Google Cloud Platform status, which will give you information if any services are down in a particular cloud region. Below that, I have billing information. If you can't see the billing tile, it's likely because billing is not enabled for your project. Now, if you scroll down, you see a bunch of other information. You have a monitoring tile where you can set up dashboards that you can quickly view. Off to the left, you have quick access to commonly used Google Cloud resources, Compute Engine, Cloud SQL, BigQuery, Cloud Run, and so on. And as you scroll further down, the Getting Started tile gives you quick link access to useful tutorials. If you've set up error reporting, the error reporting tile gives you insight into what's happening. And then you have a news tile which gives you Google Cloud News right here within your dashboard. Here we are on the main dashboard of the project that we've created. You can always look at the top of your screen and see what project you're working in. Looney GCP CDL is the name of our project. Now, if you want to access the products and services that Google Cloud has to offer, click on these three horizontal bars here, the hamburger icon, and this brings up a navigation menu. Here in the navigation menu, You can click on this little link here, view all products, and this takes you to a page where you can explore and view all of the products and services on the GCP. GCP products are categorized into various sections. For example, the management section has products and services that allow you to control costs, set up identity and access management, and set up access to various Google Cloud APIs. Now, if I were to scroll a little bit down, you can see we have the compute section. This is where I have Compute Engine, which I use to create virtual machines, Kubernetes Engine to create and manage Kubernetes clusters. There is a product named Batch that allows us to use jobs as a service, and so on and so forth. Scrolling further down, we have the storage section. These contain various products and services that have to do primarily with unstructured data. Cloud storage is object storage of unstructured data. File store gives you a fully managed NFS server, and so on. There are a whole number of products for all kinds of use cases: analytics, networking, serverless products, databases, CI CD pipelines. All of these products and services can be accessed from this page here. It does get a little bit overwhelming, but we'll explore these products in turn through this journey. Now, in the compute section, notice we have the compute engine service. This is what we use to create virtual machine instances. I'm going to go ahead and pin this so that it's available in the left sidebar. Any product or service that you plan to use often, you should pin. And then if you click on the navigation menu icon, observe that under pinned products, you can see Compute Engine. This gives you quick access to the Compute Engine service whenever you need to navigate to it. The Google Cloud offers certain services as a part of their free tier. They offer two types of free usage. There is the always free program, certain resources which can always be used for free within limits, and the 90-day free trial. The always free program allows users to utilize certain essential services like Compute Engine, cloud storage, and BigQuery within specific usage limits. The 90-day free trial gives new users $300 in credits to explore and use any GCP service. If you're logging into the Google Cloud for the first time, you likely have the 90-day free trial credits available to you. But in case you need to set up billing for your Google account, you click through to the billing option here. In order to enable billing, you use this page to create a billing account, and then you associate your credit card with that billing account. You can see I already have a billing account created called Cloud User Billing. Clicking on this billing account will show you the spends that I have in this account for the current month. This is where you can view the billing estimates for the current month, the projects that incur billing and how much billing they incur, the top services that you've used. You can see cloud storage is my most used service. I'm just going to use the back button to navigate back to the main project page. For some reason, my project got deselected, so I'm going to go ahead and reselect my project, Looney GCP CDL. I'm once again working within my selected project. Now I want to ensure that I have billing enabled for the current project. So I'm going to click through to the billing quick link that's available here. You can see that this project has no billing account, which means I cannot use resources that I need to pay for within this project. Let's go ahead and link a billing account. And since I already have a billing account created, Cloud User Billing, we saw that earlier, I'm just going to select that billing account and use that billing account for this project. That means whatever charges I incur on my current project will be billed to that billing account and will be paid using the credit card that I have associated with that billing account. I'm once again on the billing page for my project. If you ever want to head back to the home page for your project, click on this Google Cloud link and you can see that I navigate back to the home page for the project Looney GCP CDL. In a later demo, I'm going to be working with Compute Engine, which I'll use to create virtual machine instances. Products and services on the GCP have APIs associated with them, and you cannot use that product or service without enabling the corresponding API. Google makes things easy for you. It'll tell you what API you have to enable when you try to perform an action, or it'll just enable the API for you. But you can also manually enable APIs. Click on the hamburger icon, head over to the navigation menu, and click on View All Products. Observe in the very first section, the first service says APIs and services. This is where you go to manage your APIs for all Google's cloud services. So let's click through and see how we can enable the Compute Engine API, which we'll need to use if we want to create virtual machine instances. You can see in this brand new project here, I have no APIs enabled. I click on this option to enable API services, and this takes me to a search page. I can search for a specific API that I want to enable right here. And if you scroll down here, you'll find that a bunch of commonly used APIs are listed. Maybe you can find the API that you're looking for here in this list. But I find this search option very useful. I simply type in Compute Engine API, hit search, and you see that I get it as the first search result. Now, how did I know what API to enable? Well, if you head over to that product using the navigation menu, you might find a message there telling you what API to enable, or you'll find it in the documentation when you're trying to perform some kind of operation on the Google Cloud. I'm going to click through to this API and go ahead and enable it. Be taken to a page where you get documentation for this API, and you should find a big blue enable button. This indicates that the API is not enabled and you can perform the enable action. Let's say you're planning to use Compute Engine programmatically and you want to view the documentation corresponding to this API. Click on this Try this API link and you'll be directed to the documentation. Every product or service on the Google Cloud will have one or more REST APIs that it makes available that you can use to interact with that product or service. Let's go ahead and enable the Compute Engine API so that later on down the line we're able to create VM instances. Now you'll have to wait a few minutes, maybe 2 or 3 minutes, for the API to be enabled, and once it's done, we'll be able to create virtual machine instances when we need to. With that done, let's go back to our project dashboard. I click on Google Cloud, that takes me to the project homepage, and I click on dashboard, and that will take me to the project dashboard. I'll show you one last thing before we move on and play around with Cloud Shell. Notice here on the top left, we have the project info tile. If you're developing some kind of software solution within this project, you're likely doing it as a part of a team, and you'd like other members of your organization, team members, to have access to this project. You can click on Add People to this project and specify other organization members and give them specific roles within this project. For example, I've added a new principal here that is another member of my organization, Looney user at looneycon.com. And here below, I can assign a particular role for Looney user. The role determines what permissions Looney user will have on this project. This is identity and access management on the Google Cloud. Now, that's an entirely separate topic that we'll discuss in more detail later. We won't get bogged down by these permissions, but what I'm going to do is I'm going to give this user project level permissions. In fact, I'm going to make Looney user the owner of this project. Now, I've created the project. I'm already the owner of this project, which means I have full administrative access over this project. By assigning the owner role to Looney user, I'm giving Looney user full administrative privileges on this project as well. Based on the role that I've assigned Looney user has complete control and access to this project. At this point, you know how to create a new Google Cloud project. You know how to view all of the products and services available on the GCP and pin the product or service that you're likely to use over and over again so you can access it quickly. We've added a billing account to our project and also shared our project with another member of the organization. Now let's work with Cloud Shell. Now, Cloud Shell can be accessed from the top right of your screen. Cloud Shell is a terminal window right within your browser. It's an online development and operations environment accessible directly through the web browser, and it provides a command line interface with essential tools pre installed. So, all of the tools that you need to work with the GCP, you'll find that most of the tools are pre installed on Cloud Shell. If this is the first time you're accessing Cloud Shell, it might take a minute or two to come up because what Google will do is provision an ephemeral virtual machine behind the scenes and connect you to that virtual machine, giving you a terminal window right within your browser. So provisioning the Cloud Shell machine the very first time, well, that takes a bit of time. And soon enough, our Cloud Shell is available. Observe that this is just a basic Linux prompt. Now you can see a bunch of warnings here. You may not see those warnings. Those warnings exist because I've used over 90% of the storage available for Cloud Shell. Cloud Shell by default includes 5 GB of persistent disk storage, ensuring that files and configurations are saved between your different sessions. Observe that we have a command prompt where we can type in our Linux commands. Cloud Shell runs on a Linux machine. Notice also that our project ID, Looney GCP CDL, is present in brackets within the command prompt. This indicates that Cloud Shell knows that you're currently working with the Looney GCP CDL project, and any commands that you run to access or create resources from within Cloud Shell will create the resources in this project. Now, this is important. I'll explain why shortly. Rather than working with Cloud Shell using just half of the screen, what I'm going to do here is click on this icon that says Open in New Window. This will relaunch Cloud Shell in a new tab. And this is where we'll work with Cloud Shell. Observe that the command prompt is now different. It just says Cloud User at Cloud Shell and does not specify the ID of the project. This means that Cloud Shell at this point doesn't know what project you want to use to perform your operations. Before you can run any command to access Google Cloud resources from within Cloud Shell, you need to specify what project you're working within. I'll do that shortly. Now let me show you that Cloud Shell is just a simple Linux terminal. You can run the Linux command pwd and see what your present working directory is. It's /home/cloud user. Cloud user is what I've used to log into my Google Cloud account. You can run the ls-l command to list out all of the files and folders present within the current working directory. Well, I have lots of junk in here, and that's why you see all of this information. If you're running ls-l, you'll find far fewer files. Now, Cloud Shell refers to this online development and operations environment. It's also a command line utility available within Cloud Shell. Gets a little confusing, I understand. You can use the Cloud Shell utility to perform operations with Cloud Shell like downloading files, uploading files, setting up aliases, launching tutorials, and so on and so forth. Let me show you how you can actually use this Cloud Shell utility. I'm going to create a new file called secret.txt using the Nano editor. Nano is a built-in, very simple editor, always pre-installed on Linux machines. So when you call nano secret.txt, it'll create a new file called secret.txt and it'll bring up an editor that you can use to edit this file. So all I'm going to write here is this is a secret, and then I'll hit Control X. That will allow me to exit the editor. And I say, yes, I want to write to secret.txt, and then it'll quit the file, and the file will have been saved in your current working directory. If you run an ls-l now, you should find the secret.txt file in here, and you can see it there on screen. Now, Cloud Shell is available on a machine that's running on the Google Cloud platform. Now, let's say you need to access the secret.txt file on your local machine. You can use the Cloud Shell download secret.txt command. This will actually bring up a pop-up that will download this file to the machine on which you're running the browser. Go ahead and select the download action, and the file will be available on your local machine as soon as the download is complete. Secret.txt is now in my downloads folder. I'm going to show you where it is and open it up, and you can see that this is the same file. With the text, this is a secret. This is an example of how the Cloud Shell utility within Cloud Shell is useful. Now, there are other operations you can perform on Cloud Shell. Anything you can do on a Linux machine, you can do on Cloud Shell. Now, what I've done here is navigated to a URL that points to this image at unsplash.com. Let's say you wanted to access this image and make it available within your Cloud Shell terminal. You can use the wget command for this. Wget is a utility that's always installed on Linux machines by default. GNU's wget is a non-interactive network retriever, and you can use this to retrieve information over the internet. Well, I'm going to use wget to access the image from unsplash.com. So I run wget-0 mountains.jpg is the name of the file I want on my local machine, and I specify the URL at unsplash.com. Once I run this command, wget will fetch the image resource from the URL and store it in my current working directory. If you were to now run the ls-ltr command listing the contents of the current working directory, you should find the mountains.jpg file there. And of course, now that you have the file on Cloud Shell, let's say you wish to download it to your local machine, you'll run the Cloud Shell download command, specify the name of the file. This will bring up a dialog asking you to confirm the download. And if you confirm, that file will be saved to your local machine. You can see that mountains.jpg is now available in my downloads folder. And if I double click on this file, you'll see that this contains the same image of mountains that we had viewed on Unsplash. Now, let's say you're working with the Google Cloud and you want to interact with resources using some kind of CLI, like a command line interface. Well, one way to do it is to download the Google Cloud SDK onto your local machine and set up the command line tools. But another easier way is to simply use Cloud Shell. Cloud Shell comes pre-installed with many tools that you'll use to interact with the Google Cloud. These include tools that are part of the Google Cloud SDK, open source tools such as Maven, and programming languages such as Java and Python. Now, gcloud is the command line interface that you'll use to interact with the Google Cloud Platform services. gcloud allows users to manage GCP resources, deploy applications, and configure settings directly from the terminal window. All cloud platforms such as Azure and AWS offer fully functional CLIs to work with the platform's resources, and gcloud is Google's CLI. I'm going to run gcloud --help, and you'll see that gcloud is already available, and help shows me all of the different ways in which I can use gcloud. Now, let's say I want to view a list of projects that's available to my current logged in account. I can run gcloud projects list, and it will list all of the projects that we saw via the Cloud Console, that is the web interface, but now you see this within the terminal window. You can also set up some default settings for the gcloud command line tool. The command gcloud config list displays the current configuration settings for the gcloud command line tool. This includes information such as the active project, the default compute zone, and other settings that have been configured for the Google Cloud SDK environment. Observe that we have no current project set. None of the commands that we ran so far required an active project because the commands did not really work with GCP resources or services. Now, if you want to be able to set an active project, the project that you're going to be working with, you can use this gcloud config set project command. Specify the ID of the project. Ours is Looney GCP CDL, and this will set the active project within Cloud Shell to be the project that we had specified. Notice how the command prompt has changed to reflect the current active project. What this gcloud config set project command does is it sets an environment variable within this Linux terminal. The environment variable Google Cloud Project is set to your current active project. So when you run a command using the gcloud command line tool, gcloud checks this environment variable to see what project it should use to provision resources, delete or update resources based on what your command does. Now, if you look at gcloud config list, an active project should be set. Notice under the core section, we have project set to Looney GCP CDL. Now, there are other command line utilities that are available as a part of the Google Cloud SDK. One of those utilities is BQ, which is the command line tool that you can use to interact with BigQuery, Google's data warehousing solution. As you can see, BQ also comes pre-installed on Cloud Shell. BQ allows you to create BigQuery datasets and tables, upload data, query the data that exists within your tables, all kinds of operations on the data warehouse. Another tool that's part of Google Cloud's SDK is GSUtil, which is a command line tool for interacting with Google Cloud Storage, a service within the GCP designed for scalable and secure object storage. GSUtil also is pre-installed on Cloud Shell. So you can see it's very useful to be able to work on the command line with Cloud Shell. You do not have to download the Google Cloud SDK or perform a bunch of setup operations. Cloud Shell is more than just a terminal available within your browser. Cloud Shell comes with a built-in code editor that allows you to browse file directories and view and edit files with continued access to Cloud Shell. The Cloud Shell editor is available by default with every Cloud Shell instance and is based on CodeOSS. In order to open up the Cloud Shell editor, simply click on this pencil icon, the edit icon, to open up the editor. If you click on this, you can see that the terminal window is minimized and the editor opens up. If you want to work on the editor full screen, you can simply choose to close the Cloud Shell terminal. And here is the Cloud Shell editor. The Cloud Shell editor provides a feature-rich environment for coding directly in the browser. It includes support for multiple programming languages, syntax highlighting, code completion, and debugging tools. If you open up your home directory within the Cloud Shell editor, this will give you a graphical UI to view the files that you have in your home directory. So you can see I have hundreds of files here. I can view them all within the Cloud Shell editor. Let me show you how you can quickly prototype and write code in different programming languages using the Cloud Shell editor. What I'm going to do first is create a new subfolder within my Cloud Shell home directory. I click on this little plus icon and I name the subfolder sample folder. Let me prove to you that this folder is actually created within our home directory. I'm going to click on this option to open terminal. This will switch over to the Cloud Shell terminal. Let's run an ls-l command and you should find the sample folder here. The default Cloud Shell is a command line view. The editor is just a UI view of the same Cloud Shell terminal. Now let's go back to our Cloud Shell editor and I'm going to right click on sample folder and create a new file. Let's make this a Java file. I'm going to call it Fibonacci.java and here I'm going to write a little program in Java to generate Fibonacci numbers. Notice that Cloud Shell has figured out that this is a Java file and it sets up syntax highlighting accordingly. If you don't know any Java, that's totally fine. You're not expected to, but you can see that the Cloud Shell editor identifies Java. You can see at the bottom right, the code says Java. The Fibonacci sequence is just a series of numbers in which each number is the sum of the previous two numbers, and this is a common beginner problem in programming. Now let's say you want to run this Java code. You can actually bring up the Cloud Shell terminal right within the editor. Click on the three horizontal bars here, select the terminal option and select New Terminal. Integrated development environments often have built-in terminals and the Cloud Shell editor is no different. The terminal window opens up right within our editor. We are in our home directory. Let's cd into the sample folder. And here in the sample folder, if you run an ls-l command to list the contents of this folder, you should be able to see the Fibonacci.java file. In order to be able to run Java code, you need to have Java installed. Run java -- version and you'll find that Java is pre-installed on the Cloud Shell terminal. At the time of this recording, the version of Java available is JDK 17. If we have Java available, we should be able to compile and run this program. Let's run javac Fibonacci.java. This creates a compiled version of the original Java code. The compiled version is just something that Java can execute. If you run ls-l, you should see a .class file that is the compiled version of the original source code. Let's call Java Fibonacci and this will execute the .class file and you should see the first 10 terms of the Fibonacci sequence printed out to screen. I just wanted to use this example to show you that the Cloud Shell editor comes with built-in support for programming languages such as Java. Cloud Shell doesn't just support Java. In the Cloud Shell editor, you can work with other programming languages such as Python. Let's open up this left navigation pane and there we have our sample folder. I'm going to select it, right click and select new file once again. Now this new file that I'm going to create is going to be a Python source file, average.py, to compute the average of some numbers. Observe that Cloud Shell identifies this correctly as a Python file. I'm going to write a very simple piece of Python code here in this file. I've defined a function called average. This takes in a list of numbers and finds the average of that list. And I print the average of the numbers 1, 2, 3, 4, 5 out to screen. If the code makes absolutely no sense, don't worry about it. This is just Python code and I want to show you that Cloud Shell has Python installed and you can run Python programs from within Cloud Shell. Here I am with the terminal window open. If you run Python -- version, you'll see that a new version of Python, Python 3.10.12, is already installed on Cloud Shell. And we can use this to run this code that we have here in average.py. Python average.py will print out the average of 1, 2, 3, 4, 5, which is just 3. Cloud Shell also supports the JavaScript programming language, another popular programming language used today. Now, within the sample folder, I'm going to create a new JavaScript file called circle.js, and I'll write some very simple JavaScript code in here to compute the area and the circumference of a circle. Here is some very simple code in JavaScript. Again, nothing that you need to understand. You can see the console.log statements here at the bottom. That's what we use to log or print out the circle's circumference and area. Now I'm going to run this JavaScript file using Node.js. JavaScript is usually run within a web browser. Node.js is a runtime environment that allows you to execute JavaScript code outside of a web browser. Now I run node dash dash version to prove to you that Cloud Shell comes pre-installed with Node.js. This is a recent version of Node, version 20.13.0. Let's run circle.js using Node. I simply call Node and pass in circle.js, and the circumference and area of the circle should be printed out to screen. Why am I showing you this? Why is this useful? If you're developing on the Google Cloud, let's say as a developer, you quickly need to write up some code, whether it's in Java, Python, JavaScript, or some other language, you can use the Cloud Shell editor for quick prototyping. The Cloud Shell editor is not really meant for full scale projects, but it's a great resource for rapid prototyping, and it's integrated with Google Cloud services and products. In your daily job, if you're working with developers and other technologists, you should be aware of how you can use the Cloud Shell editor for prototyping in various languages. Now, let me go ahead and close the Cloud Shell editor. This should take us back to the Cloud Shell terminal. I'm going to open up the Cloud Shell terminal before we conclude this demo. Hopefully, this demo has given you an idea of how developers and administrators on the Google Cloud platform can use Cloud Shell. This brings us to the very end of this course on introducing Google Cloud concepts. We started this course off by introducing Google Cloud and its various services, including compute, storage, networking, AI, big data, and other essential offerings. This introduction provided us with an overview of the vast capabilities and functionalities available within the Google Cloud, setting the stage for deeper exploration and understanding of its ecosystem. Next, we learned about the shared responsibility model on the cloud, highlighting the division of responsibilities between cloud providers and customers. We also examined the total cost of ownership, helping us understand the financial implications of cloud adoption. We learned global infrastructure concepts and terminology, gaining insights into how Google Cloud's infrastructure is designed and operated. Additionally, we got an overview of the Google Cloud Adoption Framework, which provides a structured approach to adopting Google Cloud effectively. Finally, we explored fundamental Google Cloud concepts and the resource hierarchy within the platform. We created a project on the Google Cloud, viewed and assessed various products and services, and became familiar with Cloud Shell and the Cloud Shell editor. These hands on activities allowed us to apply our theoretical knowledge in practical scenarios, enhancing our understanding of how to navigate and utilize Google Cloud's tools and services effectively. In conclusion, we have built a solid foundation in Google Cloud by understanding its core services, learning about the shared responsibility model, cost implications, and infrastructure, and exploring practical tools and resources. We are now ready to tackle the next course in this learning journey: Compute on the Google Cloud. Hi, my name is Janani Ravi, and welcome to this course on Compute on the Google Cloud. Google Cloud's compute capabilities provide robust tools for optimizing performance and cost with flexible configurations and advanced management features. In this course, you learn about the compute capabilities of Google Cloud, focusing on specifics of compute engine configuration. You will explore various options and settings to optimize performance and cost, gaining a comprehensive understanding of managing compute resources within Google Cloud. Next, you will navigate to the Google Compute Engine page to create instances, configure regions, zones, and machine types. You will complete VM configurations by specifying the boot disk, setting up service accounts, and viewing networking management and other options. You will also practice connecting to VMs using SSH for effective management and interaction. Finally, you will use the gcloud command line tool to manage instances. You will run a simple website on a VM, configure startup scripts, and create snapshots. These hands-on activities will provide you with practical experience needed to effectively manage and deploy applications on Google. In this video, we'll discuss the range of compute choices that you have available on the Google Cloud, and you'll see that a similar spectrum of compute choices are available across all cloud platforms. We'll then compare and contrast bare metal solutions and virtual machines and understand how they're different. Now, across all cloud platforms, compute choices lie along a spectrum. You can see the spectrum here: bare metal, virtual machine instances, container clusters, hosted applications, and serverless functions. Let me quickly define each of these. Bare metal solutions are when you have direct access to the physical hardware on which you're running your software. With bare metal, you're actually dealing with the CPUs of the machine and memory. Virtual machine instances offer a layer of abstraction over the physical hardware. The same physical machine can host multiple virtual machines. You're dealing with virtualized CPUs rather than actual CPUs. Container clusters are a distributed environment where you have a number of servers, but you run your applications in isolated packages called containers. Hosted applications are when you do not deal with the underlying infrastructure at all. This is a platform as a service offering. You only write code for your applications and leave the infrastructure management to Google or the cloud provider. And finally, we have serverless functions. This is another platform as a service offering where all you have to do as a user is write code to deal with external events. As soon as the event occurs, your code runs. You do not provision infrastructure or do any other management. It's pretty clear from these explanations that as you move from the left to the right in the spectrum, you depend more on the platform, that is, the cloud provider. You're moving from infra as a service offerings to platform as a service offerings. In return, you have less operational and administrative overhead. There is less infrastructure management and configuration that you have to do. As you move from the right to the left of the spectrum, you get more control over how your software solution runs. You have granular access, but in return, you have a greater administrative overhead. For example, at the extreme left for bare metal solutions, you have to install the operating system, the network drivers, and everything else that you need to host your app. The two ends of the spectrum can be thought of as infra as a service offerings and platform as a service offerings, and we've already studied these in detail. Bare metal is not technically part of infra as a service because there you're directly dealing with the physical hardware. But you get the overall picture. Towards the left, we have infra as a service, towards the right, platform as a service. We won't discuss bare metal offerings from Google right now. We'll discuss that later on in this journey. That's a more advanced topic. But let's discuss the other four solutions: compute services for VM instances, container clusters, hosted applications, and serverless functions. These are the Google services for infra as a service through platform as a service. Google Compute Engine allows you to create and manage virtual machine instances. Google Kubernetes Engine allows you to run container clusters using Kubernetes as an orchestrator. Compute Engine and Kubernetes Engine can be thought of as infra as a service offerings. Google App Engine, Cloud Run, and Cloud Functions are platform as a service offerings. App Engine allows you to run hosted applications on the Google Cloud, where you write the code for the app but don't manage infrastructure. Cloud Run allows you to run containers in a serverless manner. You package your code into containers, but you do not have to set up a cluster for those containers to run. Cloud Run is serverless, which means that the infrastructure is automatically managed by Google. And Google Cloud Functions give you event driven serverless compute. You simply write the code for a function to handle a particular event and deploy it with a few clicks. You'll find that all cloud platforms offer similar services along the spectrum. For example, if you were to work on AWS, Amazon EC2 allows you to provision virtual machines. Amazon Elastic Kubernetes Service, or EKS, allows you to set up Kubernetes clusters. Elastic Beanstalk is for hosted applications. Fargate is for serverless containers. And Lambdas are for serverless functions. And you'll find the same compute choices on Azure as well. You'll use the Azure VM service to create and provision virtual machines, Azure Kubernetes service to work with Kubernetes clusters, Azure App Service to create and deploy hosted applications with no infrastructure management, Azure Container Instances to run containers in a serverless fashion, and Azure Functions to write functions that respond to events. The basic spectrum of compute choices that Google offers are available on other cloud platforms as well. We've already discussed zones and regions before. Let's just refresh our memory. A zone is an isolated location within a region. A region is made up of multiple zones that are connected using high speed network links. Regions and zones are both abstractions over the resources that are provided across Google's data centers. Google zones and regions are named in a very specific manner. For example, there is a zone located in Mumbai, India, and that zone is Asia South 1A. Now, the name of the corresponding region is Asia South 1, and there are multiple zones within the Asia South 1 region. A, B, and C are the suffixes of the zones. When you provision resources on the Google Cloud, resources such as virtual machine instances, they have to live on a network so that they can communicate with one another. A network on the GCP is a global resource. It's not tied to any region or zone. Once you have a network, you can set up your own user controlled IP addresses, subnets, and firewall rules. Subnets are just logical partitions of the network. When you first set up a Google Cloud project, what Google does is behind the scenes, it automatically sets up a network for you. This network is called default network. The default network is created and provisioned so that when you actually provision your resources like VM instances, you do not have to worry about networking unless you want to. It's possible for you to go ahead and provision other networks that you need. If you don't want to think about networking, the default network is available. In the demos that will come up shortly, we'll work with virtual machines on the Google Cloud. These are Google Compute Engine instances. These are just VMs hosted on Google's infrastructure. So the terms compute engine instance, virtual machine instance, VM instance, and VM are all synonymous. Virtual machines are zonal resources. They are created and provisioned within a zone. I've briefly explained the terms bare metal and virtual machine. Let's now understand the difference between the two, starting with bare metal. Bare metal refers to physical servers that run applications directly on top of the operating system without any virtualization layer. This setup allows applications to fully utilize the hardware's resources, often resulting in improved performance and reduced latency compared to virtualized environments. In a bare metal configuration, the operating system is installed directly on the server's hardware and you get direct access to CPU, memory, storage, and network resources. Bare metal tends to be very beneficial for high performance computing, database workloads, and other applications that require maximum performance and low overhead. With bare metal, your applications run directly on top of the OS, which means they become intimately tied with the underlying operating system and may end up being less portable. Also, it's unlikely that your application can fully utilize all of the resources that the bare metal offers, which is why there's likely to be a lot of wasted space because of underutilization. Virtual machines are not actual machines, they are software based emulations of physical computers running an operating system and applications just like a physical server. Unlike bare metal, VMs operate on a virtualization layer called a hypervisor, which abstracts the underlying hardware and allows multiple VMs to run on a single physical server. Observe here that we have a host operating system, a hypervisor, and then each virtual machine has its own guest OS. And your application runs within the virtual machine. Because the same physical server is used by multiple virtual machines, there tends to be less wastage of resources. However, VMs may have a slightly reduced performance compared to bare metal due to the overhead introduced by the hypervisor. Let's compare and contrast bare metal versus virtual machines based on a variety of features, starting with performance. Bare metal typically offers higher performance with direct access to hardware resources. Apps running on virtual machines might see slightly lower performance due to the hypervisor overhead. Bare metal offers dedicated resources to every application running on the machine. There is no sharing of resources. With virtual machines, the resources are shared amongst multiple VMs on a single physical server. Bare metal does not offer scaling or automated scaling because you're limited to physical hardware capabilities. Scaling requires adding more servers. VMs tend to be highly scalable, they are easy to create, clone, and manage. VMs use dynamic resource allocation. In terms of flexibility, bare metal tends to be less flexible because hardware and configurations are fixed once you set up your server. VMs are more flexible. You can easily change resource allocations and configurations for virtual machines. You'll have to deal with a higher management overhead if you're working on bare metal due to physical hardware maintenance and operating system management. That's on you. With virtual machines, your management overhead is lower. You have access to centralized VM management tools and automated provisioning. And finally, with bare metal solutions, your speed of deployment tends to be slower because this involves setting up physical servers. With virtual machines, you get faster deployment. New virtual machines can be spun up very quickly. In the previous video, we were introduced to the compute choices available on the Google Cloud, and we discussed that Google Compute Engine allows us to create virtual machines. We also understood the difference between bare metal and VMs. In this video, we'll discuss Google Compute Engine in more detail, and we'll discuss some of the configuration choices that you have when you provision a virtual machine on the Google Cloud. First, some VM terminology for Google. Virtual machines on the Google Cloud belong to machine families. A machine family is a curated set of processor and hardware configurations optimized for specific workloads on Google. When creating a virtual machine, you select a predefined or custom machine type from your preferred machine family. Each machine family is designed to cater to specific types of workloads, such as general purpose computing, memory intensive tasks, or compute intensive operations. Once you've picked your machine family, you can choose from different machine series. Machine families are further classified into machine series and generations. For instance, the N1 series within the general purpose machine family is an older version compared to the N2 series. A higher series or generation number typically indicates newer CPU platforms or technologies. Newer series often leverage the latest advancements in CPU architecture, providing better performance, efficiency, and features. Within every machine series, you can choose your machine type. Each machine series includes predefined machine types that specify a set of resources for your virtual machine, such as CPU, memory, and storage. If a predefined machine type does not meet your needs, you can create a custom machine type in some machine series. Virtual machines on the Google Cloud can support different kinds of workloads, and you pick the machine family for the kind of workload that you want to run. Let's say you want to run a general purpose workload. A general purpose workload is any software solution that you wish to deploy on a virtual machine which does not have special requirements for compute or memory. The machine series that you might choose for a general purpose workload could be the N series N4, N2, N2D, N1. These give you a balanced price performance ratio across a range of machine types. The N4 series is, of course, the newest generation at the time of this recording. For general purpose workloads, you also have the C3, C3D machine series, which offers consistently high performance for a variety of workloads. If you were to pick the E2 series of machines, this works very well for day to day computing at a lower cost. These tend to be the most inexpensive of all general purpose machines. There are general purpose machines available on specialized ARM architectures as well. The Tau T2A machine series is the first machine series in Google Cloud to run on ARM processors. Tau T2A machines are optimized to deliver compelling price for performance, and they're meant for scale out workloads. Let's say you're not running a general purpose workload, but something that's more specialized. There are machine families available for optimized workloads as well. The storage optimized machine family is ideal for horizontal scale out databases, log analytics, data warehouse offerings, and other database workloads. This offers the highest block storage to compute ratios for storage intensive workloads. Then you have compute optimized machine family. Compute optimized machines offer ultra high performance for compute intensive workloads. These are ideal for compute intensive and high performance computing workloads. They offer the highest performance per core and are built on architecture that utilizes features like non uniform memory access for optimal, reliable, uniform performance. Machines in the memory optimized category are ideal for online analytical processing and online transaction processing workloads. They work well for genomic modeling, electronic design automation, and your most memory intensive high performance computing workloads. This family offers more memory per core than any other machine family. They have the highest memory to compute ratios for memory intensive workloads. And finally, you have virtual machines that include accelerators or GPUs. This family is ideal for massively parallelized training of AI models, machine learning, high performance computing, and so on. This is the optimal choice for workloads that require GPUs. Once you've picked your machine family based on the kind of workload that you're running, general purpose or optimized, and you've picked the machine series you want to go with, let's say you're going with the latest series, you have to select your machine type. Now, machine types on Google can be of two types: predefined or custom. Predefined machine types are configurations that Google has already set up behind the scenes. These are a fixed set of types with fixed ratio of memory to vCPU count. These are configurations that have already been created, and when you use these predefined types, you become eligible for committed and sustained use discounts on your virtual machines. It's recommended that you go with one of the predefined machine types if you can. But sometimes you might be running a specialized workload and you need to go with a custom machine type. In a custom machine type, you can independently configure the number of virtual CPUs you want on your machine and the amount of memory. You'll configure these based on your specialized needs. When you configure and set up your virtual machine, you'll specify some block storage to go with your VM. Block storage just refers to the hard disk connected to your VM, boot disks, and additional disks. This kind of disk storage is referred to as block storage because data is split into and stored in fixed size blocks. Google offers several block storage options. These include persistent disks, Google Cloud Hyperdisk, hyperdisk storage pools, and local SSD disks. Let's discuss each of these. Persistent disk volumes are durable network storage devices that your virtual machine can access like physical disks in a desktop or a server. The data on each persistent disk is distributed across several physical disks. Compute Engine manages the physical disks and the data distribution for you to ensure redundancy and optimal performance. Google offers different kinds of persistent disks. Standard persistent disks are suitable for large data processing workloads that primarily use sequential input output operations. These are backed by a standard hard disk drive. A balanced persistent disk gives you a good balance of performance and cost. This type typically offers performance levels suitable for most general purpose applications. These are backed by solid state drives, so they tend to have better performance than standard persistent disks. Google also offers performance persistent disks. These are suitable for enterprise applications and high performance databases that require lower latency and more input output operations than standard persistent disks provide. These are also backed by solid state drives. Google Cloud also has extreme persistent disks, which offer consistently high performance for both random access workloads and bulk throughput. They're designed for high end database workloads and they're backed by solid state drives. Persistent disks fall into two broad categories: zonal or regional. Zonal persistent disks are attached to virtual machines within a single zone. Because they are confined to a single zone, they are vulnerable to zone wide outages. If the zone becomes unavailable, the data on the disk will also be inaccessible. These are ideal for applications that do not require high availability across multiple zones and where cost efficiency and performance within a single zone are prioritized. You also have regional persistent disks. These are designed to provide higher availability and redundancy by replicating data between two zones within the same region. If one zone experiences an outage, the data remains accessible from the other zone. This improves fault tolerance and data reliability. These are preferred for mission critical applications that require continuous availability and can benefit from automatic failover capabilities. Google Cloud Hyperdisk is Google's next generation block storage. By offloading and dynamically scaling out storage processing, it decouples storage performance from the virtual machine type and size. Hyperdisk offers substantially higher performance, flexibility, and efficiency. Hyperdisk storage pools make it easier to lower your block storage total cost of ownership and simplify block storage management. With hyperdisk storage pools, you share a pool of provisioned resources across a maximum of 1,000 disks in a single project. You first create a storage pool with the estimated capacity for all workloads in a project in a specific zone. You then create disks in the storage pool and attach the disks to existing VMs. Local SSDs are different from all of the other block storage options that we have discussed so far because these are disks that are physically attached to the server that hosts your virtual machine. All of the other persistent disks are attached to the same network in the same zone as your virtual machine's server. But the local SSD has a direct connection with your virtual machine. These are great to be used as scratch disks or caches. The data that you store on a local SSD is ephemeral in that it only persists until the VM is stopped or deleted. They have higher throughput and lower latency than standard persistent disks or solid state drive persistent disks. While we are discussing block storage, I'd like to briefly introduce and discuss cloud storage buckets. Cloud storage buckets are scalable storage containers in the cloud designed to hold and organize data such as files, images, and backups, and these are accessible over the internet. Cloud storage buckets are examples of object storage, that is, they store blobs of data, where a blob is a binary large object. These are the most flexible, scalable, and durable storage option for your virtual machines. If your applications don't require the lower latency of persistent disks and local SSDs, you can store your data in a cloud storage bucket. Cloud storage buckets offer infinitely scaled storage. Let's quickly compare and contrast persistent disks with buckets. Persistent disks are examples of block storage, where the data is broken down into fixed size blocks and stored on disks. Buckets are examples of object storage, where data is stored in binary form and data usually comprises of very large objects. Persistent disks do not offer you unlimited storage. When you provision a persistent disk, you specify the size of the disk and you cannot store data larger than the capacity of the persistent disk. Buckets, on the other hand, cloud storage buckets are infinitely scalable. You just upload as much data as you need to, and the storage is just available for all your data. For persistent disks, you pay what you allocate. If you provision a 500 GB persistent disk and only store about 10 GB of data, you have to pay for the entire 500 GB. On the other hand, cloud storage buckets follow the pay what you use model. If you store 10 GB of data in a cloud storage bucket, you only pay for the 10 GB of data that you've stored. Persistent disks are intimately tied to Google Compute Engine virtual machines. You typically do not use a persistent disk as a standalone store of data. You use persistent disks by attaching them to virtual machines, and applications running on the VMs use the persistent disks. Cloud storage buckets, on the other hand, are completely independent of Google Compute Engine VMs. In fact, they're their own Google service and not tied to any other product or service on the Google Cloud. Persistent disks are zonal or regional resources, which means they can only be accessed by other resources in the same zone or region. Buckets, on the other hand, can be accessed by resources anywhere around the globe. Global, regional, and zonal access here refers to access by other resources on the Google Cloud and not by users. All resources are always accessible by users, provided they have the right permissions. Before we move on to some hands on implementation using Google Compute Engine, we'll create and provision VM instances very soon. Let's understand a few more compute engine concepts. Starting with machine images. Machine images or images are static copies of a virtual machine's disk, including its operating system, installed applications, and configurations. This resource stores all the configuration metadata, permissions, and data from multiple disks of a virtual machine instance. You can use a machine image in many system maintenance, backup, and recovery and instance cloning scenarios. Images are used to create new VM instances quickly, ensuring consistency and uniformity across deployments. Users can also create custom images tailored to specific needs or use publicly available images provided by Google. Images are divided into two broad categories: public images and custom images. Public images are available to anyone using the Google Cloud. These tend to be provided and maintained by either Google, open source communities, or third party vendors. There are no restrictions on accessing public images. All projects on Google have access to these images and can use these images to create instances. Examples of public images include images for the Linux operating system, the Windows Server operating system. There is a container optimized operating system image which allows you to run container clusters. There's also an image which you can use to install the SQL Server database on your VM. Linux is an example of an image maintained by a public community. It's an open source image. Windows Server is an example of an image maintained by a third party, Microsoft. Custom images are images that are only available to your project. Custom images are images that you or other users in your project might create. Let's say you set up your operating system within a VM and then you install a bunch of software and you want all of this to be captured as a static image. You can create an image using your VM instance and then share that image with other team members who are working on the same project and allow them to use that image to create virtual machine instances. Another important term that you should know of when you're working with virtual machines is a snapshot. Snapshots on the Google Cloud are point in time copies of persistent disks. They capture the state of a disk at a specific moment, allowing users to back up data and restore data as needed. Snapshots are incremental after the first snapshot, meaning only changes since the last snapshot are saved, which optimizes storage usage and reduces costs. The lifecycle of a snapshot created from a disk attached to a running VM instance is independent of the lifecycle of the VM instance. Snapshots are primarily meant for data protection. They provide a reliable way to back up and restore data, protecting against data loss. Snapshots of a boot disk of a virtual machine can be used to create other virtual machine instances. The Google Cloud also offers something known as sole tenant nodes. These are dedicated physical servers specifically assigned to a single customer. Sole tenant nodes offer physical isolation by allocating entire servers to a single customer. This means that your workloads are the only ones running on that hardware, eliminating the risks associated with multi tenancy. When you use sole tenant nodes, you're not sharing resources on the physical hardware with other customers. So, no other customers' workloads will be hosted on the same physical hardware. This ensures better security and privacy for your data and applications. For normal virtual machines, the servers that hold your virtual machines can host virtual machines from other customers and other organizations. Not so in the case of sole tenant nodes. Sole tenant nodes can help meet compliance and regulatory requirements. They are ideal for organizations that need to comply with strict data residency, security, and compliance regulations such as HIPAA and GDPR. If your application is very performance sensitive, you might choose to use a sole tenant node. They're suitable for applications that require consistent high performance computing resources without interference from other tenants, that is, other customers. Sole tenant nodes are also beneficial for enterprises with specific licensing requirements that mandate the use of dedicated hardware. Sole tenant nodes also help with data isolation. They provide an additional layer of data isolation, enhancing security for sensitive or confidential data. Google Compute Engine also offers a special type of virtual machine called Spot VMs. These are preemptible virtual machine instances that offer significant cost savings by utilizing unused compute capacity. Typically, when you provision a virtual machine, that is a dedicated virtual machine. That is, that machine will be available to you so long as you choose to have it. The machine only goes away when you explicitly stop and decommission the machine. A major advantage of Spot VMs is that they are available to you at a much lower cost than dedicated virtual machines. Google Cloud treats the Spot virtual machine a little differently. These VMs can be terminated by Google at any time if resources are needed elsewhere, making them ideal for fault tolerant and flexible workloads. If you're going to be hosting your website in a single virtual machine, you are not going to choose a Spot VM. That's because if the machine goes away, your website will be unavailable. But Spot VMs are great when you want to use it as a part of a distributed cluster setup. Even if the Spot VM is preempted or terminated, the remaining machines of the cluster will be available for your processing. Spot VMs are great for batch processing and data analysis. They are perfect for running large scale batch processing jobs or data analysis tasks that can be paused and resumed without significant impact. Continuous integration and continuous deployment CI/CD tasks can leverage Spot VMs to perform builds and tests at a lower cost, reducing the overall expense of development operations. Applications that are designed to be stateless can take advantage of Spot VMs for handling fluctuating workloads. Applications such as websites and containerized applications managed by Kubernetes. Big data processing frameworks like Apache Hadoop and Spark, as well as machine learning training tasks, can effectively use Spot VMs to manage large data sets and compute intensive operations at a lower cost. Google offers additional security for your virtual machines using shielded VMs. These provide enhanced security features to protect virtual machines from rootkits, bootkits, and other advanced persistent threats. They include features like Secure Boot, Virtual Trusted Platform Module or VTPM, and integrity monitoring to ensure that the VM's firmware and bootloader are not tampered with. Shielded VMs mitigate and prevent unauthorized changes and provide continuous monitoring and verification of your VMs. If you require additional security to safeguard sensitive applications and data in the cloud, you may want to use shielded VMs. Google also offers confidential VMs. These are designed to provide advanced security and privacy for your workloads by encrypting data in use. Confidential VMs ensure that the data processed within the VM is encrypted, protecting it from unauthorized access, even from Google's infrastructure administrators. So, when you run your workloads in the cloud, you have the assurance that your data is private and secure. Confidential VMs are useful for industries with stringent data security requirements such as finance, healthcare, and government. At this point, you've explored some of the basic functionality that the Google Cloud has to offer. You've created projects, you've played around with Cloud Shell, and you've also seen how the Cloud Shell editor works. Let's get started using some of Google's services, and we'll start with the most foundational of all services, Google Compute Engine. I'm going to head over to the navigation menu, and if you remember, earlier in this journey, I had pinned Google Compute Engine to my navigation menu. As you hover over Compute Engine, it brings up a larger submenu. That's because Google Compute Engine has many different subcategories of services. If you just click on Compute Engine, you'll be taken to the VM instances page. VM here is a virtual machine. Google Compute Engine is the Infra as a Service IaaS offering from the Google Cloud Platform that allows users to run virtual machines or VMs on Google's infrastructure. Now, the most important and the most often used feature on Google Compute Engine is virtual machines, but there are other features that you can access. Observe all of the options here on the left navigation menu. Under virtual machines, you have VM instances, instance templates. I haven't really discussed those yet. We'll do that later on in this journey. It's just a way to set up the configuration options for your virtual machine in the form of a template and then use that template to create virtual machines as you need. We've discussed sole tenant nodes, where your virtual machines are hosted on isolated hardware. We've discussed machine images, the software, usually the operating system that you install on your virtual machine, and there are many more options here. If you scroll down here, you should see a category for storage. Here is where you can view the persistent disks that you have created, any storage pools that you've set up, the snapshots that you've used to back up your persistent disks, any custom images that you've created, and many other options. We don't really need to discuss or worry about them now. As a beginner on the Google Cloud, you're not really expected to know all of these for the Cloud Digital Leader exam. Let's provision our very first virtual machine and we'll be able to explore some of the options that Google Cloud offers for VMs. Click on Create Instance. This will take you to a page that will walk you through the creation of your VM. Now, the first thing I'm going to show you here is compute engine pricing. We've discussed the fact that there are different machine types and images that you can use for your VM. Let's take a look at how these are priced. Compute engine pricing. This is a page where you can view the pricing for all kinds of VMs and configurations. You can scroll over on the left and see all of the options. Let's say you want to view the pricing details for general purpose machine types. Click on the general purpose machine types link off to the left, and this will give you the pricing details. General purpose machines, provide a balanced mix of compute, memory, and networking resources, making them suitable for a wide variety of workloads. Within the general purpose category, there are several series of machines, and you get pricing for each series. What you see here on screen is the pricing for N4 machine types if you were to provision the VM in Singapore, in the region Asia Southeast 1. Notice that there is a little toggle off to the top right where you can view pricing hourly or monthly. Observe that you get pricing breakdown for virtual CPUs and for the memory that you want to provision in your VM. There are on demand prices, which tend to be the highest overall. Commitment based prices tend to be lower, where you commit to using a VM for a certain number of months or for a certain number of years. And there is a 1 year and 3 year flexible CUD consumption rate. CUD here refers to committed use discount, which allows you to commit to a certain amount of resource usage or spend for 1 year in exchange for a discount. So you can see that pricing, even for VMs, can get fairly complex. So if you provide an upfront commitment for number of months or for resource usage, you can get heavy discounts, allowing you to save a lot of money. Let's close the pricing page and head back to our page here, which will allow us to create a virtual machine instance. Let's walk through this step by step. The first thing that you need to do is to specify a name for your instance. Your virtual machine instance name need not be globally unique, but it has to be unique within your project. Now I've called my instance instance01, and this is an acceptable name. However, VM names do have certain limitations. If you were to try and use the uppercase I to name your VM, that is, the first letter is an uppercase letter, you'll find that you'll encounter an error. Here you can see the rules for virtual machine naming. Name must consist of lowercase letters, numbers, and hyphens. Name must start with a lowercase letter. So let's rename it to instance1 with the lowercase I. If you're unsure about a particular configuration property, hover over the question mark and you'll get additional information. Now, the next thing that you need to specify is the region where you want to provision your virtual machine and the zone where you want the VM to be located. Once you specify the region and the zone, you cannot change these. By default, the region chosen is US Central 1 in Iowa, but this is something that you can change while you're creating the instance. You can simply use the drop down here to specify the region where you want your instance to be provisioned. Any region which has good energy efficiency is clearly marked as low CO2. Before I select a different region, let me highlight the monthly estimate of the cost for the VM that we are provisioning using all the current default settings. On the top right, you can see that it costs about $24.86. This estimate is based on your current selection. So let's say you were to choose a different region, US South 1 Dallas. As soon as you make the selection, notice that the monthly estimate changes and it's more expensive to provision a VM here. It costs $29.33. The cost of your VM depends on where it's located. Now you can see in the zone option, zone is set to any by default. This means the virtual machine can be provisioned in any of the zones in the region US South 1. Zones usually have an alphabet as a suffix, US South 1 A, B, and C. And like I mentioned earlier, Google usually ensures that every region has at least 3 zones. Some regions have more. Let's try this once again. Let's change the region where we want to provision our instance to somewhere in Europe, Europe Southwest 1 Madrid. Observe the cost is still about $29, and you can see the 3 zones for this particular region, A, B, and C. You can try out a few different regions and see how the cost changes. Let me switch over to Asia East 2, that's located in Hong Kong. Now, this is an expensive region. If you look at the monthly estimate, it's $34.72 to run a VM with the same configuration as before in this region. I'll leave it to you to explore all of these different regions and their zones on your own. Let's go back and provision our instance in US Central 1. This is a large region and has good capacity. Observe that this particular region has 4 zones instead of 3, and it's also pretty cost effective. I'm going to go ahead and select a particular zone, let's say zone US Central 1A, and we've set our region and zone, and we're ready to move on to other configuration options. Before we move on to the next step in the configuration, let me just expand the details here of this monthly estimate so that you can see what you're paying for. The default configuration for the VM is 2 vCPUs and 4 GB of memory, and that costs $24.46. And then there is a 10 GB standard persistent disk that's attached to the VM, and that costs 40 cents a month to give you a total of $24.86. Now, the next step here is the machine configuration. What kind of machine do you want to provision? Do you want a general purpose machine, a compute optimized machine, memory optimized machine, a storage optimized machine, or a machine that runs GPUs? General purpose is selected by default, and you can see all of the machine series available under the general purpose category. What I really like here is that you get a quick description and overview for each machine series. For example, the E2 series is best for low cost and day-to-day computing. The vCPU range is 0.25 to 32, so it supports fractional vCPUs as well. Memory is 1 to 28 GB, and what platform you get is based on availability. And like this, we have descriptions for every series. The E2 series is a low cost one. Let's say you were to change the machine series you want to instantiate for your general purpose machine. Well, if you were to switch to N4, notice the monthly estimate goes up to $91. If you were to go with the C3 machine series for consistently high performance, notice that's about $175 per month. So based on what kind of general purpose workload you want to support, you can pick the right series for you. Make sure it fits within your budget. I'm going to stick with the E2 series. This is the lowest cost after all. Now, compute optimized machines allow you to run compute optimized workloads. We've discussed that earlier. Applications such as compute heavy gaming applications. Compute optimized machines offer 3 different series, H3, C2, and C2D, and you can select the series of your choice and see whether it falls within your budget. The most expensive here is the H3 series, $3,600 a month. If you're running memory heavy workloads, you'll of course go for a memory optimized machine, and you can select that tab and view the different series that are available. Notice the monthly estimate, $36,000. In fact, I do not have enough quota to provision this VM. In general, memory optimized machines tend to be quite expensive. Another category here is the storage optimized machine. Go ahead and select that option. There's exactly one option here, again, quite expensive. And if you'd like to train machine learning model, you'll select a machine with a GPU. If you select this drop down here, you'll be able to see all of the different GPU options that you have available, which you can use to provision your machine. You can choose to provision a VM with a single GPU. You can also choose 2 or 4 GPUs. Well, we'll keep things simple. I'm going to go back to the general purpose machine and we'll work with the E2 series, the one which is for low cost day-to-day computing. Virtual machines on the GCP can have predefined configurations. These are the preset VMs that are selected by default, or you can set up your own custom configuration. If your workload has special needs, a custom configuration is what you may choose. Let me show you how the custom configuration works first. Here, you can manually specify the number of cores or vCPUs in your machine and the amount of memory in your machine. Simply use the slider to select the right number of cores. And notice that the estimate goes up based on the cores that you've selected. With 16 vCPUs, you're now paying about $272. Similarly, you can explicitly configure the memory requirements for your machine as well. You can add more memory, reduce the memory size. So, these custom options are great for very specialized workloads. Custom configurations tend to be more expensive. GCP offers a whole host of predefined configurations that are likely to suit your use case. You can see by default, the configuration chosen is a machine with 2 vCPUs and 4 GB of memory. If you select this drop down, you'll see all of the predefined machine types available in the general purpose category. Observe that you have standard machines, shared core machines, high memory machines, and high CPU machines, all in the general purpose category. Now, here I'm going to choose an E2 small machine which has zero point 0.5 to 2 vCPUs. It uses a shared core and 2 GB of memory. This less powerful machine is less expensive, only about $13 a month. Shared core machines share a physical CPU core with other VMs, making them more cost effective for light workloads. Standard machines tend to have dedicated CPU cores and they tend to be a little more expensive as compared with shared core machines. Let's choose the E2 standard 2 vCPUs, a dedicated core, and 8 GB of memory, and that's about $50 a month. There is a whole lot of optionality here. Only if one of these options does not suit you will you choose to go for a custom machine type. Because overall, they tend to be more expensive because they have to be customized for your use case. I'll leave it to you to explore the high memory and high CPU variants in the general purpose machine category. These machines are different from the compute optimized and memory optimized machines that we looked at earlier. These tend to be less powerful and thus less expensive. I'm just going to go for the cheapest option there is, a shared core machine. I'm going to choose the E2 micro option. You can see that it contains only 1 GB of memory and up to 2 vCPUs. You can see that this is a very low cost option. It's only going to cost me about $7 a month. The next bit of configuration that you can specify for your virtual machine is the provisioning model. There are two choices here, standard or spot. The standard provisioning model gives you a dedicated virtual machine that's always available whenever you need it. The spot provisioning model gives you a preemptible or a spot instance. The instance is available to you at a lower cost, but Google can preempt or take away that instance whenever it has need for additional resources. Let's scroll down and take a look at some of the other configuration options. We come to the configuration of the boot disk. The boot disk is a persistent disk that contains the operating system image and is used to boot a virtual machine instance. A boot disk is automatically attached to your VM, providing the necessary system files and configurations for the VM to start and run. You can see the size of the boot disk is 10 GB by default, and the image that is chosen to be installed by default is the Linux 12 bookworm image. This image has no license and can be accessed for free. Now, you can, of course, change this if you want. If you click on change, this will bring up a little dialog that allows you to configure the image and the size of the boot disk. You can choose from public images, custom images, snapshots, archive snapshots, and other existing disks. All of these options are ways to configure your boot disk. Now you can see that the operating system installed on the boot disk by default is Debian Linux, which is open source and thus free. But there are other operating systems that you might want to choose. Maybe you want Ubuntu, maybe you want Windows Server, maybe you want Rocky Linux. If you choose any of the other operating systems, you'll have to pay a license fee. Let's say you stick with Debian, you can also choose the version of Debian you want installed. We have the latest version, version 12, but you can go for an earlier version as well. You can also choose the type of disk that you want for your boot disk. Balanced persistent disk, an SSD, a standard persistent disk. These are all the options. Switching to a different operating system image and a different persistent disk size will change your VM pricing. Let's stick with the Debian GNU Linux. No change to the operating system and the default persistent disk. And let's move on and look at some other configuration options. The next thing is identity and API access. This is where we configure the service account for the VM. You can see that this is set to the Compute Engine default service account. Now, service accounts are a more advanced topic that we'll discuss later on in this journey, but let me briefly introduce them to you. Service accounts are special accounts designed for use by applications and virtual machine instances rather than individual users. Now, you are logged in with your Google Cloud account. A service account is an account similar to that, except that it's an account to represent software or VM instances. If the software running on your VM instance requires special permissions to access other Google Cloud services, let's say it needs to access a database, it needs to run under an identity which can then be assigned the permissions required to access the database. What's the identity of your software? Well, it comes from a service account. Service accounts allow secure access to GCP services by authenticating applications and instances, enabling them to interact with other GCP resources without user intervention. It makes no sense to allow software to run under an actual user's identity. That user might have additional permissions that you don't want the software to have. And this is exactly why we need service accounts. Now, you might wonder where the service account came from. Well, when you set up your project, a service account for Compute Engine virtual machines was automatically created, and that's the service account assigned to your VM. The service account is an email address just like your Google account, except that this is an email address of an application or a VM instance. Whatever permissions you need to assign your instance, you'll assign those permissions to this service account. Well, we'll discuss service accounts in more detail, but it's important that you understand what they are for. Access scopes allow you to specify the type and level of API access to grant to the VMs. I'm just going to set this to full access to cloud APIs. You can give default access that allows access to only certain APIs, or you can manually configure the access that this VM has to each individual API. Next, you can configure the firewall rules that apply to your virtual machine. Now, let's say your virtual machine is going to host some website. You need to allow HTTP traffic to reach your virtual machine. By selecting this checkbox, you automatically set up a firewall rule on the network where this VM is provisioned to allow HTTP traffic to reach your machine. A firewall rule basically controls the flow of traffic on the network. You should select this option only if you need external HTTP traffic to reach your machine. If your machine is only going to be accessed by internal resources, you do not need this. There are many more configuration options for your virtual machines. If you expand advanced options, you'll be able to see the various sections. You can configure networking options, the disks that you attach to your VMs. You can configure additional disks if you want to. You can set up security. Shielded VMs prevent the tampering of the boot sequence of the machine. There are management options, and you can also choose to host this VM on a sole tenant node so that the underlying hardware is not shared across projects. We'll only briefly look at some of these configurations, starting with networking. There's really just one important thing that I'd like to discuss here. Under network interfaces, notice that this virtual machine is automatically provisioned on the default network. If you remember, we discussed this earlier. When you set up your Google Cloud project, a virtual private cloud or a network is automatically provisioned as a part of that project. That network is called the default network. This automatic provisioning of a network ensures that if you're setting up VMs or databases, you do not have to worry about networking. There is a network already there and available for you to use. If you want to provision your VM on a separate network, you need to create that network first, then explicitly configure it here. If you want to expand the size of the persistent disk available to your VM, under this section, you can add new persistent disks. The security section is where you turn on and configure additional security for your virtual machine. A shielded VM is a type of virtual machine that provides advanced security features to protect against rootkits, bootkits, and other persistent malware. There are a whole host of options under management. This is where you can set up deletion protection for your virtual machines. You can set up encryptions for the data stored in your VM and so on. And under sole tenancy, you can see that's not available for this kind of machine. Now that you have an overview of some of the most common configuration options that you can choose for your VM, let's go ahead and finally create our virtual machine with our current configuration. Once it's available, you should see a green check mark next to your VM instance to indicate that it's running successfully. At this point, you've created your very first virtual machine and you have a fairly good idea about the different configuration settings that go into setting up your VM. We discussed many of these configuration settings as a part of the theoretical overview of Compute Engine VMs earlier on in this journey. However, when you actually see these configuration settings when you're setting up your virtual machine, things become much clearer and you tend to remember them. Now, let's click through to this instance 1 virtual machine that we've created and take a look. This virtual machine details page allows you to quickly review the details of the virtual machine, the configuration of the virtual machine that you've just created. Observe under basic information, you can see the name of the information, the instance ID, which is a unique identifier that Google assigns. You can see the status is running. You can see when the instance was created, the zone where the instance is provisioned, US Central 1A in Iowa. As you scroll down on this page, you can see the configuration settings that were set up for this machine. Many of these we configured explicitly, others are the default values. If you remember, in the firewall settings, we had enabled HTTP traffic to this machine. HTTP traffic is on. Observe that network tags is set to HTTP server. This is not something that we had configured. It turns out that when you actually enable HTTP traffic, Google automatically assigns this HTTP server network tag as a way to tag your virtual machine as a VM that should be able to receive HTTP traffic. There's one last thing I'd like to show you, something that we've discussed earlier. If you look at the network interface, you can see that this VM was provisioned on the default network and the default subnetwork within the default network. This is the virtual network that was set up by default when our project was created, behind the scenes by Google. Google automatically sets up some basic monitoring on your virtual machine instance. You can configure additional monitoring if you want to. If you head over to observability, you'll find a number of graphs showing you different features of your virtual machine. You can see the disk throughput, logs by severities, disk IO metrics, and a number of other operations automatically available for you to use. Now, let's head over to the logs for this particular VM. Logs are detailed records of events, actions, and transactions that occur within an application, system, or network. Logs capture various activities related to cloud resources, such as user actions, system behavior, and other security events. You can see the few logs that were generated when this VM was provisioned. If any errors occur during VM provisioning, they ought to be captured here. If you remember, when we configured our virtual machine, a boot disk was automatically attached to the VM. That boot disk is what helps the VM start up. On the left, under storage, if you head over to the disks link, you should find the boot disk available here. This is the boot disk that starts up our virtual machine instance. Let's go back to the main VM instance page and I'll show you how you can create a clone of your current virtual machine. Clicking on that little VM instance icon will take you to the main page. Here you can see the single instance that we have created, instance 1. Let's click through to instance 1 and on the top you can see several links for what you can do with this instance. Note the create similar link, that's the one I'm going to click. This link will allow me to create an instance with an identical configuration to one that I already have. All of the configuration details will be set to the same values that we had for our old instance, and you can change any specific detail that you want to. Now, I've changed the instance name to instance02, but you can go ahead and make any other changes based on your needs. Now, I've set the zone to any, meaning this instance could be created in any zone within US Central 1. I'm just going to leave the other configurations as is, no change at all, and I click on Create. Instance 2 should also be created. You can see that instance 02 is located in a different zone in the same region, US Central 1F. Now, I want to point out some other interesting details here. Observe that each instance has two IP address. There is an internal IP address and there is an external IP address. Why two IP addresses? The internal IP address is an IP address that is available to all instances that are provisioned on the same network. For example, you might be referenced by a nickname within your family, but you have a real name that others, like your friends and colleagues, use. The internal IP address is kind of like the family nickname. Only virtual machines which are provisioned on the same network can use the internal IP address to access and refer to that instance. If you'd like to access these machines from outside of the network, that is from anywhere in the world, anywhere in the broad internet, you have to use the external IP address. The external IP address is what is visible to the rest of the world. So that's like your real name or your professional name. Observe that both of these VMs are located and provisioned on the default network. This means when these VMs talk to each other, they can reference each other using the internal IP. Now you've provisioned your virtual machines. What if you want to install software on these virtual machines? Well, you need to connect to them. Click through to instance 1, and here on top, you should see an option to SSH into that instance. If you click on the drop down, you'll see different methods that are available to SSH into the instance. I'm just going to open in browser window, which will open up a new tab and connect to that instance using SSH. SSH or Secure Shell is a cryptographic network protocol used for securely accessing and managing remote servers over an unsecured network. It provides strong authentication and encrypted data communication, ensuring that the data transmitted between the client and server remains confidential. If you look at the prompt, you can see that I'm connected to the terminal for instance 1 via SSH. Now, because this is a Debian machine, I can run Debian commands here. If I run who am I, it'll give me the logged in account, that is just cloud user, the account that I've used to log in to the GCP. If you run the hostname command, that'll give you the hostname of the server that you're connected to. We'd only specified the hostname instance 01, but there is a complete hostname on the GCP instance 01.c project ID looney GCP CDL dot internal. Now that you've SSH'd into it and you have root access to this machine, you can treat it like any other machine and install whatever software it is that you need. For example, let's say you wanted to use the NeoFetch utility. NeoFetch is just a command line system information tool that displays your system's information alongside an ASCII art logo of the distribution. Now, how would you actually install this command line utility on a regular Linux distribution? Well, you'd use the apt install command. Apt is the package management tool used for handling packages on Debian based systems, and install is the command to install a specified package. The sudo command runs the command with superuser root privileges, which is necessary for installing software. This will prove to you that by SSHing into the machine, I have root privileges on this machine. I say yes and go ahead and complete the installation. I should now be able to use the NeoFetch tool to view the system information. Simply run NeoFetch and you can see the details of the current system. I'm logged in as cloud user, the host name of the system instance 0.c.looney GCP CDL.internal. You can see the version of the OS that's running. The host is Google Compute Engine because this is a Compute Engine VM. And you get a whole bunch of machine details as well, the kernel, the packages, the CPU, the memory, and so on and so forth. Instance 1 has been provisioned on the default network, and instance 2 is also provisioned on the default network. Now, because they are on the same network, you can actually use the name of the instance to communicate with the instance. I'm going to use ping, which is just a network utility used to test the reachability of a host on an IP network and to measure the round trip time for messages sent from the originating host to a destination computer. Ping instance 2 will check whether instance 2 is reachable from instance 1, and -c4 will send 4 messages. And you can see that we get a response from instance 2, indicating that when you just reference the instance by name within the same network, that instance is reachable. If you remember, I'd spoken about the two IP addresses assigned to the virtual machines, the internal IP and the external IP. You'll notice that instance 1 can reference or reach instance 2 using both of the IP addresses. I'm going to copy over the external IP address of instance 2 and I'm going to run the same ping command, but this time I specify the IP address of instance 2 and I'm pinging from instance 1. This external IP address is reachable from instance 1 and you can see that the ping command is successful. Since instance 1 is on the same network as instance 2, you can use the internal IP address of instance 2 to ping instance 2 from instance 1. Here I run the ping command using the internal IP address of instance 2 and you can see that instance 2 is reachable via its internal IP as well. Now let me prove what I said about the internal and external IP addresses. I've switched over to the terminal window on my local machine where I have the ping utility installed. My local machine is clearly not on the GCP, it's definitely not on the default network. Now, if I were to try and ping instance 2 using its external IP address, I'm going to copy over the external IP of instance 2, you'll see that this is possible. I can use the external IP address to reach instance 2. That's available on the internet. But let's say I tried to reach instance 2 using its internal IP address. Well, let's see what happens. I'm going to copy over the internal IP address of instance 2 and from my local machine, which is not on the default network, I'm going to try and ping instance 2 using the internal IP. And you can see that it's not accessible. The internal IP is accessible only for virtual machines provisioned on the same network. This is the default secure configuration that Google sets up via its firewall rules. The default firewall rules allow VMs on the same network to communicate via the internal IP address, and any external communication has to be via the external IP address. We've seen how you can create a virtual machine instance using the Cloud Console, that is Google Cloud's user interface. But let's say that the people in your team need to write scripts to automate the creation of virtual machines. You're not going to be using the UI. You're going to be using the G-Cloud command line tool. The tab that I have open right now is Cloud Shell, and you can see the Cloud Shell prompt. Now, the Cloud Shell prompt is such that it doesn't know what project I'm working on, so I need to run the gcloud command, gcloud config set project looney GCP CDL in order to tell Cloud Shell what project the resources should be provisioned in. This is important before you go ahead and start provisioning VMs and so on. Notice that the prompt has changed and the project ID now shows up as a part of the prompt. Now let me show you how you can use a command line to provision a virtual machine. Now the command that you'll use is compute instances create. So gcloud compute instances create. Now if you don't know how to use this command, you can use the help feature. Gcloud help compute instances create will show you how exactly this command can be used and all the different flags that you can pass in to configure your virtual machine. You also get explanations for every flag. The CLI allows you to specify all options that you can see in the UI and more. The CLI flags are usually a superset what's available in the UI. Let me just hit Q to quit out of this and let's create our first instance. If you don't specify any configuration flags, the instance will be created using default values. All I've specified here is the name of the instance, gcloud compute instances create instance 03. Now, I have to indicate what zone I want to provision this instance in. In addition to the name of the instance, the zone is also a required property. Now, by default, gcloud asks me, did you mean this zone, Asia Southeast 1B? That's the default zone for me. I'm just going to say no. I type in an N and it will list out all possible zones that I can use to provision my instance. Let's say I want to provision my instance in Asia East 2A. I select the numeric value 7. Let me go ahead and specify 7 here at the bottom. Go ahead and hit enter and this instance will be provisioned in the zone that I've selected. Now you can actually head over to the VM instances UI, and if you hit refresh, you should be able to see that this instance 03 is currently provisioning. Observe that instance 03 has been created in Asia East 2A and it's provisioned on the default network. The configuration properties for instance 03 will be default values that gcloud has assumed. So we have the instance name, we have the instance ID, the zone we specified, but all other configuration properties are set to be the default. So for example, if you look at the machine configuration, the machine type was set to N1 standard 1 by default. It's a machine of an older generation and less powerful than the newer machine series. Let's go back to Cloud Shell and you can see that the command has run through successfully. And you can see the successful status running printed out to screen. You can use the gcloud CLI to perform other operations on VM instances. Let's say you want to see all of the VMs that are available within the current project. You'll run gcloud compute instances list, and this will list out the details of all provisioned virtual machines and their current status. You can also perform other operations on instances. On the Google Cloud, it's possible for you to stop an instance running. And you can run a gcloud command for this. Gcloud compute instances stop, specify the name of the instance, instance 03, and the zone where the instance is provisioned, and this will stop the instance. If the instance has stopped, any application that you have posted on that instance, well, that won't work. It's like shutting down an instance. If you head back to your VM instances page and hit refresh, you should be able to see the updated status of instance 3. You can see the little icon next to instance 3 has changed, and you can see that instance 3 no longer has an external IP. That's because it's currently in the stopped state. Stopping an instance, restarting it, all of these operations are also available on the UI. Let's continue using the gcloud tool, and I restart instance 3. gcloud compute instances start. Make sure you specify the name and the zone of the instance. You may have to wait a few seconds, but soon you'll find that the instance is back up and running. And of course, if you go back to the Cloud Console, the VM instances page, and hit refresh, you should be able to see the updated status of instance 3. It's now currently running and it has an internal IP as well as an external IP. As long as your VM is up and running, you're paying for that virtual machine. If you no longer need a virtual machine, you should go ahead and delete that instance. And you can do that in gcloud or even the UI. gcloud compute instances delete is the command, specify the name of the instance and the zone where it's provisioned. And this will go ahead and just deprovision and delete the instance, and you'll no longer be billed for it. Make sure you assert yes, you want to delete the instance, and if you look at the UI, you'll see that the instance is being deleted. And in a few moments, the deletion will be successful and instance 3 will no longer exist. When we created instance 3, we specified no configuration via flags when we used the gcloud command line tool. Let me show you how you can provision an instance and specify some configuration parameters. I use gcloud compute instances create once again. The instance name is instance 04. I've used the -- zone flag to indicate the zone where I want this instance to be provisioned, US Central 1C. I've specified the machine type flag as F1 micro, so I want a really small machine. I use the image flag to specify the image I want to install on the instance, and Ubuntu image. Ubuntu is just a Linux distribution. I also specify the image project, that's the Debian Cloud. That's the project which contains the image. And then I specify the size of the boot disk as 12 GB. There are, of course, many configuration options for VMs, and all of them can be specified via the command line using flags. Here I've just shown you a small sample. Let's go ahead and create this VM. I get a warning saying my boot disk size is rather small, but that's fine. I'm not planning to do much with this VM. And you can see that soon the VM is up and running. And if I go back to the VM instances page, I should see instance 4 provision there. If you want to see the configuration of this instance, you can click through to the instance and view the details. I'll just point out one thing to you. Under firewalls, notice that both HTTP and HTTPS traffic has been turned off. That's the default setting. This means if you were to host an application on this instance, well, HTTP traffic would not be able to reach this VM. I've already shown you how you can connect to VMs using the Cloud Console, that is the UI. Let me show you that you can SSH into virtual machines using the gcloud tool as well. You can run gcloud compute SSH that allows you to specify the virtual machine that you want to connect to. I've indicated the zone where the VM is provisioned, US Central 1C, the name of the VM instance, instance 4, and the project where it's provisioned, Luni GCP CDL. Though, if you have the project configured on your Cloud Shell command line, well, you don't need to explicitly specify the project here. Once this command runs through, you're actually connected to the virtual machine, meaning the terminal that you see here is the terminal for instance 04. If you look at the prompt at the bottom, you can see that we are connected to cloud user at instance 04. This indicates that any terminal operation that I run right now will be run on instance 04 and not on the Cloud Shell machine. So, for example, if I were to run the sudo apt update command, this will retrieve the latest package information from the configured repositories, that is, the Debian Linux systems repositories. Now, if I wanted to install NeoFetch on this instance, instance 04, I can run sudo apt install NeoFetch and NeoFetch will be installed on the virtual machine. So all operations that I run here are on the VM and not in Cloud Shell. Let's run NeoFetch and you can see all of the system configuration of the VM. ASCII Art is different because this VM runs Ubuntu. If you want to get out of this connection, if you want to exit this connection, simply type the exit command. This will bring you back to Cloud Shell. Even if you didn't actually perform this hands-on demo, hopefully this has given you a taste of how the gcloud command line utility can be used to work with resources on the Google Cloud. Here I am on the VM instances page. We have 3 VMs running, instance 1, 2, and 4. If you look at the structure of the internal IP address, the format in which it's displayed, it's the same for all 3 VMs. The IP addresses are of course different. If you look at how the external IP address is displayed for the 3 virtual machines, you can see there is a difference. Instance 4 does not have a link for the IP address, whereas instance 1 and 2, the IP address is a link and there's also a little arrow next to that link. Now, why is this the case? Well, we discussed this earlier. Instance 04 does not have HTTP or HTTPS enabled. That is, the firewall rules that have been configured on the default network will not allow HTTP traffic to reach instance 4. And that's why the external IP address is displayed differently. HTTP traffic can reach instance 1 and 2, but cannot reach 4. Now let's click through to instance 4 and change this. Let's enable HTTP so that HTTP traffic can reach instance 4. There are certain configuration parameters of the VM that you can edit while the VM is running, and enabling HTTP is one of them. Click on the edit link and let's edit this instance. Under firewall, I'm going to allow HTTP traffic to flow to instance 4. Notice that as soon as I click this checkbox, a network tag was added to instance 4. A network tag is just a marker that firewall rules use in order to figure out what virtual machines can accept HTTP traffic. It's just a way of directing firewall rules at certain VM instances. Let's go ahead and save the changes that we've made. And once the saving is complete, if you look at instance 04, you'll see that HTTP traffic has been turned on and we have the HTTP server network tag on this virtual machine. Now that we've configured this VM instance so that it can accept HTTP traffic, let's do something interesting. Let's log into this VM, that is SSH into this VM, and let's deploy a very simple website on this virtual machine and see whether we can access that website on port 80. I've successfully SSH'd into the instance 04 virtual machine. And my objective here is to run a very simple Python web application on port 80 and see whether we can access and view the web app. Now I'm going to run a bunch of operations to install the libraries that I need to run a simple Python web application. You don't need to know the exact details of what's going on. I'll make sure you have a good high-level understanding of the steps that I'm performing. Now, in order to install the Python library that I need to run the web app, I need the Python package manager, that is pip. So I use sudo apt install python 3 pip in order to download the Python package manager on this VM instance. The Python package manager is not available by default on the Ubuntu VM. Go ahead and say yes, I want to continue. And in a few moments, the Python package manager pip will have been installed. Now, this Ubuntu VM already has Python installed. If you run Python 3 version, you can see that Python 3.8.10 is available. This means that I should be able to run a Python web application. I just installed the Python package manager pip. Let's make sure pip is available. I run pip3 dash dash version, and you can see that pip is indeed available now for me to use, version 20.0.2. Well, with pip available, I can install Flask. Flask is just a lightweight web framework for Python that is designed to make it easy to build web applications quickly and with a minimal amount of code. We need the Flask library in order to run the code for our web app. So I install Flask and make sure you use sudo so you run with root privileges. And this will make sure that the Flask library is downloaded and available for us to use on this VM. The next thing is for us to set up our web app. I'm going to use the Nano editor to create and edit a Python file, app.file, that will contain the code for our app. Now, the code is very straightforward. Don't worry about all the code that you see here. You don't need to understand these details. What you do need to know is that when we actually hit this app, you should get an H1 header that displays GCP VMs are fun. Also, that the app will run on port 80 of the local machine. Hit Ctrl X to save the changes that you made to this file. File name to write is app.py. Hit enter, and this file should be saved, and you should go back to your terminal window. In order to run the web application, all you need to run is sudo python 3 app.py. This will bring up a web application that is hosted on your virtual machine, and you can access this web application on port 80. You can see that in the output. We know that HTTP traffic is enabled on this VM. Can we actually view this app on the VM? Let's find out. Here on the VM instances page, the first thing to note for instance 4 is how its external IP address looks. Because we've now allowed HTTP traffic to reach this virtual machine, observe that the external IP address is now in the form of a link and there's a little arrow next to it. We can actually click on this IP address to view the application that we've hosted on this virtual machine. Let's click through, and there we see it. GCP VMs are fun. This application is available over HTTP, and that's why you see the not secure there on the browser. We only have the IP address. We do not specify port 80 because that is the default port for any machine. When you don't specify a port, port 80 is assumed. We've successfully enabled HTTP for our VM instance and deployed and run a little website on our VM. In this demo, I'll show you another little bit of configuration that you can apply to your virtual machine. I'll show you how you can set up a startup script. A startup script is a script that runs automatically when a virtual machine instance boots up. These scripts are usually used to perform all kinds of initialization tasks. So, any software that you want to install, any services that you want to configure, any environment variables that you want to set up, all of these can be specified in a startup script. Startup scripts are very, very useful for automating the setup and configuration of your VMs. Startup scripts allows developers and administrators to ensure that the VMs are ready to use as soon as they start up without any manual intervention. In this very simple demo, I'll show you how you can configure a startup script when you create your virtual machine. We'll get the startup script to automatically install a web server on the VM when it starts up and display a simple web page, a customized web page. Now, let's go ahead and create the instance. I'm going to change the name of the instance to be instance 05. I'll leave the instance in US Central 1, that's the region, but let me pick a specific zone. Let me place it in US Central 1A. You can leave the zone as any if you want to. You don't really need to change any of the other configurations. You can choose the default values for all of these, but you do need to allow HTTP traffic to reach this VM. So make sure you select that option under firewall rules. This is important because we're going to have our startup script install a web server and we want HTTP traffic to reach the web server. Now you configure startup scripts under advanced options. So go ahead and expand that. you'll need to head over to the management section under startup options, and this is where you should see a little section for automation. Here's where you'll specify your startup script. Since this is a Linux virtual machine by default, the startup script that you specify here has to be a Linux bash script. A bash script in Linux is just a text file containing a series of commands written for the bash interpreter. That is the command line interpreter that Linux uses. And these scripts typically automate repetitive tasks. I'll just highlight parts of this bash script. Notice the sudo apt-get install nginx lite y. This is where we install the nginx web server. Nginx is just an open source web server that allows you to host web applications. The lines at the center, starting with sudo and ending with EOF, simply sets up an HTML file in the default directory from where Nginx will serve HTML resources. The HTML page of our website should just display the text GCP VMs are fun and a little paragraph body, startup script web server set up successfully. And then at the bottom, sudo service nginx start just brings up the nginx server. And that's it. This is all we need to do to configure a startup script. Just click on create and wait for this virtual machine instance to be created, and it'll be up and running in no time at all. Notice the external IP address of instance 5. It has a little arrow next to it indicating that HTTP traffic can flow to this instance. Well, that's good, but did the startup script actually run? Well, let's click on that IP address and take a look. You can copy the IP address over and paste it into your browser. The Nginx server will run on port 80 by default, so that's where you should be able to access our web page. And there you see it, the web page that we had configured in our startup script. GCP VMs are fun. And the startup script web server set up successfully. Startup scripts in virtual machines are very, very useful for tasks such as file manipulation, program execution, and system monitoring. Something that you want to run every time a VM starts up. Startup scripts tend to be a powerful tool for system administrators and developers. When we introduced Google Compute Engine virtual machines, we spoke of snapshots. Snapshots are point in time copies of data stored on a disk, typically used for backup, recovery, and data migration purposes. Snapshots capture the state of a persistent disk, allowing you to create backups of your VM instances disks. These snapshots can be used to restore data to its previous state or to create new disks based on the snapshot. Snapshots are thus a convenient way to recover from data loss or to copy disk content across different instances or projects. Now, let me show you how you can create a point in time snapshot of the disk associated with instance 5. I'm going to click through to instance 5, and this will show me its configuration details. In order to take a snapshot of the persistent disk associated with this VM, we need to open up the left navigation pane and head over to snapshots under storage. This is where we can create our snapshots. This is the page for the snapshot service. This is the very first time we are using it. That's why here it's completely empty. We haven't created any snapshots. Let's go ahead and fix this. Click on the create snapshot link here, and this is where you set up a snapshot. Every snapshot should have a meaningful name. I'm going to call this instance 5 snapshot 1 because the snapshot is of the disk that is connected to instance 5. It's useful to have a description associated with your snapshot so you know exactly what the snapshot represents. Snapshot of instance 5 with Nginx installed. Remember, instance 5 is the instance that we configured with the startup script. So when the instance came up, Nginx was installed on the disk associated with that instance. That's the disk that we are going to be snapshotting here. The snapshot source type says disk, or you can take an instant snapshot. An instant snapshot is just a feature that allows you to quickly create a snapshot of a persistent disk with minimal disruption to running applications. A disk snapshot, which is what we'll select, takes much longer to complete and may affect the performance of the disk during the snapshot process. Well, I don't really care about that. Let's go ahead and choose a disk snapshot. Next, you need to specify what is the disk that you want to snapshot. And here I select the disk associated with instance 5. That's the one that has my Nginx server. There are other configuration options here. Let's just ignore those and go ahead and create a snapshot. Click on the create button. The great thing about a snapshot is you can use the snapshot of your persistent disk at a certain point in time to create and instantiate another virtual machine. And the new virtual machine's disk will contain the same contents as your snapshot disk. Let's go back to the VM instances page and click on create instance. I'm going to create this instance from the snapshot that we've just taken. Call this instance 06. You can leave this instance in US Central 1 Iowa. Let's place it in US Central 1A, or you can place it anywhere, that doesn't really matter. Scroll down to where you can configure the boot disk for this VM. Let's change this so that the boot disk uses our custom snapshot. This brings up a little dialog. Notice the tabs there. Go to the snapshots tab. We should have a snapshot available, the one that we just took. Notice instance 5 snapshot 01. Go ahead and select that. This is a snapshot of an original 10 GB disk. So this new disk is also of size 10 GB. That's totally fine. It should match. Go ahead and hit select. Now the only change I've made is that I'm using a snapshotted disk. I'm also going to allow HTTP traffic to this virtual machine because it's going to have the Nginx server running. That's the Nginx server that we installed on instance 5 using a startup script. We snapshotted that disk, and the snapshot disk that this VM uses, well, that's also going to have the Nginx server running. Go ahead and create this instance. In a few moments, instance 6 should be up and available. Notice this external IP. That's a link that can clearly be clicked on. Copy this over to the clipboard and let's paste that in. Let's see if the Nginx server is available, and indeed it is. We've successfully taken a snapshot of a persistent disk and instantiated a new virtual machine using the snapshot. This brings us to the very end of this course on compute on the Google Cloud. We started this course off by exploring the compute capabilities on Google Cloud. We dove into the specifics of compute engine configuration, learning about the various options and settings available for optimizing performance and cost. Additionally, we covered other essential Google Compute Engine concepts, which gave us a comprehensive understanding of how compute resources are managed and utilized within the Google Cloud. Next, we learned how to navigate to the Google Cloud Compute Engine page and create an instance. We configured the region, zone, and the machine type, ensuring we understood the implications of each choice. We completed the VM configuration by specifying the boot disk, setting up service accounts, and viewing the networking management and other configuration options. We also practiced connecting to VMs using SSH, which is crucial for managing and interacting with our instances. Finally, we explored using the G-Cloud command line tool to work with instances. We gained practical skills in managing VMs through commands. We ran a simple website on a VM, configured startup scripts to automate tasks, and learned how to snapshot a disk and create a VM using that snapshot. These hands-on activities provided us with the practical experience needed to effectively manage and deploy applications on Google Cloud. In conclusion, we've built a strong foundation in Google Cloud's compute services by understanding compute engine configurations, creating and managing instances, and utilizing advanced features like startup scripts and snapshots. You're now ready to tackle the next course in this learning journey: data storage and management concepts.